I'm assuming that you don't know anything in this subject, so I'm going from basics. I'll just teach you basics, and after that we shall go into problems and solve them. So in all the formulas, the same thing has happened. That is called dual. Whenever you want to design any electronic circuit, first the procedure is switching expression is a finite number of combinations of switching variables. What do we mean by canonical form? There are two types of canonical forms. Many expressions represent the same function, but then so whatever is the value of a, F4 got it. If any function, any Boolean function can be represented using Venn diagram or using contact representation. In computer science, you could easily solve this and get 4 marks question easily. So the basic element of Boolean algebra is a Boolean variable. So why the name Boolean algebra is switching algebra and Boolean algebra is here we have any variable will take two values. One is 0, other is 1. So they are just like true and false. Okay, so 0 means false and 1 means true. You can even compare it that way. Now the basic element of switching algebra is a Boolean variable, and a Boolean variable can take 0 or 1, and the main operators that we have in switching algebra is like this. So we have only two values here to consider. One is 0 and 1 because we are talking about only Boolean variables, and then switching algebra contains operators like this. One is or and not. Okay, or and not. I'm assuming that you don't know anything in this subject, so I'm going from basics, maybe 2 or 3 videos. Just bear with me. I'll just teach you basics, and after that we shall go into problems and solve them. Okay, and now you must be knowing all this. Still, let me do it now. Anding of 0 when ANDed with 0, the value is 0. 0 when ANDed with 1, the value is 0. 1 when ANDed with 0, the value is 0. 1 when ANDed with 1, the value is 1. Right? Similarly, OR. About OR, 0 0 ORing is 0. 0 1 ORing is 1. 1 0 ORing is 1. 1 1 ORing is 1. Right? Similarly, NOT. If I have NOT of 0, it is also called as a complement or prime or not. Everything is same, right? So sometimes complement, sometimes not, and sometimes prime. It is ORing, or sometimes it is actually similar to union, and AND is similar to concatenation. But here let's fix to these names OR and AND. Okay, and then 0 means 0, not means 1, and 1 not means 0, right? So with these basics, let's see the properties that are the basic properties of the switching algebra to understand how the switching algebra works. So here are the rules that we have here. Idempotency. Idempotency means this one. X when ANDed with X, the value is going to be X. So if you want to know whether any equation is, sometimes some equation will be given, and if you want to know whether it is really true or not, which means if the left hand side is equal to right hand side, what you do is construct the truth table. Truth table means like this. Construct the truth table and see what is the expression that you are getting for, what are the truth values you are getting for LHS, and what are the truth values you are getting for RHS. In case if they both are equal for every combination of the input, then both are right. So maybe if you have any doubt, you could just construct the truth table and then see what is LHS and what is RHS. If X is taking a value 0, and what will be this 0.0, 0. And if X is taking a value of 1, what is 1.1, 1. Therefore both are equivalent. This is how you should check. I'm just saying you from next time onwards you check it. Okay, so x dot x, it is verified. X plus x, it is verified. Now x plus 1, anything when you are with 1, the result is going to be 1. The reason is simple. Check this. Anywhere you are ORing anything with 1, right? Whenever you see 1, then the result is going to be 1 irrespective of what the other value is, right? And anything when you AND with 0, the result is 0. Check this. Anything when you AND with 0, the result is 0, right? Unless and until the both values are 1 1, AND will always produce a 0. Got it? And anything when OR with 0 will be the same thing, and these are all trivial. You must be knowing it. Next one is commutative. So commutativity means commutative means this way. So an operator is given and operands are given. Can you just interchange the position of the operators, these operands, and is that operator value still valid for the other combination? Which means this operator is given and operands are given, can you just interchange them and still say that they are valid? Yes, they are valid, right? And here for AND also it is same. And now associativity. Associativity means, so let me just explain you associativity once more here. What is the real meaning of associativity? Means we have two types of associativity, left associativity, right associativity, like this. See, associativity arises when we have a ambiguity. Ambiguity in the sense, if I have operand 1 and then some operator and then operand 2 and then some operator and then operand 3. Let us say we have this, which means I have something like A or B or C, right? If you have anything like this, then what happens is, this one, if this one and this one both are having equal priority, then we don't know which one we should associate this operand to. For example, should I associate this operand to this plus, or should I associate this operand to this plus? If I have to associate this operand with this plus, then this is what it is. If I am associating a operand to the left side operator, then this operator is called left associative. Okay? If I am associating a operand to the left side operator, then it is called left associative. When is it applied is, whenever two operators are of same priority, then when we are associating an operand to the left side operator first, then this operator is called left associative. Keep that in mind. And if I associate with like this, then this operator is called right associative, right? So left associative and right associative is defined whenever any operand has two operators on either sides, and now we can associate it with either the left side operator or to the right side operator, right? Now watch this one, that is associativity. So now if you are writing like this, what is that you are effectively doing is, if you have 2 plus, which means if you have two R symbols, and now both are of equal priority, obviously both are of equal precedence, right? So precedence is same. Now when the precedence is same, you are associating Y to the left side operator, right? Therefore in this expression, X is evaluated as if X is left associative, right? And if you look at it, Y is associated with the right side operator, which means here Y is evaluated as if it is right associative, right? Therefore both are equivalent. So what does it mean? Here plus is both left associative as well as right associative, right? So that is the meaning of it. Same thing is happening to AND also, right? So R is left associative and right associative, and AND is left associative and right associative, right? And next one is complementation. So complementation means, you know that one I have shown you. 0 complement is 1, 1 complement is 0. Now if you want to see whether this is right or wrong, you have to actually assign some truth values and check it out. Okay, so if X is 0, then what happens to X complement? X complement becomes 1. Therefore 0 or 1 becomes 1. If X is 1, then X complement is 0. Therefore 0 or 1 again becomes 1. So at any time in discrete mathematics is also called as tautology. Tautology means it will always be true. The reason is either X will be 1 or X complement will be 1. So at least one of them is going to be 1, and therefore the entire result is going to be always 1. It is called tautology. It will always produce true, right? And what about this one? X dot X. See, I am talking about in the language of discrete mathematics. We shall again look at it there. Okay, now just leave it. Now X dot X. So what does it mean? If X is 0, X complement will be 1. If X is 1, X complement will be 0, right? So anyway, either X or X complement is always going to be 0. Therefore the ANDing is going to be 0. That is the meaning of it. Next one is distributivity. So distribution means is one operator distributed over other operator. So check this. Now X, Y, Z and plus is given. Now here there is AND. So AND is actually distributive over plus, which means we can take the AND and distribute it to both the operators which are having OR. Therefore this is nothing but XY plus YZ, right? And here it is interesting. You must be knowing about this from mathematics. In mathematics it is perfectly valid, right? But then in mathematics it is not valid. Check this. Now I am saying that plus is distributive over dot, which means or is distributive over and. Check this, x plus yz is written as x plus y into x plus z. It is very important because you might, you don't see it in mathematics. In mathematics language we don't have this, right? I cannot write a plus bc equal to a plus b into a plus c, but then here you could write it. Okay, first of all, how could you know that these two are equal, or how could you know that these two are equal? Construct the truth table and then check if LHS equal to RHS or not. That procedure is going to be lengthy, but then that is the only procedure we have. Or if you have any doubt, maybe just give some assignment to x, y and z and you can check it out. Okay, so let's say you have a doubt about this, whether these are equal or not. How to check such expressions is give some value to x. I mean, I'm talking about fast checking. See, the basic procedure is, if you want to check whether an expression is, this equality is right or wrong, you are supposed to construct the entire truth table. How does the truth table look like? See this. The truth table contains x, y, z. You have to construct entire thing. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. You have to construct all the 8 values. 1, 2, 3, 4, 5, 6, 7, 8, and then you have to evaluate this one and you have to find out what the value of that function is, and then you have to evaluate this function and then find out what the value of that function is. If both the functions are having the same values, then you can say that both are equal. But then if you want to do it fast, I mean, in exam, if this is not the question actually given, in exam if some other complex question is given and if you want to say yes or no fast, what you could do is, only in place of x substitute 0 and check both the terms, and only in place of x put 1 and check both of them. In place of x, if I put 0, then what happens? The entire term becomes zeros, and in place of x, if I put 0, right hand side becoming 0, right? Fine. And in place of x, if you put 1, what happens? If I put 1, it is going to be y plus z. If I put 1 here and here, it is becoming y plus z. That is, you can check it faster. Then what about this one? See this, x plus yz and then x plus y into x plus z. How can you check this? Again the same thing. In place, you have to actually construct the entire truth table and then compare it. But then let's do it faster. So let us say in place of x I put 0. If I put 0, this entire term is going to be yz. And in place of x, if I put 0, it is 0, which means the entire term is y, and it is 0, which means entire term is z. Therefore, it becomes yz. Got it? So that is how we could verify it. Now, if you observe these rules, all these rules, you will see one interesting thing. All these rules, you just observe them. You will see one interesting thing. I am writing them in pairs, right? Like a couple. So for every formula, for every equality, there is one more equality, right? And check this. So for this equation equality, there is this equality, right? So just check them. What is the difference? In this one, this plus is made to dot and dot is made to plus, which means if we interchange r into and into r, we are getting the pair, and along with that 0 is changed to 1 and 1 is changed to r. You can take, 0 is changed to 1 and 1 is changed to 0. You can take any such pair and you can observe them. For example, in this one, in all of them, in all these pairs, you could observe one thing commonly you could observe this. See, dot is changed to plus in the corresponding pair, in the corresponding the second formula, and plus is changed to dot, and if there is any 0, it is changed to 1, and if there is any 1, it is changed to 0. In all the formulas you can check it. Watch it. Here plus is changed to dot, 1 is changed to 0, 1 is changed to 0, plus is changed to dot, 0 is changed to 1, right? And then plus is changed to dot, and then plus is changed to dot, right? And plus is changed to dot, plus is changed to dot, and 0 is changed to 1. Here also same thing has happened, right? So in all the formulas, the same thing has happened. That is called dual, like duet, dual, right? Dual means these two are like couples, right? That is the dual, and this property is also called as duality, principle of duality, principle of duality. Okay. Now let's see a switching expression. Whenever you want to design any electronic circuit, first the procedure is we form the switching expressions, and then we minimize it, and then we realize it. Realize it means implement it using AND gate and OR gate. Okay, what is AND gate, OR gate, we shall see it later, but the important thing here is, if you have any switching expression, since we are going to convert it into a circuit, the smaller the expression, the better it is, because if the expression is smaller, the circuit is going to be smaller. So we are very often interested in smallest expressions in terms of either a literal. Literal means any variable which is occurring either in its true form means like A, or its complement form A prime, right? That is called a literal. So I'll just take an example and explain you. So first, now see how does this switching expression look like, and then we shall see how to minimize it. So watch it. Switching expression is a finite number of combinations of switching variables. Switching variables means like A, B, C, D, which are supposed to take A, B, C, D or X, Y, Z, whatever, which are supposed to take only two values, which are 0 and 1, Boolean variables, right? Combination of switching variables and constants. Constants means in switching theory the constants are only 0 and 1 by means of switching operations. So any other operation can be implemented using these operations. Therefore, these are the basic operations or primitive operations or complete. They are functionally complete also. Functionally complete means any operation can be implemented using these operations. Plus, dot and not. If I have AND, OR and NOT gates, NOT operations, and if I have these Boolean variables along with the constants, and if I form any expression, that is called switching expression. Now what is the main purpose of the switching expression is, we will somehow convert it to a digital circuit. The smaller it is, the better. Now how can we know that a switching expression is smaller? Either we decrease the number of terms or we decrease the number of literals. So literals means, check this in this expression. So this is all the expression. Switching expressions look like this. Literals means 1, 2, 3, 4, 5, 6. So even though the variables are 1, 2, 3, the literals present here is 6. Every occurrence of a variable in its true or complement form is called literal. Therefore, I am going to count x, x prime, and again x here. So 6 literals are there. Either you decrease the number of literals or you decrease the number of terms, depending on your definition of minimality. We want to just simplify the switching expression. Now there are various methods of simplification, but the simplest method is, we shall form some rules or formulas, and using which if we can directly simplify it, it is better. Otherwise there are various methods. All the methods are actually equivalent. Now let's see one method using just the formulas. Watch it. First one is properties for simple, and again one more thing, here also the principle of that duality can be applied, which means if you write a formula, the equation, then you could actually substitute AND with OR with AND, plus with 0, 1 with 0 and 0 with 1, and you can get the actual, whatever we did it, we can get the same kind of expression. Now the first one is called absorption. Absorption means, see how it is, x is going to absorb the next term. So how can you write this? X plus x into y. So how can you write this one is, you could write it as x concatenated with 1, x ANDed with 1 plus xy. Then you could pull out x as common. Why? Because dot is distributive over plus. Using that rule, I am pulling out x as common. Then what is remaining? 1 plus y. And you know that 1 plus y is nothing but always 1. So anything odd with 1 is 1. So what is this? Directly x. So it is proved. And even you could write the dual of it, and the same thing will apply. If you write dual of it, what happens? X concatenate x and x plus y equal to x. This is the dual of it, right? So you can prove that this is also equal to this. Simply if you want directly prove it, just you multiply, or just you add x with x, then you get x, and we add x with y, we get xy. Therefore this expression and this expression both are same, and anyway it is already proven to be equal. Duality holds there. Now what about this one? It is interesting. See, how are you going to prove that these two are equivalent is, now we already know that plus is distributive over dot. Therefore x plus y prime, x plus x prime y can be written as x plus x prime and x plus y. and you already know that x plus x prime is 1, therefore what is it, x plus y. So this one is equal to x plus 5, and here also duality holds. So what is the dual of this one? So how can you prove that this is right? Here you can use the rule of and is distributive over R. Therefore you could take this and you can multiply it, right? So I think yeah, and is distributive over R. So how can you do it? X into x prime plus x into y, this one. Now what is x into x prime? It is 0. 0 plus xy, which is nothing but xy. Got it? It is very important. Consensus theorem is very important and is very tricky to understand it. So what we wanted is, we want to simplify this, but in order to simplify it, we'll expand it and again simplify it. See how it works. See, if you had to remember this, definitely as a formula you have to remember this, or we shall practice lots of questions on this. Therefore I think automatically you will remember it. But then see how it works. X into y, I mean x and y, x prime and y and z, which means if there is a expression concatenated with some variable or concatenated with some expression, and then a complement of the expression concatenated with some other expression, and a combination of these two expressions, then these two are actually redundant. Redundant means you can remove them. So okay, one more way of saying redundancy is, just follow this. If the value of expression does not depend on any term, then that term is redundant, which means even if you have the term or even if you don't have the term, if it is not going to be of any difference, then you better remove it. That is called a redundant term. And now in this case, this yz is going to be redundant. So we shall prove it. We shall prove how it is going to be redundant. It is unlike the other proofs. Instead of when we are trying to reduce it, we'll expand it and then reduce it. See this, how it works. Xy plus x prime z plus yz concatenated with 1, ANDed with 1, concatenation. See, by mistake I am saying whenever I say and, I am using concatenated. You please correct it. And now in place of 1, it could be x plus x prime. So it is xy plus x prime z plus yz into x plus x prime, that equal to, so now you can expand it out, xy plus x prime z plus expanded. See, in place of 1 I am writing x plus x prime. I think you understood how it is. It is already a rule. So x plus x prime is 1, that you must be knowing already, right? I am just expanding it out. Then what do I get? Yz into x plus yz into x prime. Then what is this? Check this. Now if you look at these terms, xy and then xyz, if you look at these terms, from these two, xy could be written as xy concatenated with 1. Therefore if you pull out xy from these two, this term and this term, what do we get? Xy into 1 plus, what is remaining here? Z plus. Now from these two terms, if you can see that there is x prime z, right? X prime z. So x prime z is common in both of them. Maybe you can multiply with 1, and if you pull out x prime z from these two terms, then what do you get? X prime z, sorry, if you pull out x prime z, then what do you get? 1 plus y, right? So 1 plus z is nothing but 1, 1 plus y is nothing but 1. Therefore what do you get? That equal to xy plus x prime z, which means this one, right? It is very interesting and very important also. Not direct, you might not see that it is directly possible, but then if you can observe this, it is definitely possible. Okay, so the proof is, whenever there is y, or how to remember it is, in place of x and in place of y, sorry, in place of x and in place of x, there could be any expression. I just generalized it. I just put x, but in place of x and y, there could be any big expression. So even if there is any big expression here, and if there is a complementation of the expression here, and if there are two different expressions here, and there is a concatenation of those, I mean ANDing of those two expressions, always remember this expression is redundant. That is the what can I say, usefulness of this consensus theorem. So we are going to use it very frequently while minimizing the Boolean expressions. This so you just remember it, or you can derive it. Better you remember it. Fine. Now watch this. Simplify this. So given any expression, switching expression, we would like to have a as small expression as possible. Even if it is very big, I want to simplify it, right? So there are various methods. Maybe you could use the consensus theorem, or you could use absorption. Whatever you like, you could use. But finally, one more thing. There are various ways to simplify it, and whatever it is, the final answer should be same. Whatever I do, whatever I get the answer, and whatever you get, both of them should be same, right? Now here, if you look at this, it is very straightforward. It is simple that you are seeing z as common in everything. So pull out z as common. If you pull out z as common, then what do you get? Plus y plus x, isn't it? So it really matters when you are looking at TOC. In TOC, you should always pull, if z is here, you should always pull z from the right side, because in TOC, concatenation is not commutative, which means a dot b is not equal to b dot a. It is concatenation. But here the AND operation is commutative. A dot b is equal to ba. Therefore, either you pull out from the right or pull out from the left, it doesn't matter. So if the z is here, you could either pull out from the left or pull out from the right. It doesn't really matter much. Okay. And now see this. See these two terms. And second rule I am going to apply is, you could apply any rule. I am going to apply the second rule is, plus is distributive over AND. Therefore, I'll take plus and I'll distribute over AND. So what do I get? Z into x prime plus y into y prime plus y, which means I'm just taking this and I'm distributing over here. So y prime plus y and x prime plus y plus x, right? Then what do we get? Z into this entire factor is nothing but 1. Then what is remaining? X prime plus y plus x, right? And now x plus x prime is nothing but 1. So what is it? Z into 1 plus y. So what is it? Completely it is going to be 1. So whatever you got is z. Understood this? So this entire thing can be minimized to z. So we used, luckily it is, it is very simple that you could apply rules and easily do it. But maybe if the expression is very big, we would like to use some other methods. Later we shall see those methods. And one more thing, you might have got some other method to solve this, but the final answer should be same. You please check it. And next one is in switching algebra, you should remember that cancellations is an inverses and cancellations are not allowed. For example, if you have a plus c equal to a plus b, if you have expression like this, some equality like this, then you should not cancel out a and a. And if you have a into c equal to a into b, then you should not cancel out these two. Okay, so you should find out the values of a and c, a, b and c, for which this equality holds. That is the meaning of it, right? You should not cancel out either, you should not cancel out, or you should not do the inversing. So these two operations, these two are not allowed in the switching expressions, right? De Morgan's law states that xy complement, whole complement, is x prime plus y prime, and x plus y whole complement is x prime y prime, right? Or in other words, what De Morgan's law says is, if you have a switching expression, then you could take that expression and convert every variable into its complement, which means every literal has to be replaced with its corresponding complement, and plus has to be replaced with dot, dot has to be replaced with plus, and 0 has to be replaced with 1, and 1 has to be replaced with 0. Okay, I'll write it. See this? Let us say there is a function f, and this function is containing, it is a switching expression. This switching expression is containing all the variables a, b, C, so on. So let us say some Z, just for the sake of example. And now it is containing some constants 0, 1, and it is containing the operators dot and plus, right? Now what I mean is, De Morgan's law says that if you want the complement of this expression, then you take the same expression and you replace every literal with its complement, which means if a variable is occurring as A, you replace it with A complement. If the variable is occurring as B, I mean A complement, replace it with A. So whatever is the occurrence of the literal, you just complement the corresponding one. It doesn't mean that you should make everything as complements. It means that if there is already a true value, make it complement. If there is a complement, make it true, which means like this. If there is A, make it like this, right? Convert A into this, B into this, C into this, and then Z into this. And if there is a 0, convert it into 1, and if there is a 1, convert it into 0, and if there is a plus, convert it to dot to plus and plus to dot, like this. So if you convert everything, he is saying that whatever you get is nothing but the complement. See, in the light of this explanation, maybe you could examine that principle of duality again. So what is duality? We have left the literals as it is and we did everything complemented, which means it is just like complement, but then we just even changed the see this, I will explain you. This is nothing but the complement, right? So F complement is nothing but this. Now if F is this, then what is duality of F? FD, let me say that is duality. Leave the literals as it is, which means A, B, C, D, so on, Z, they have to be left as it is, and the constants, they have to be changed, they have to be modified, which means in place of 0 you put 1, in place of 1 you put 0, and in place of dot you put plus, and in place of plus you put dot, right? So this is the meaning of duality. Now what is the relationship between the complementation and duality is simple. First, if you want to find the complement, or let us say from the function you found out the complement, you take the complement and again you complement the literals, then you are going to get the duality, right? Or, so I hope that you remember the principle of duality. Principle of duality is I told you in the first video, right? And now you can directly go from F to dual and dual to complement. How? First you find out the dual and then complement the literals. So what is the basic difference between complementation of expression and duality of expression? You see, if you have an expression F, what is the main difference between complementation and duality is complementation actually, if you take the complementation of the expression and if you again negate or complement all the variables, you are going to get dual, right? So both are almost same except that the literals in both of them will be in the opposite form. If a literal here is in true form, here it will be in complement true, like that. For example, let's see this example. See, let us say x prime plus y prime. If I want the complement of it, what does this De Morgan's law say is, take this expression and you convert every literal to its complement and then replace dot with plus, plus with dot. So what do I get? Then x for this x prime I get x, and for this y prime I get y, and for this plus I get a dot. Therefore this is nothing but complement, isn't it? Now what is duality? Duality is leave the variables as it is, just you change the operations and then the constants, right? So duality says that leave the operands as it is and you just change the remaining things, right? Operators, then I get this. So this is duality, right? And now you just check these two, they actually are the same expressions, only difference is if a variable is in true form here, that will be in complemented form. That is the difference. Got it? So that is how this De Morgan's law work. Now let's take an example and see how to simplify it, taking this De Morgan's law into consideration, right? Let's now simplify this. If you have to simplify this expression, maybe let's see how to simplify at least some parts of it first. So this is actually this expression's whole complement. Here you could apply De Morgan's law and you could simplify it. So if I write it, it will be x plus y followed by the complement of it. So what do I get the complement? I mean, if I apply the De Morgan's law, every variable has to be replaced with its complement, and then every operation has to be complement, I mean changed, plus has to be changed in dot. So you will get this. How did I get this? X is replaced with x prime, I mean x prime is replaced with x, y prime is replaced with y, z prime is replaced with z, and in place of dot I kept, in place of r I kept and in place of and I kept r, right? Plus x prime y prime plus x prime z prime, right? And now if you have to simplify it, for now we shall expand it. Later you can, you can even do one thing. Here in order to simplify these two, you could observe one thing. Directly you could always remember that if it is x plus y into x plus yz, it is directly x plus y. For now we shall derive it. And the other one is, maybe you could turn this into a dual, its dual, and then you could do it, right? If you turn it into its dual, what do you get? Xy plus xyz, isn't it? Xy plus x into y plus z. Either you can take it into dual and then simplify it, or without confusion, for now just see the multiplication. I mean just see the every 4 terms, which means x into x dot x is x itself, and x dot yz is xyz, and y dot x is, and this one is yz, plus x prime y prime plus x prime z prime. Got it? And now you could observe this. Here in these two I could pull out x as common. If I pull out x as common, what do I get? X into 1 plus yz, right? And now in these two, let's leave it as it is. I could pull out y as common, but then let's leave it as it is. Xy plus yz plus x prime y prime plus x prime z prime. See, I am following one method. You could follow any other method if it is easy for you. I am just following maybe the longest method. Now 1 plus this is x plus xy plus yz plus x prime y prime plus x prime z prime, right? Now what I will do is these two. If I again pull x out of x as common, these two will become x. The reason is, if I pull out x, you will get 1 plus y. Therefore this entire term can be replaced with x, right? Yeah. So this entire term could be replaced with x plus yz plus x prime y prime plus x prime z prime. Now let's combine these two. If I combine these two, what do you think we get? X, these two, right? So x plus x prime into x plus y prime. How did I get this? By distributing r over and what are the two remaining terms? Yz plus x prime z prime, right? Now what is this entire thing? This entire thing is 1. What is this entire thing? X plus y prime plus yz plus x prime z prime. Now we can combine these two. If I combine these two, what do I get? X plus z prime. I'm just simply deleting it. If I combine these two, I get x plus z prime, right? Then what is it? X plus z prime plus y prime plus yz. If I combine these two, then what do I get? X plus z prime plus, if I combine these two, I am going to get y prime plus z. Now if you combine these two, z prime plus z is 1. Therefore it is x plus y plus 1. So which is nothing but simply 1. So the entire expression turns out to be 1. So maybe I have taken the longest route possible. You could directly do it in a shortcut with practice, but I just wanted to show you the entire method. Okay. Now let's formally define what do we mean by canonical forms. There are two types of canonical forms. I'll define first one first and then the next one, and I'll show you with an example. Okay. So I'll read out. See, what you do is, from now on, from this part, we are done with basics. I mean, what is and, what is or, what is not, all that you know it. And from now on, I'm going to introduce you to some terminology, so that this terminology will be useful for you in solving the gate questions as well as in understanding the further topics. So you just keep taking the notes. Pause the video, take the notes. Pause the video, take the notes. Do like that. Okay. Now understand this. I'll just read it out and explain you each one. A product term which contains each of n variables as factors either in complemented or uncomplemented form is called min term, which means product term means what? Only a term formed using and. A product term in which each of n variables contains each of n variables as factors, which means that one should contain all the variables present. If the function is produced, consisting of 3 variables, then every min term should contain all the 3 terms, right? So this is the definition of a min term. So understand this. A product term which contains each of n variables as factors either in complemented or uncomplemented form is called min term. So if you are talking about a min term, if a function is made of 3 variables, all these variables should be present in the min term. For example, if the function is made of 3 variables a, b, c, then the min term should contain all these 3. So like this, a into b into c, this is the min term. Or a, b prime, c. Why? A variable can occur either in its complement or in its true form, right? So either as complemented or uncomplemented form, a variable can occur in any of the forms. Now this every term is called a min term. So anything which is made of 3 variables is min term, right? And if you have a variable like this, if you have a term like this a, b, but the input is consisting of, or the function is made of 3 variables, and you have a term which contains only 2 variables, then it should not be called as the min term, right? Now a min term gives the value 1 for exactly one combination of a variable. So you take any min term that will give only for one combination of the input, the value will be 1, not for all the other combinations. For example, if you say the min term is a, b, c, right? Only for one combination of the assignment of truth values for a, b, c, it will be 1. What is it? 1, 1, 1. Only if you assign 1, 1, 1 to a, b, c, then only you get the value to be 1. If you assign any other value other than this, the value will be 0. You can check it. If you assign 0, 1, 1, the value will be 0. Check anything. So 1, 0, 0, the value will be 0. Anything, right? Or you can take one more example. Let us say the min term is a, b prime, c. Only for one assignment of the input, it will be 1. Only for single combination it will be 1. For all the other combinations it will be 0. For example, this one will be 1 only if the input is only if the input is 1, 0, 0. Only if the input is 1, 0, 1, then only this output, it will give you a output as 1. For any other combination of the inputs, it will not generate the output as 1. So that is the property of the min term. So remember that min term should contain all the variables either in complemented or uncomplemented form. And second thing is, min term will always generate a value of 1 only for one combination, not for all the combinations, right? And only for one combination will generate 1 and all the other combinations will generate 0. The sum of all min terms of a function, which means if you now consider a function, right, the sum of all min terms, which means you take the min terms and you form the sum. Sum is nothing but ORing. The sum of all the min terms of f for which f assumes 1, which means wherever f is taking the value of 1, that is what they are talking about. The sum of all min terms of f for which f assumes 1 is called canonical sum of products. So you can take all these combinations and that is called canonical sum of products. Generally, sum of products means R of AND terms, that is called sum of product. And canonical sum of products means the R terms contain the AND terms, the min term, the AND terms are nothing but the min terms. I'll just tell you the difference. What is sum of products and what is canonical sum of products. It is also called as disjunctive normal form. Disjunctive means or means it is found with the ORing of various forms. That is why it is called disjunctive normal form. Now I'll just take this example and explain you what we mean by this. See this. First of all, there is a difference between sum of products and canonical form, canonical sum of products. For this one, if you take this one is the function is function is in terms of ABC. If I write A plus BC plus AC, something like this, then this is sum of products, isn't it? Because this is a product. What is the product? A into 1, and this is a product B into C, this is a product A into C, and in fact this is sum of products. Similarly, what is canonical sum of products is, if I write like this, ABC plus A prime BC, this is nothing but canonical sum of products. The reason is, every minterm is containing all the variables. Here every minterm need not contain all the variables, so keep it in mind. Sum of products means it need not contain all the variables. Canonical sum of products means it will contain all the variables. Got it? And now how to write the function using the minterms is, they are saying that, see this, you have to write a sum of all the minterms for which the function has taken the value 1. So for this function f, you can write it like this. So for this combination, the minterm for this combination is A prime B prime C. Why? Only for that combination, only for that minterm will take, for this combination 0 0 1, a value of 1. That is why I am writing it as C. Whenever the value is 0, you write it as complement. Therefore A prime, and whenever the value is 0, you write as complement B prime, and whenever the value is 1, you write directly A prime B prime C plus, now check this one also has to be written, right? So here it is complement, therefore A prime B C prime, A prime B C prime plus, now I am talking about this one, A B prime C prime, A B prime C prime plus, now I am talking about this one, A B C prime, A B C prime. Therefore the function is now written as, sum of minterms of all the minterms for which the function assumes 1, right? So what is the meaning of it is, if the input is given as 0 0 1, then among all these minterms only one minterm will give a true value, which means a value 1, and that minterm is already included here. Therefore if you assign this input, this particular input, to all these minterms, definitely you are going to get the output as 1. Why? Because exactly for this one, at least 1, you are going to get the output as 1. That is how these 4 terms are useful in representing the entire function, right? Similarly, if you give the input as 0 1 0, the second term will give the value of 1. That is why the function will assume the value of 1. Similarly, the third term and this one, right? And we need not include all these. Got it? So what happens if I include all this is, if I include anything, if I include A prime B prime C prime, what happens is, if I include A prime B prime C prime, then for the value of 0 0 0, that A prime B prime C prime will become 1, which will show that f is having a value of 1 for this combination, which is wrong. Therefore only for the combination for which f is showing 1, you include the minterms, so that whenever that particular input is given to the f, only that particular minterm will show 1, and all of them will show, all the remaining will show 0. Anyway the function will show 1. Got it? So this is how we can define it. In shortcut, how we could write it is, see this, if you convert this into decimal numbers, this is nothing but 0 1 2 3 4 5 6 7, right? Now how can you write it? Now the sum of product terms is nothing but, sum is represented with sigma, and what are the minterms? What are the minterms for which we got this? One is 1, and what is the other one? The other one is 2, and what is the other one? 4, and the other one is 6. So this is the compact representation of the same thing. Either you write like this, which is nothing but sum of all these minterms, or you write like this. Both are going to represent the function. Got it? Now there is one more normal form, this one more canonical form, that is nothing but the, it is, if it is conjunct to disjunct to normal form, that is conjunct to normal form. We shall see about it. There I am going to write the same kind of definitions with slight changes. Okay. Now we shall see with example how to represent a function in some other form. Then we shall see about how to use these functions in general. Okay. One other canonical form is product of sums, canonical product of sums. Previously we have seen sum of products. What is sum of products? It is nothing but we have product terms to which we have applied the sum. Now what is product of sums? We have sums to which I apply product. So let me take an example instead of using my hands. See, a sum term which contains each of n variables as factors either in complemented or uncomplemented form is called max term. Here we use the term max term to represent the sum. Okay, min term means to represent the product. If the product contains all the variables either in complemented or uncomplemented form, that is called min term. Max term means it should contain all the variables which are present in the function in either complemented or uncomplemented form, right? If that is the case, then we can call it max term, right? For example, if this is the function ABC, it is a function ABC, a max term will be A plus B prime plus C. The reason is it is containing all the variables in either complemented form or uncomplemented form. I have a doubt. Can I have the same variable two times in complemented and uncomplemented form? You think about it. If I write one more time plus A prime, then what happens? A plus A prime becomes 1 and that 1 plus everything becomes 1. Therefore, we cannot write it. Okay. So, every variable is going to occur exactly once, not two times. At least once, at most once, which means exactly once. Either in min term or max term, remember, every variable will occur only once, right? And now this is called a max term. So if you have any term like this, A plus C, this is not a max term because it is simply a sum term. It can be called as sum term, but then it is not a max term. So max term means everything should be present. If you have three variables, all the three variables should be present in some form. They should occur, right? A sum term which contains each of n variables as it is called max term. So this is a max term formula. And next one is a max term gives a value of 0 for exactly one combination of the variables. Now if you take this term, this particular term, for exactly one combination of the variables it will give 0. Previously min term exactly for one combination of values it is giving 1. But here exactly for one combination of values it will give 0. So what is the combination of the values for which it will give 0? 0, 1, 0. If you apply this combination to this, it is 0 plus 0 plus 0. Only for this combination it is going to give you 0. You give any other combination it will not give 0, it will give 1. For example, if you apply 1, 1, 1, definitely it is 1. You give any other combination it is going to be 1. Got it? So that is the specialty of this max term. Now we are going to define the function. We are going to write the function in terms of max terms. See, min terms is nothing but saying when a function is going to be 1. Max terms is nothing but saying when a function is going to be 0. So either you say when a function is going to be 1, that is nothing but defining the function, and or you say when a function is going to be 0, that is also a definition of function, because we now know where to put zeros for the function or where to put ones for the function. Either you define zeros or you define ones, automatically the remaining is going to be ones or zeros, isn't it? See, in min terms what happened in canonical collection of min terms, what happened? We are going to say what are the values of the inputs for which the function is going to be ones. That is enough. You need not talk about all other combinations, because all other combinations are obviously going to be zeros, right? Similarly here we are going to say what are all the combination of values for which the function is going to be 0. That is enough. Why? Because all others are going to be 1, right? Either you can define the function in terms of where the value is going to be 1 or where the value is going to be 0. Both are same. So one uses min terms and other uses max terms. Now look at this. The product of all max terms of f for which f assumes 0, which means wherever the function is taking 0, you take the product of all those max terms, right? Then that is called conjunct to normal form. So I'll tell you this. For this one, where is the function taking 0? Here and here, here and here. For these 4 places the function is going to take 0. Then what is that you are supposed to do? Only for these 4 cases you find out the max terms. What is max term? you give the combination of the variables in such a way that for that variable, for that assignment, for that particular assignment, the value should be 0, right? And now you put all of them in product. So see this. Now what does it mean is, for this one I have to form the max term. What is max term? What is the term which contains or which produces 0 when I assign 0, 0, 0? If I assign 0, 0, 0, and if a plus b plus c, some kind of term, should produce 0, then the term is a plus b plus c, isn't it? Only the term a plus b plus c is going to produce a 0 for the input combination 0, 0, 0. Or if you didn't understand this, directly the method is, when you are writing the max term, whenever there is 0, you write the true form. Whenever there is 1, you write the complemented form. That is how you could remember, right? Now, for this one, what is the combination of a, b and c, or what? How should you write the variables a, b and c for the value to be 0? A, b prime, c prime. If it has to be 0, 1, 1, if for the 0, 1, 1 the value has to be 0, you have to write it as a plus b prime plus c prime, right? And what about this one? You have to write it as a plus b prime plus c, isn't it? Why? Only for that. Oh, this one, a prime plus b plus c prime, a prime plus b plus c prime. For that combination, you know, this minterm is going to be 0. Now what is the minterm for this? A prime plus b prime plus c prime. Now you product all of this. Now it is going to represent the function f. How is it going to represent function f is, we are going to say where the function f is going to be 0. Now it is not that where the function f is 1, it is that we are defining the function f in terms of where is it going to be 0. Now how does it work is, you give any input for which the, this one is 0, for which the function is 0, then if you give any input, for example 0, 0, 0, to all of them, at least one of them is going to be 0, which one? The first one. And when one of them is going to be 0, then obviously because of the product, everything is going to be 0. That is how we have represented the value of f whenever it is going to be 0. So for any combination which produces a value 0 for the function, will definitely produce a value 0 for one of the max terms, exactly for 1. And now that 0 will produce the entire 0. Got it? So we can define the function in two ways, either canonical sum of products or canonical product of sums. It is called as product of sums. The reason is we are using the product of sums. So what is the compact representation of this one is, previously like you have used sigma to represent the sum, now you can use pi to represent the product, right? What are the values you have taken? For 0, 3, 5, 7. For all these values, the value is going to be 0. That is how you represent the canonical product of sums. So you now understood how to use both the canonical forms. Now we shall see, given any expression, how to convert it into the canonical forms. Okay. For a given switching function, let us say there is a switching function like this. It is a function of two variables, 0, 0, 0, 1, 1, 0, 1, 1, and if the function is like this, right? So if the function is containing these two variables, and if it is the function, you can even generally extend it. The way to represent this function, there can be many expressions which are representing the same function. Just like there are many automatas which represent the same language, here also many expressions represent the same function. But then when you try to convert that expression into either canonical SOP or POS form, then whatever you get is unique. So what I mean to say is, even though there are many expressions representing the same function, when you try to convert each of them, every expression, into POS or canonical form, all of them will produce the same thing, right? Just like that finite automata. As you know, there are many finite automatas for a given language, but when you try to minimize the finite automatas, you are going to get the same minimal finite automata, right? So similarly, the same thing, this also holds in the same way, right? So given a function, there will always be a unique canonical SOP or POS form, right? In finite automata, we actually minimized it to prove that two finite automatas are same, but here we are taking every expression and we are trying to maximize it, right? Actually canonical forms are maximum forms, right? So we are trying to put everything and then show it. Fine. Next one is two switching functions f1 and f2 are same or said to be logically equivalent if and only if the functions have the same value for each and every combination. What does it mean? Two functions, let us say f1 and f2, they are said to be logically equivalent whenever for every combination, which means this is a combination, this is a combination, this is a combination, this is a combination. For each and every combination, if both the values produced by the functions are same, which means if for this combination the value of f1 is 0, f2 has to be 0. If for this combination the value of this is 0, this is 0, 1, 1, then only we can say that two functions are equivalent. Here instead of using the word equal, we have equivalent. Okay. Now two functions are equivalent if their canonical POS or SOS are identical, which means the same thing, right? So if they have the same table, same values assigned here, obviously the canonical POS or SOS form or POS or SOP form are obviously equal, right? So all these talk about the functions. How does the function look like? Now let's examine, given any number of variables and any number of functions, let us see how many functions will be possible given some variables. Okay, let's see what is the relationship between number of variables and type of the functions and number of functions. Fine. Let's count the number of switching functions possible. So before counting the number of switching functions, let's talk about the number of functions in general. Assume that we have a set A in which the number of elements is n, and we have a set B in which the number of elements is m. Okay, then how many functions are possible from set A to set B? See, here every element in A has m possibilities, which means every element A can be mapped onto any one of these m possibilities, but only one at a time, right? Therefore the first element of A has m possibilities, and the second element of A, again it will have m possibilities, right? So every element of A has m possibilities. The first element has m, the second element has m, the third element has m possibilities, so on. The nth element of A also has m possibilities. Therefore how many functions are possible from A to B? The set A to set B is m into so on this much. Therefore it is m power n. These many functions are possible. Just remember it. Now we shall derive how many functions are possible if I have let us say I have a function, switching function, if I have n variables, n Boolean variables. Boolean variables means they can take only two values. N Boolean variables are there, then how many Boolean functions are possible? How many Boolean functions are possible? Okay, now observe this. It is a kind of combinatorics question. See, if I have n Boolean variables, what does it mean? Every variable can take only two values, either 0 or 1. Then how many Boolean functions? Boolean functions means they are saying that even a function will also take only two values, 0 or 1, right? So if I have n Boolean variables, which means 1, 2, 3, 4, so on, n Boolean variables, then I am going to construct the table first. Then how many rows does this table have? How many rows will it have? Depending on the number of variables and the number of values. Now each variable has two values possible, right? Therefore 2 into 2 into 2 into so on n times. Therefore the total number of rows that could be present in this table is 2 power n, right? These many rows are present. And now think about it. This is a function, some function, right? So how many functions are possible? So every row can be given a value, every row can take two values, which means, okay, how to explain this is, now the total number of elements in one set is 2 power n, and these many elements have to be mapped to other set which contains only 2 values, which means this. Now one set is containing total number of elements of 2 power n, then this set has to be matched to other set where only 2 elements are present, which is 0 and 1. Now compare this. If I have n elements here and m elements here, what is the total number of functions? M power n. Similarly here, if I have 2 power n elements here and 2 elements here, then how many functions are possible? 2 power n, right? So if I have n Boolean variables, then the number of Boolean functions possible is this much. Let's now just change it a small bit. Let us assume that instead of n Boolean variables, yes, I have n variables only, n Boolean variables, let us say n ternary variables, and then how many Boolean functions are possible. So what does it mean? It means that the value of n can take, every variable can take every n ternary variables, which means every variable can take now 3 values, 0, 1, 2, right? So if every variable can take 3 values, then how many variables are there? N variables, and everyone is going to have 3 chances. Therefore, how many total elements will be present in this question? In this question, the total number of elements that will be present as input is 3 power n, right? Therefore, one set is containing 3 power n elements, and they are saying that the function is Boolean function. Boolean function means function takes only 2 values. Therefore, here it is 2 values. Then, how many functions are present? Totally 2 power 3 power n, isn't it? 2 power 3 power n. So now let me tell you one more, generic question. Assume that I have n k-ary functions, k-ary variables. So what does it mean? The number of variables are n, but each variable can take k values, right? And then how many m-ary functions? M-ary functions means the function can take m values. If I have n variables, each can take k values, then, and a function can take m values, then how many functions are possible here, right? Then how many m-ary functions are possible? Then how can you solve it is, first let's construct the table. So in order to construct the table, putting up all the elements inputs here, I have 1, 2, 3, so on, n elements, and each element is having a k possibilities. Therefore, totally how many rows do I get? I get a total of k power n rows. These many rows are there. Therefore, one set is containing k power n elements, and the other set, the function values are, it is a m-ary function, which means the function can take m values. Therefore, other set is containing m values. Then how many functions are possible from this set to this set? It is m power k power n. So what does it mean? The number of variables will be here, and the number of type of variables, right? K-ary type of variables will be here, and the type of functions will be here if it is m-ary function, right? So in case if it is Boolean, it is 2, right? In case if it is ternary variable, it is 3, Boolean means 2, right? So that depends on what type of variable and what type of function we are using. Got it? So this is how we can find out the total number of functions possible. So just for the sake of example, if I have just two variables which are both are Boolean, then how many and the functions are Boolean functions, then how many Boolean functions are possible? Which means like this. Assume that I have just two variables. A and B, right? If I have two variables, both are Boolean, and then the function is Boolean, then how many functions are totally possible? With two variables which are Boolean, I have 2 power 2 rows, isn't it? Therefore each row can take either, each value can take 2 combinations, therefore 2 power 2 power 2. Even if you substitute in this formula, you are going to get 2 power 2 power 2. Then how much is that? 2 power 4, which is nothing but 16 functions. 16 functions are possible with just 2 variables, right? So what are they? If you would like to see that, 0 0 0 1 1 0 1 1, right? So one function is, let us say f1 is 0 0 0 0, null function. f2 is 0 0 0 1. What is this? It is AND, right? So a dot b, so this represents, f2 represents AND. f3 is 0 0 1 0. So what is this function? This is a prime plus b, that is nothing but a implies b. It is a implies b, f3, right? f4 is 0 0 1 1, right? So what is this function? f4 is simply a. So whatever is the value of a, f4 got it, right? And next one is f5. f5 is 0 1 0 0. It is nothing but a prime b. Oh, already we got a prime b. I think we got a b prime. It is a prime b. So previously it was a implies b, and it is okay. You can just check it. Let's not give any names. I think it is confusing. I didn't say it right. So leave about the names. We shall see the names later. Now f6 is how much? 0 1 0 1. f7 is 0 1 1 0. f8 is 0 1 1 1, right? Similarly, I have written 8 functions. In all these 8 functions, the first element is 0. You can reproduce one more 8 functions, 1 2 3 4 5 6 7 8. In all of that, you can put this first one as 1, and the remaining you can repeat it. Therefore we can get 16 distinct functions with just 2 variables, right? So now the question is like this. Now what happens is, sometimes we have these many 16 distinct functions which are unique, right? But then if we have to write some expression, many of the expressions will be same. If you convert them to Boolean form, if you convert them to canonical POS or SOP form, many of them will be same. Now we have to identify how many expressions are mapping onto one function. Are you understanding this? We have 16 unique Boolean functions, right? And now many expressions which are mapping expressions to these functions. Many expressions will lead to the same function. Therefore, one kind of question possible is, given 2 expressions, are they equivalent? And moreover, what is the function they are equivalent to in POS or SOP form? Then we can use this. Anyway, we shall solve many questions on this, then you will understand what is the significance of writing all this. So with just 2 variables, we are able to get 16 functions. What about 3 variables? How many functions do we get? 2 power 2 power 3. So what is that? 2 power 8. Just look at the growth in which the number of functions are growing. 2 power 8, the rate at which they are growing is very large, isn't it? It is not even just exponential, it is super exponential. Exponential is 2 power n, and the order in which they are growing is 2 power 2 power n. As the number of inputs increase, the number of functions are growing exponentially, super exponential, right? Okay. How many Boolean functions are possible with 3 variables such that there are exactly 3 minterms? It means that the functions, if you write the functions, then okay, first of all, how many minterms will be possible totally? I'm not minterms. How many inputs are possible? The rows. With 3 variables, the number of rows that will be possible is 8. Why? Every variable can take 2 possibilities. Therefore, the input combinations we have is 8, and they are saying that exactly 3 minterms should be there, which means out of these 8 combinations, only 3 combinations have to be assigned 1, and all the other combinations have to be assigned 0, right? So they are saying, how many ways can you assign 3 ones to 8 elements? If you didn't understand it, so what they are trying to say is, let us say 3 variables is A, B, C, right? And now if you look at the table, how many combinations will be there for the inputs? Since there are 3 variables, there are supposed to be 2 power 3, because all the 3 variables are Boolean variables. So assume that it is Boolean variables. Since nothing is given, assume that it is Boolean variables, right? Otherwise they will give you something. Now 3 variables are given. Therefore if you look at all of them, it will look like this: 0 0 0. Let me represent with 0, likewise 1, likewise 2, likewise 3, 4, 5, 6, 7, right? So if you have all these rows, then how many, they are saying that exactly 3 minterms should be there, which means only 3 input combinations should be given 1, and all of them have to be given 0. So how many ways you can give? There are many ways, right? So 1 1 1 0 0 0 0 0, or 1 0 1 1 and then 0 0 0 0. So there are many ways you could write. So I could write it as this: if I have 8 combinations, out of which I am going to choose 3 combinations and I am going to assign them this particular value 1, and for the remaining you need not talk about them, because if you have assigned 1 for 3 combinations, obviously the others got zeros. Therefore the number of combinations or the number of functions you have is 8C2, right? And now similarly you can extend this question to any longer. For example, let us say they are saying that how many functions are possible with at most 3 minterms. Let us say with at most 3 minterms. So what is the meaning of it? So we have to just go till the point where there is, where you assign at most 3. So the number of minterms could be 0, or the number of minterms could be 1, the number of minterms could be 2, 3, that's it, right? And for this also just assume that 3 variables, 3 Boolean variables are given. 3 Boolean variables are given, and they are asking you about how many functions should be there, how many functions are possible with at most 3 minterms. So how can you write it? Watch this one. 8C0, which means among all the 8 inputs, I will not give any minterms at all. Then 0 plus 8C1, the number of functions which have exactly 1 minterm, plus 8C2. It is nothing but number of functions which have exactly 2 minterms, 8C3, number of minterms which have exactly 3 minterms. Therefore what we wanted is at most 3 minterms, therefore I got at most 3 minterms, and beyond that I don't want to assign it, right? And similarly at least 3 minterms means 8C3 plus 8C4, so you could extend it like this. Got it? So what I mean to say is, assume that there are k variables, then how many rows are possible? 2 power k, right? Then depending on how many minterms they wanted to assign, you can get those many functions. Let us say they wanted to get m minterm functions, which means the function should contain exactly m ones to these combinations. Among all these combinations, you can choose any m combinations and assign them 1. That is nothing but functions containing exactly m minterms. Then how can you write it? 2ck c m. This is normal formula. I mean, you need not by heart it, I am just generalizing it. So don't by heart it, you could derive it anyway, right? So in case if it is not a binary variable, then what happens? Depending on the type of the variable, this 2 changes. If it is a ternary variable, how many rows do you get? This you are going to change. Got it? And then minterms, if you have to define minterms and max terms, generally you have to talk about binary variables and then binary functions, which means variables can take 2 values and functions can take 2 values. Okay, so this is how you can write about it. One interesting point about it is there is something called as neutral functions. Neutral functions means, okay, we shall talk about it. Let's see this. How many neutral functions how many neutral functions are possible with some certain Boolean variables? Let us say the given input is 2 Boolean variables. With 2 Boolean variables, how many neutral functions are possible? So a neutral function is a function in which number of minterms is equal to number of maxterms, which means the number of ones should be equal to number of zeros among all the inputs. For example, if I have two variables a and b, they can take 0 0, 0 1, 1 0, 1 1. Then what are all the functions? What are all the neutral functions I have? So 0 0, 1 1, right? 1 1, 0 0, or 1 0, 1 0, or 1 0 1, 0 1, right? Or 1 0 0 1, or 0 1 1 0. Check it. How many did you get? 1 2 3 4 5 6. Yeah, 6. So these are all the neutral functions possible. I mean, there is only one thing about neutral functions is number of minterms should be equal to number of maxterms. No other special property. Maybe if you would like to see what they are, see, this function is nothing but whatever is in A, you are seeing it here. Therefore, this is function is nothing but A. Alright. And what about this function? This function is A complement. And what about this function? This function is B complement. This one is B. And this one is X NOR, I guess. So what is it? It is 1 1 is 1, 0 0 is 1. Yes, X NOR. And this one is exclusive OR, right? So exclusive OR and exclusive OR. So these are the neutral functions we have. So neutral function is nothing but, see, these names doesn't have any significance. I'm just writing it just to show you how they could be written. That's it. They don't have any significance compared to the in coming to the neutral functions. Only one thing is, in neutral functions, the number of minterms and number of maxterms should be equal. Then how many minterms do you think are possible? So here I have completely four combinations, 4 input combinations, and out of these 4 input combinations I can choose any 2 input combinations and give them 1. Obviously the remaining 2 combinations will get zeros, right? So in general, if I have n variables, then how many inputs will be there? The number of inputs possible will be 2 power n, right? And among all the inputs, you assign to half of them the value 1 and the remaining half the value 0. So then what happens? Among this 2 power n, you assign half of them, 2 power n by 2, a value of 1, and automatically rest will get a value of 0. Then how can you write it? 2 power n c 2 power n minus 1, right? This is the number of neutral functions that are possible with n Boolean variables. Got it? Watch this. Find the Boolean functions that the following this one represents. So there are various ways we could represent the Boolean functions. One way to represent it is using Venn diagram. So I'll just tell you how the Venn diagram works, and then we shall solve that question. First, let's see the Venn diagram, right? Assume that we have 3 Boolean variables. Then we can write the Boolean functions like this. So generally it is not scalable, in the sense if you have more than 3 Boolean variables, if you have 4, 5, this method really is restricting the scale. I mean, it is difficult to write them. So we generally don't use them, but then I have seen some questions related to this, therefore I am doing it. But at practice we really don't use it. It is just to understand the concept that it could be used, but we are not using it really at practice. Theoretically, to some extent it is used. So see this. Now if I have 3 variables, I could represent them in the Venn diagram like this. Say this is A, B and C, right? Then let's see what each area specifies. So each area, which means if this is the total Venn diagram, if outside everything means here at this point nothing is present, no A, no B, no C. Therefore what can you say about it? A prime, B prime, C prime, right? And what about this one? A is present but B and C are not present. So remember one thing, in order to represent the complementation, sometimes I use like this A prime or sometimes I use like this. Both are same, don't get confused. Okay. Now coming to this point, if you look at it, A is present but B and C are not present in this one, right? Therefore you can represent it as A, B prime, C prime. And coming to this area, B is present but A and B in this one, B is present but A and C are not present. Therefore A prime, B is present, C is not present, C prime. Coming to this area, C is present but A and B are not present. Therefore how can you represent A prime, B prime, C, right? And looking at these areas, this one here, only this one, this part, which means this one, right? If you look at this one, only B and C are present but A is not present. Therefore how can you represent it? A prime, B, C. And if you watch this, only A and B are present but C is not present. Therefore A and B are present, C is not present. If you watch this one, only A and C are present but B is not present. Therefore only A and C are present, B is not present, isn't it? Now if you look at this, everything is present, so this is nothing but A, B, C. Now see the number of minterms we got here. The number of minterms we get here is, watch it, 1, 2, 3, 4, 5, 6, 7, 8. Therefore, if I have 3 variables, the number of input combinations is 8. The number of different minterms we have, I should not say, no, yes, the number of minterms we have is 2 power 3, which means 8. So 8 possibilities are there. Fine. Now we want to represent a function. Function is nothing but the collection of minterms. I mean, one way of representing the function is you collect the minterms for which the function gives you 1, isn't it? Therefore one way of representing a function is you shade in the areas where the function takes a value 1 and you leave the areas where the function does not take any value. For example, in this one, check this, he is shading the area in which the function is taking A. These 2 areas are shaded. Now they are asking what is the term that this one is representing. If you watch this one, this entire A is included in the function, therefore A should be included plus. So why is completely A is included and why you cannot take, see, you could have even taken it like this, right? A, B prime, C prime, and what about this one? This is A, B, C prime, and what about this part? C. This contains in itself 3 parts, I think 4 parts. See, this part represents A, B prime, C prime, and this part represents A, C, A, B prime, C, and this part, middle part represents A, B, C, and this part represents A. This part, I am talking about only this part, I mean inside this, right? A is present, B is present, C is not present, right? Now if you combine these two, what I get is AB. And if I combine these two, what I get is AB prime. You know how to combine them. I am just pulling out AB prime as common. Then what is remaining? C and C prime. And if I pull out AB as common, what is remaining? C and C prime. Therefore here it is AB and it is AB prime. Now if I combine these two, then what I get is A only, right? Therefore representing it using 4 terms is as good as representing using 1 term, A. So later we shall see various ways to minimize it. Here I minimized it using the formula that I already know it, right? So what is that? I am pulling out AB and then I know that C plus C prime is 1. Using that formula I minimized it. Later we shall see various methods. But then the advantage of Venn diagram is it is clearly showing you that all the four put together will make up A. Therefore this entire part could be represented by just A. And what is remaining? If you see it, only this part is remaining, right? Only this part is remaining. What is this part? In which B and C are present but A is not present, which is nothing but A prime BC. So the remaining part is nothing but A prime BC, right? So now it could be written as A plus A prime BC. So what is the answer? C. This is not the answer, because they are saying that A plus A prime B prime C, which means they are including C, this one. They are saying that it is A plus this, it is wrong, so this one, got it? So if you could directly minimize it, it is fine, or if you could guess it from this, it is fine, or you could use the formulas. Later we shall see various methods using which we could minimize it, right? As of now, my intention is not in minimizing. I am just trying to explain you how the functions are represented, got it? So now we have already seen that there are eight areas in this Venn diagram, right? And every function is nothing but some particular area or some combinations of areas being shaded. Then how many functions are possible? If we have n variables, how many functions are possible? We have already seen it. So what is it? 2 power n. Why? 2 power n rows are possible, and every row can take 2 values. Therefore 2 power n functions are possible. So there must be 2 power n ways in which we could shade this Venn diagram. So if the question is, how many ways can you shade this Venn diagram? How many? These many. 2 power n ways we could shade this, because each one is representing a function and there are these many unique functions. Therefore there must be these many shadings possible, right? So just for the sake of example, explain me this. What is the function that is represented by? For example, I want to represent the function like this. I am going to shade this completely, the outside part. Tell me the function represented by this kind of shading. I am shading the entire outside part. It is completely shaded. Outside part is completely shaded, and now I'll shade the insides, only this part, and I'll shade this part, and I'll shade this part, and I'll shade this inside part, and I'll leave out only this one and this one, right? Then what is the function represented by this kind of shading is, you can see it. So directly you could say the outside part is shaded, therefore the function can be represented as A prime B prime C prime, plus this part is shaded, therefore A prime B prime C, plus this part is shaded, therefore A B C, plus this part is shaded, A prime B C prime, plus this part is shaded, A B prime C prime. So we got 5 minterms, only 3 are remaining. I am not worried about minimizing. So in case if you minimize, you might get a minimized function, or I don't know, we can see it later. But here what I'm interested is, what is this one representing? Sometimes instead of giving such a diagram, the meaningful one, they might give you some meaningless diagrams also, like this. So in case if they give you like this, what they want to test is whether you really understood this concept or not. So in case they are saying that a variable A is there and inside that variable B and C are present, it is completely meaningless, but still let's see what it really means. And now they are shading this. So what does it mean? This shading is equal to A is present, B is present, as well as C is present, an intersection of all these three, right? So then what is the function represented by this? The function represented is A, B, C, right? Or they could give you some other diagram like this. This could be A, this could be B, and this could be C. If they shade these two parts, then what is the function represented by this? Even though they are not capable of generating all possible functions, the reason is they are not drawn in such a way that all possible functions can be derived. If they are drawn in this way, all possible functions can be derived, 2 power n. But if you draw it in this way, some of the functions will never be possible, right? Because always whenever A is present, B is present, or C is present, A is always present, which is nothing but every term will contain A, right? And what about the terms which does not contain A prime, which does not contain A, which means what about the terms, minterms which contains A prime? You cannot get them there, right? Now what about this? The function represented by this is A, B, C prime, plus this one is A prime B C. This is the combination, right? So this one represents this and this one is representing this. But then here if you see it, there is no term ABC. There is no intersection between all these three. So their intention is not representing all the functions, they just wanted to test whether you understood this concept or not. So this is how you can represent using Venn diagrams the functions. Okay. What's this one? This is called contact representation. Venn diagram representation is one of it. If any function, any Boolean function can be represented using Venn diagram or using contact representation. Contact representation means like this. I'll just explain you what it is. Every Boolean function can be represented with the help of serial and parallel contacts. So this is a contact, right? So serial contact means these two, they are in serial, right? Parallel contact means these, like this. So parallel means, you know, I mean, in electric circuits, we are lucky that, you know, you didn't take electrical. Otherwise, I'll just tell you why computer science is so easy, or why you are lucky not choosing electrical. I still remember that I had a subject called as EDC, Electronic Devices and Circuits, I guess. I don't remember the name of the subject also, and I think you too don't remember it. But then what I mean to say is that subject is so stupid. I mean, I should not be saying that, but the electrical subjects are so stupid that you will not really enjoy them. The logic behind them is too complex to enjoy. Yes, you could enjoy it, but for that you have to dwell into the subject a lot. But computer science is so logical that, you know, the CS, you could call it as common sense rather than computer science. That is what I feel. You know what? I still remember one question. Whenever I see such things, I just remember one question that I have answered in my EDC. You know, there is something called as capacitor, right? This is a capacitor, and in the question there is a question where AC passes through the capacitor, but DC will never passes through the capacitor. How I answered it is, see, AC means alternating current, therefore it passes through the capacitor, right? And DC means direct current, which means it looks like a single line, therefore it is not supposed to pass, it will not allow it. This is what I have given in the logic. In my BTech exam, I still remember that this is what I have given it, and I don't know how I got 97 marks in that subject out of 100, and I don't know where I missed out 3. Maybe I'm not sure whether this question has got it, or whether the evaluator, you know, got it or no. Every question I did it like this only. I made up my own explanations and I have written it, and I have written it so neatly and in such a way that I think he might have got convinced that this is the right explanation. That is how I got 97. BTech examinations are really stupid. Okay, fine. So sorry for deviating. Now let's see this. What I mean to say is, every function can be represented using contacts. These are called contacts. And when I write the contacts like this, they are called serial contacts. And when I write the contacts like this, they are called parallel contacts. Now watch it. Serial contacts are performed or performing AND operation. So if the current has to flow from here through this circuit, then definitely there should be at least one path, right? Either the above path or the below path. If the above path has to be formed, then A has to be closed. If the below path has to be formed, then both B and C have to be closed at once. Therefore, how can you know that current is passing through this circuit is, one is either A should be closed or both B and C should be closed. That is how I am writing it. So this circuit is so simple that you are able to write it directly, but there will be some complex circuits for which you might have to follow a procedure, an algorithm. I'll just tell you what the algorithm is in the next few minutes. Now you just answer this and then we can move on. This is not a kind of contact, it is a kind of, you know, logical question. AB, which of the following does this following circuit represent? Which means, what is this is representing? That is what they are asking. So if the current has to pass through this, either both A and B have to touch the on, or either both A and B have to touch the off. So touching the on is nothing but using the variable in its true form. Touching the off is nothing but using the variable in its complemented form, right? So if I have to touch, both A and B have to touch the on form, it is nothing but writing it as AB. If both of them have to touch the off form, it is nothing but writing it as A prime B prime. Therefore, the function represented by this circuit is AB plus A prime B prime. Got it? So this is how we could represent it. So let's see if a complex this contact circuit is given, then contact representation, how to convert it to the Boolean function. So let's see that. Identify the Boolean expression given by the following circuit. So this is a circuit given, and now we have to identify the Boolean expression. This is a contact representation. So whenever such a circuit is given, you just follow the method which I am going to say. Now find the valid forward path. Forward path means we should start from input and go to the output. That is a forward path. Find the valid forward path, and then after finding all the valid forward paths, you perform the ORing. ORing means you just you put a plus. Find the forward path and then perform the ORing. Now there are two things you should be knowing here. One is I am saying that valid forward path, which means there could be invalid forward paths as well, right? And second thing is I am saying that there is something called as forward path. What is the forward path first? See this, forward path is any path starting from input and ending at output without forming a cycle. So anything that starts from here and ends at here without forming any cycle in the middle is called a forward path. And validity means no path should contain a variable in both true and its complement form. So if you have a, then you should not have a prime. Got it? So that is what the validity means. So just observe this. Identify the Boolean path. How to identify the Boolean path is first you find out the forward paths and then see what are the valid forward paths in that. I'll just take this example and explain you. So how many ways can you reach from input to output here? How many ways can you reach from input to output here? See, so one way is A, B, B, and then this one, right? Then how can I write it? A, B prime, C prime. This is a forward path, right? Or let's see other paths also. A, B, C. Which means I would have taken this path and I would have gone there, right? And what is the other path? I would have taken A, B, A, B, A, or I would have taken A. I think I have explored everything starting with this B. If anything is remaining, you please do it. I feel that I have explored everything here, right? So let me explore this one. A, B, C, right? A, B, C, I can go there. Therefore I get A, B, C, and now A, B, and again I can come down and again go there. A, B, A, B, A, or A, yes, A, B is over. Now A, C, see this, A, C, A, C prime, C, A, C prime, C. This is what I call as invalid. The reason is it is containing both C and C prime. So what is C concatenated with C prime? 0. So what is the relevance of C is concatenated with C dot C ANDed with C prime in this circuit is when you are saying that one is saying that C is on, other is saying that C is off. So simultaneously the same switch, even though they are located at different places, it means that whenever at the input, when you switch on C, both of them will switch on or both of them will switch off, which means even though I am writing the C prime and C here, you could think of it like this. There is a common switch somewhere and this is what you are operating. Depending on what this value is, all of them will be set at the same time. So if the value of C is 0, this will be 1, this will be 0, and this will be 1, like that. So depending on the value of C, C prime is also decided. Therefore just keep in mind that these two are not independent, both are dependent on each other, both are not mutually exclusive. So the value of the other one depends on what the other one is. Therefore a switch cannot be simultaneously on and off. It is saying that the switch has to be off as well as on. It is not possible, right? Therefore it is invalid. That is what I say by what I mean by valid and invalid. And now one path is A, C prime, C, which is found to be invalid. Other path is A, C prime, A, C prime, A. Now you could simply simplify it. So what is this? A. This you can all simplify it, right? And then you have seen that this particular one ABC and ABC is repeating. Therefore you can remove one ABC, right? and again it is AB and it is AB, so these two are repeating, therefore yeah, both are AB only, right? Therefore you could remove this, right? So it is AB, ABC, A prime. So you can just, my intention is not in simplifying, so you could simplify later. It could be further simplified a lot. The reason is it is again AB and it is ABC, therefore AB plus ABC will be AB, so this one will vanish, right? And it is A prime, A, B prime, C, it is AB, and again A C prime. So you could try to even minimize it, or you can leave it there. My intention is not just my intention is just to explain how this one can be represented or converted to a function. Okay, fine. So one of the questions possible is they'll give you some expressions and they'll give you the equation. It is not rather an expression. They are equations. Which are the following simultaneous Boolean equations? We should call them, instead of expressions, equations. What are the values of w, x, y, z? Which means how to solve it is very simple. Just take each one and you substitute the value there. So it is x, w, x, y, z. So the values are given. The input is w, x, y, z. So these four values are given. If the input is x, y, z like this, so you just take each one and you substitute there, and you see that it is, the equations are verifying with that, agreeing. If it is not true, then we are going to cross it off. If they are verifying, then we are going to put it there. Now just watch it. So w, x, y, z. So if I put this value there, x plus y plus z. So what is x plus y plus z? Yes, 1. It is fine. For this one it is verifying. Now let's check this one. X into y is 0 and w prime is 1 into z prime is again 0. It is also verifying. Then what about this one? X into w prime is 0 and y into this is 0. So for the last one it is failing. Therefore it cannot be the answer. Now what about next one? X, y, w, x, y, z. So if you put y, x plus y plus z, what do you get? It is 1. First one it is verifying. Second one, x it is verifying, x into y it is 1. Sorry, x into y is 0 and y prime is 0 into z prime is 0. Therefore it is verifying, is it? X into y is 0 and w prime is 0, z prime is 0. Oh, it's verifying. Now the last one is x into w prime. X into w prime is 0 and y into z prime is 0. So for the last one it is not verifying. Okay, and next one, let's see if this one satisfies this or not. Now x, y, z. X, y, z, it is 1, satisfying. And what about this one? X, y. X, y is 0 and w prime is 1 and z prime is 0. For second one also it is satisfying. And the last one is x into w prime. X into w prime is 1. Yes, it is satisfying. Therefore this is for C. All the three equations are satisfied. Therefore what can you say? That C is the answer. For such a question it is a very simple question. It is just to check out whether it is satisfying or not. Nothing much. Fine. F of a comma b is a prime b. Then find all this. So it is a nested function. So whenever nested function is given, it is always better that you implement the innermost function first and then implement the next level of function. So what is innermost function? This one, right? So first we implement this and then we shall implement the other functions, right? So f of a comma b is a prime plus b. Then let me find out what is f of x plus y comma y. It is very important that you understand this, because going ahead we are going to do a lot of questions on this nested functions. Now what is f of this is, see, if this would have been a and this would have been b, then the function is represented by a prime b. Therefore a prime is x plus y whole prime plus b. B is nothing but y, right? Then what do you get? It is x prime y prime plus y. Then you could distribute this plus over n, right? So if I distribute this plus over n, then what do I get is x prime plus y into y plus y prime, which is nothing but x prime plus y. So this expression evaluated to x prime plus y, which one? This part, right? Now what is the whole part then? Whole function. Whole function can be evaluated like this. Then the whole entire function can be evaluated as f of, in place of this whatever we got, I am going to write it. What did we get? X prime plus y, that is what I got, comma z, right? Then now if this would have been a and this would have been b, then the entire function has to be evaluated as a prime b. Therefore it has to be written as a prime. A prime is nothing but x prime plus y whole prime plus b, right? B is nothing but here z, right? Then what is this? It is x y prime plus z. That is how we evaluate it. So this is the answer. So the value is x y prime plus z. Okay. Now later we shall see where to use it. Okay. Let's now see the minimization of switching expressions. Just like this particular minimization of finite automata, a language can have many finite automata, but then when you try to reduce the states, the minimal whatever we get is unique, and that contains less number of states, isn't it? Similarly, here also I want the same kind of thing. So what I wanted is, any expression or any function can be represented by many expressions, and among all these expressions I want to pick the smallest one, so that implementing it will be easy, so that constructing the electronic circuit for that will be easy, right? So watch this one. A switching function can usually be represented by using number of expressions. As I said, like a language has many finite automata, similarly a function will have many expressions. Take this example. Let us say if f of x equal to xyz, xy plus y, like this, it can even be represented by this. It is canonical sum of products. Either you can write in the SOP like this, canonical sum of products like this, or like this. Both are representing the same thing. But then what do you think is the difference? You will observe that here the number of terms are less, and here the number of terms are 4, here the number of terms are 3 only, and moreover the number of literals per term are even less here. Therefore this is smaller and compared to this. So implementing the above function will be easier if you are trying to build a circuit from scratch. And let's see why this one will also be useful in some cases later. And while simplifying a switching function, f of x1, x2, so on xn, which means when you are trying to simplify a function, our aim is to find an expression which is equivalent to f, which minimizes some cost criteria. Whenever you are trying to minimize it, the function value should not change, the meaning should not change, isn't it? So whatever is the function values, which means the assignment of all the inputs, what if for some input, if the output is 1, then even after you minimize it, the expression should produce the same function without changing anything, which means if you are minimizing f to g, then f and g should be equivalent. If you look at that function assignment, f and g should be equivalent, and then which should minimize some criteria. It depends on what you take as the criteria. Sometimes some people will take number of, let's see what are all the criteria. So there are all the criteria which are available, and let's fix up on one criteria from now on, and then we apply the same criteria for minimizing all the functions. So one criteria is you can minimize the appearances of a literal, which means you can see that a occurs only once, or a prime occurs only once. So you don't want a to be repeated 2 times. Either you could minimize it that way, or literal is nothing but occurrence of a variable either in true form or a complemented form. If the variable is a, then a and a prime both are called literals. Any occurrence of a variable in its true form or complemented form is called literal. Maybe you could note it down, maybe because we are going to use the term literal many times, right? And in fact you had note everything down so that later it will be easy for you to revise it fast. Next one is minimum number of literals in SOP or POS. So if you want to minimize it, first thing is either you minimize the number of literals or you minimize the number of literals in SOP or POS, which means you try to decrease the number of terms occurring in every min term. I mean, min term means the product term or the sum term. Now, or the other one is minimize the number of terms in SOP expression. You minimize it, and then provided that there is no such expression with the same number of terms and fewer literals. So which means this is the definition we are going to use. Minimization we are going to use this way. This one says that you even minimize the number of terms available, and within each term you even minimize the number of literals like this. You minimize the number of terms like this, minimizing 4 to 3, and then within each term you are even minimizing number of literals, and this is called the minimal expression, provided that there is no other expression which has 3 terms with fewer literals. In this case you will not find any other expression which has fewer terms, the same 3 terms and then less number of literals. So finally what is the criteria we fix upon is, whenever you are asked to minimize any expression, try to see that you reduce the number of terms, and moreover within each term you reduce the number of literals in such a way that once you have declared that something is minimal, you should not find any other thing as minimal later, right? Okay, don't worry, you just take down the theory. With problems it will be very easy, it will be dead simple. It is easiest topic you would come across, minimization of functions, right? Let's see this expression. Forget about that theory, I'll tell you later. Now let us say f is a function in 3 variables, and now we are supposed to minimize it. Okay, so how I am trying to minimize it is, I'll just take these two first and I combine them. Then what do I get? You can clearly see that if I pull out x prime and y z prime as common, there will be y and y prime remaining. Therefore x prime z prime into y plus y prime plus, leave the next term as it is, x y prime z prime plus, combine these two. It is very clear that y and z are common in that, and then x and x prime are remaining. If I pull out y and z, then what do I get? X plus x prime, and then leave the next one as it is, x y prime z, x y prime z, right? And now we can clearly see that it is 1 and it is 1. So what is it? X prime z prime plus x y prime z prime plus yz plus x y prime z. Now from the remaining, from these two, you can easily see that you could pull out z prime, these two, right? Then what is remaining? X prime plus x y prime z prime plus, from these two you could easily see that I could pull out z as common. Then what is remaining? Y plus x y prime z, right? Then now you can distribute this plus over dot. Then what do I get? X prime plus x into x prime plus y prime into z prime plus, now you can distribute this plus over dot. Then what do I get? Y plus x into y plus y prime into z, right? Then it is obviously it is x plus x prime. Therefore what you get? This is 1, and you can expand these two. Then the solution is x prime z prime plus y prime z prime plus, this y plus y prime is obviously 1, and you can expand these two, y and this one. So it is yz plus xz. Therefore when I try to minimize these 6 terms, I got 4 terms in which each term is containing 2 literals, right? So just remember this. I'll just let us put it here. Remember that we got this expression, and now you know the derivation, right? So using this procedure I am showing you that for this expression, when I minimize it, I got this expression. Now let me see if there is any other procedure available. I want to minimize the same one by doing some other procedure. Oh, I actually cut off the question. Okay, the next 3 terms are x prime yz plus xyz plus x y prime z, right? This is the expression which I was trying to minimize, and I found out that finally in one way if I minimize it, I got this answer, right? And now let me try another way to minimize it. So let me minimize these two, and let me combine these two, and let me combine these two and see what happens. See this? If I combine these two terms, clearly what is the common? x and x prime y, x prime z prime, right? Sorry, the common part is x prime z prime, and what is remaining? Y plus y prime. And now in these two, if you pull out, what we could pull out as common is yz. If I pull out yz as common, then x plus x prime is remaining. And now in these two, if I pull out, what could I pull out as common? xy prime. xy prime, then I get z plus z prime, right? Now you know that these are all ones. Now we get x prime z prime plus yz plus xy prime. This is what I get. And now we cannot combine any two terms anymore. Here also you cannot combine any two terms further. You cannot decrease the number of in min terms. See, for the same expression, when I try to minimize it, I got this one as well as this one, and both are actually irredundant. Irredundant means there is nothing redundant in this. You cannot simplify this further, nor we can simplify this further. Both are irredundant and both are irreducible. Irreducible means we cannot reduce them further. So there is no redundant term here, as well as there is no reducibility further. So what can you understand from this? Even when you try to minimize a function, you might get many different functions which cannot be reduced further, right? And moreover, even though in these two you can say that this is minimal, right? But then there is a chance that, not in this example, there is a chance that I might get one more minimal expression which contains different terms, but then the same number of terms and the same number of literals per term. So minimal is not always unique, and moreover there could be, and moreover, see this, even though it is irreducible, it is not minimal. So two things you should observe is, if you have simplified the terms in such a way that you are not able to further simplify it, and you are even proving that I cannot further simplify it, it does not mean that whatever answer you got is minimal. That is first thing you keep in mind, because it is an example. You cannot simplify it further, but it is not minimal also. And second thing is, there could be many minimal expressions for the same function. This might not be the only one, you could get even more. Not for this example, for some other examples. So keep this in mind. And in order to define all this, we are going to introduce new terms, the terminology. And the terminology is like this: irredundant and irreducible. Irreducible means we cannot reduce it further. Irredundant means in the expression there is no term which is redundant, that is irredundant. Okay, now watch this. Irredundant or irreducible expressions. An SOP, which means sum of products expression of an SOP expression from which no term or literal can be deleted without altering its logical value, is called irredundant or irreducible expression. What does it mean? They are saying that if you take this one, you cannot delete a term or you cannot delete a literal. Term means this one, min term. I mean, not min term means it contains all the literals. Term is nothing but, you can take either a product of two variables, two literals, or a sum of two literals. It is called as a term. Now they are saying that if we cannot delete any term or any literal without altering the meaning, which means if you try to delete it, the meaning will change, right? Then such a term is called irredundant expression. Such an expression is called redundant expression. Now this is very important, this note. An irredundant expression is not necessarily minimal. It is irredundant, but it is not necessarily minimal, right? So in the exam, when you get an expression and when you are struck at that point and you are not able to further reduce it, don't say that there is minimal. That would be wrong. An irredundant expression is not minimal, nor the minimal expression is always unique, which means when I try to minimize it, I might get an answer, you might get an answer, both might be right, both might be minimal, and both might be different, right? It is unlike finite automata. In finite automata, what happened when many people try to minimize the finite automata, everyone is supposed to get the unique minimal finite automata. But here the answer could be it is not true. Anyone, depending on the procedure you follow, you might get a minimal answer, I might get a minimal answer. Got it? Now let's see what is the relationship between these minimal answers and irreducible everything. What is the class of it? In order to simplify a function, the expression, using that algebraic rules, it is going to be really hectic. Maybe you might have seen that previously I was trying to do simplification in two methods. and it is very difficult to again trace back and take other path. Once you are done with the shortest, once you got a expression, proving that it is minimal is difficult, first of all, because we got four literal term or four terms expression, and now we don't know whether to say that it is minimal or not, and now we have to see all possible minimal expressions. Therefore, minimization using these formulas and then algebraic methods and applying them some rules, it is all going to be very hectic. So a better convenient method has been introduced, and it is called K-map. So K-map is particularly convenient to represent the function as well as to minimize it. It lends itself so that we could easily visualize the function and then we could easily minimize it. And in GATE exam, they'll give you either 3 variables or 4 variables, and for 3 and 4 variables, K-map is the best way to minimize it. There are other ways also, we shall see it, but K-map is the best one. So let's write some theory. Let's get used to the terminology. What I suggest you is, I'll read out the points. You just keep pausing it and you write the theory. This theory will be useful to help you in solving the questions, definitely. So please write it down, and then later you can revise it easily. So because it entire thing it is going to be a bit confusing from now on. But let me tell you, this is the easiest topic you could think of. In computer science, you could easily solve this and get 4 marks question easily. Okay, let's start with this. K-map. The algebraic procedure of combining various terms and applying them, the rules becomes very tedious as the number of variables increases, which means as the size of the expression becomes very large, then the algebraic method obviously becomes very tedious, right? The map method provides a systematic method for combining the terms and deriving the minimal expression. So the map is actually designed in such a way that it lends itself readily for the simplification. A K-map is a modification of the truth table. So K-map is actually a kind of truth table, because in truth table, what did you see? We find out all the combinations and then we assign the truth value. Similarly here also, in a K-map, for every combination there will be a designated cell. In the designated cell we write the truth value. Therefore K-map is a kind of truth table, even though it looks different, right? It is a truth table in which the arrangement of combinations is particularly convenient for minimization. What is the difference between truth table and this one is, in truth table you cannot directly look at the truth table and keep on combining the terms, but in this K-map you can look at the table, that map, and you could combine the terms and keep on minimizing it. That is the main difference. Truth table and K-map both are almost same. Only difference is, in truth table you cannot apply minimization because it doesn't lend itself, the format there is different, but in K-map it is actually suited for minimization. And now every n variable map consists of 2 power n cells, which means if you have n variables, then how many terms are there, min terms? 2 power n. If you have 3 variables, 8 terms, 4 variables, 16 terms. Every n variable map contains of 2 power n cells representing all possible combinations of variables. For example, a 3 variable map has this big, right, 8 cells, and similarly a 4 variable map has 16 cells, right? So and one more thing, many students, when in the classroom when I teach this, they get confused in one small thing. See this, whenever you are filling the rows, whenever you are putting the numbers about the table, these tables, okay, watch it, I'll just explain you one by one. Now this cell, so whenever you form a table, let us say this is a 3 variable map, which means this is used to simplify any function which is containing only 3 variables like x, y and z, and each cell is going to represent one particular value. For example, this cell is actually representing one min term. What is the min term? See this, it is x, it is y, it is z, which means this column corresponds to x value and y value, and row corresponds to z. It is not a rule that you should always put x and y in the row and z in the column. You could as well put as x here and then y z. It is not an issue. But then when you have fixed upon some convention, try to follow it when you are trying to filling it, which means when you are trying to take the min terms and write it there, just follow the convention. If you have used x and y, then corresponding element should be made made there, right? And now see this particular element, this cell 0, actually corresponds to the min term x prime, y prime, z prime. How? See this, x and y are 0 0, therefore x prime, y prime, and z is 0, therefore z prime. And if you look at this cell, this particular cell, if you want to know which min term corresponds to this cell, just look at this combination. So x is 1, y is 0 and z is 0. Oh sorry, z is 1. So this cell corresponds to x, y, 1, 0 and z is 1. So what is it? X, y prime, z, right? So that is how you could represent each cell. So all the 8 cells, why are there 8 cells is, if you have a 3 variable functions, the number of minterms present in 3 variables is 8 and each one of them can assume either 1 or 0 independently. Depending on the function we are going to fill this. And I have written the numbers just for the convenience, but then I suggest you not to by heart them. So one mistake what you might do while constructing this K-map is, here it is 0 0 0 1, then remember it is 1 0, right? What people try to write is 0 0 0 1 and immediately they will write 1 0 and then 1 1. That is wrong. So keep this in mind. It should be 0 0 0 1 1 1 and 1 0. Why is this so? I'll discuss that shortly. Two cells should have only one literal changing. What is that? I'll tell you later in soon. So just remember that 0 0 0 1 1 1 1 0 has to be used. It is not 0 0 0 1 1 0 1 1. You don't do that. And next thing is, here also the same thing. It is a 4 variable K-map. If the number of variables are 4, then how many minterms are possible? 2 power 4, which is 16, right? W, X, Y, Z, and all of them can be 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0, and each cell is representing one minterm. For example, let us say this cell. If you want to know what this cell is representing, just see what WX combinations for that are. The WX combinations are 0 1 and YZ combinations are 1 1. So W is nothing but 0 is nothing but W prime and 1 is nothing but X, and YZ are nothing but 1 and 1, therefore YZ. So W prime X Y Z, this is represented by that, right? So the numbers which I am writing in these cells are not of any significance. Don't read them, don't by heart them. For the explanation I am just giving you that. So don't by heart them. What will be present inside these cells is the truth values for that particular minterm. What is the truth value associated? That is what I am going to write it there. Okay, we shall see more about this. I'll explain you, and after seeing this we shall see some questions, and then we shall go into depth about how to solve all the questions in this. Watch this. The function value associated with a particular combination is entered in the corresponding cell. So once we have the K-map, then go to the corresponding cell which represents that particular minterm, and we are going to put that number, put that truth value. For example, look at this one. Let us say, let's not write these function values inside. Let's say it is a 3 variable K-map, right? And assume that the function is like this. The function is sigma 3, 7, which means we have 2 minterms, and these 2 minterms are having value 1 and the other minterms are having value 0. If the function is having 2 minterms, which means in this function only these 2 minterms are given a value of 1 and other are given 0. So what is 3? 3 is, you can write it like this, right? X prime YZ. And what is 7? X, Y, Z, right? Therefore only in these 2 cells we are going to put 1, and in the remaining cells we are going to put 0. Now what is X prime YZ? X prime YZ means 0 1 1. So 0 1 1 is 0 1 1, this one. This is 3, and 7 is X Y Z. X Y Z means all are 1. So X Y Z, which is nothing but this one, right? So that is how these 2 are represented. That is the meaning of the first one. The function value associated with a particular combination is entered in a corresponding cell, which means every function is going to have minterms, and the minterms are going to have value 1s, and in that particular cell we are going to put 1. Next one is, cycle code is used in the combination as column and row heading. So what is cycle code is, whenever we have a cycle code, it means that we are actually changing, or if you have a cycle code, the property of cycle code is between any 2 successive numbers there will be only 1 bit change. For example, see this, if I write 0 0 and from 0 0 if I change to 0 1, if this is next number in the cycle code, only 1 bit is changing, right? And if I write 1 1, check this, From this to this, only one bit is changing. What is the one bit? The first bit. Second bit remains same. And if I change from 1 1 to 1 0, and again one bit is changing. Just check this. Here from 0 to 1, only one bit is changing. And again from 0 to 1, only one bit is changing. And again from 1 to 0, only one bit is changing, right? That is called a cycle code. Again, at the end I will talk about cycle codes in detail, but for now understand that if I have a cycle code, between any two numbers, adjacent numbers, there is only one bit change. Just keep that in mind, right? So what is that they are saying is, cycle code is used in the combination as row and column heading. So look at this row heading, 0 0 0 1 1 0 1 1. If you look at any successive numbers, only one bit changes. That has a practical significance here. I'll talk about it. And even look at the row 0 1, which is nothing but only one bit changing. Now here also you look at it in the four variable map. Look at the column headings, 0 0 0 1, only one bit is changing. And from 0 1 to 1 0, only one bit is changing. And from 1 1 to 1 0, only one bit is changing. The same thing is happening in the row values also, right? So watch this. So what does that mean? We are going to change only a single value either in the row or in the column, right? Whenever we are going from one row to the next row, like that. Because of this, we have some good property there. Because of these codes, what are the codes? Cycle codes. Two cells which have a common side. So what is two cells which have a common side is, look at these two cells, this cell and this cell. These two are having a common side. This is the common side, right? That is what they are talking. Because of these rules, two cells which have a common side correspond to combinations that differ by the value of just a single variable. So what is the meaning of it is, just look at these two. These two cells are having a common side. Because of this property, these two min terms just differ in just one term. So if you write what it is nothing but x prime y z prime. This is x prime y z prime. And if you write this, it is nothing but x y z prime, right? Now these two differ only in one cell. What is this cell? Here these two are same. I mean, what is the variable? Differ in only one variable, right? So y and z prime both are same. Only difference is x and x prime. Got it? And now these two cells play a major role in the simplification process. So because of this difference, we are able to simplify it. Why is this K-map really suitable for simplification procedure is because we are having cycle codes representing the headings, and because of that, two cells which are adjacent are going to have only one variable difference, because of which we can apply the simplification rule like this. See this. Now when we have only one variable changing like this, we can pull out the common variable side. So what is that we can pull out? Y z prime, we can pull it out. Then we can combine happily x prime and x. Then what is it? It is nothing but 1. So simplification has happened only because of this rule. What is the rule? The headings are cycle codes, and now they are differing. Two cells which are adjacent are just differing in one variable, right? So these two cells play a major role in simplification procedure because they can be combined by means of the rules this one. So when there are two min terms which are differing by only one variable, and that variable can be eliminated, isn't it? Therefore by combining two cells, I can eliminate one variable. What if I combine four cells? In four cells, how many will be differing is 2. If I combine four cells, I can eliminate 2. Okay, we shall see it. Don't worry, we shall go step by step. So what is this entire procedure is? Now I am able to draw the something called as K-map, and K-map has an inherent character that the row headings or column headings are going to be cyclic codes, because of which if there are two cells which are adjacent to each other, which are having a common side, then definitely we can combine these two cells and we can minimize the expression. How? By applying the rule which we have just seen, right? Now let's see how to minimize a function using the K-map. So we know what is a K-map and how it is useful for minimization. Let's see the procedure, what is used. So first of all, we are going to define something called as a subcube. Subcube. So what is subcube is? A subcube is a collection of 2 power m cells. So always a subcube will be a power of 2 size. Okay. Each adjacent to m cells. which means if you take a subcube, any collection of 2 power m cells is not going to be a subcube. If you take a subcube in which every cell should be adjacent to m other cells, right? Each adjacent to m cells of the collection. So if you take a collection of 2 power m cells, then in that every cell should be adjacent to m cells, right, of the collection is called subcube, and the subcube is said to cover all these cells, right? So I'll tell you just what the meaning of it is. Let us say you want to see what is a power 2 subcube. If you want to talk about a power 2 subcube, then in that collection of the subcubes which are having 2 power 1 subcube, every cell should be adjacent to one cell, which means both the cells should be adjacent to each other. That is what the meaning. So if you have this element and this element, these two can form a subcube because it is a collection of 2 power 1 cells, which means 2 cells, and moreover these two cells are adjacent to each other in the collection, right? Now when you say a subcube of size 4, which is nothing but 2 power 2, if you have to call it a subcube, then every cell in this should be adjacent to 2 other cells, then only you can call it a subcube of size 4. So for example, if I take like this 4, can I call it a subcube of 4? Yes, because you take every cell, every cell is actually adjacent to 2 other cells. This one is adjacent to this one and this one. This one is adjacent to this one and this one. This one is adjacent to like that. So every cell, if you count it, it is adjacent to 2 other. Maybe let's see if there is any other subcube of size 4 possible. If this is not the case, this one, this one, this one, this one. If you have to call this as subcube, then every cell has to be adjacent to 2 cells. So this one is adjacent to 2 cells, right? And this one is also adjacent to 2 cells. What about this one? Is this one adjacent to 2 cells? You are finding that this one is adjacent to only this cell, right? But actually this cell and this cell are also adjacent. The reason is you can actually wrap around and you can make them adjacent. Or remember that whenever you have this like this, they two are adjacent actually. So how can I prove it is, if you see the value of this, it is w prime x prime y prime z, and if you see this value, it is wx y prime z. So only one value is changing, therefore they are adjacent. So therefore it could form a cell subcube, right? Now let's see any other combination which could form a subcube. Let us say I have values like this. It is a combination of 4 cells. Can it form a subcube? It turns out that it cannot form a subcube because the entire 4 cells cannot form a subcube. Maybe these two can form a subcube, these two can form a subcube, these two can form a subcube, but all those subcubes are of sizes 2. They all combined cannot form a subcube of size 4, because if they have to form a subcube of size 4, then every cell has to be adjacent to 2 cells. But then if you look at this cell is adjacent to 1, 2, and this one is adjacent to 1, 2, but then this one is adjacent to only 1, and even this one is adjacent to only 1. Therefore you cannot put all of them in one subcell. So remember that whenever it has to be a subcube, then the number of cells each one is adjacent should also be counted. So if the subcube has to be of size 2 power m, then every cell in this collection should be adjacent to m cells, then only you can call it as a subcube. Now what is the importance of this subcube is, once you find a subcube, we have found a minimization, which means if every cell is represented by n variables, then the entire collection of these 2 power m cells can be represented by a literal, by a term, by a product term which is having less than n cells, n variables. See this? Each subcube can be expressed by a product containing n minus m literals. Once you form a subcube, then you can express every subcube as a product containing n minus m. So why n minus m? If the subcube size is 2 power m, then you can actually reduce m terms. How is it possible? I'll just show you in some time. It is possible. Literals, where n is the number of literals in the variable, and then it is different. So I'll just explain you what they mean. See, let us say I have a n variable function. Then how many cells will be there? 2 power n cells are there, and each cell is represented by n variables, isn't it? Because every minterm contains all the variables, right? And every cell is a minterm. So if I have 2 power m cells combined, then all these m cells can be represented by a single product term which contains n minus m terms only, m variables only. The reason is these n variables, out of these n variables we can remove m variables by combining all these cells. That is why the K-maps are used. So just as an example, I'll tell you this. If I have, okay, consider this one. If I have one here and one here, so what does these two represent? Check this one. If I have one here and one here, what does these two represent? This one is representing W prime X and Y prime Z, right? And what about this one? If a function is having only these two ones, I can put a plus, right? And what about this one? This one is representing Wx Y prime Z, right? Now you can check, you can clearly see that these two are same and only these two are differing, right? Therefore, when there are two cells which are adjacent, only one variable will be differing and that variable can be removed by pulling out everything as common. Therefore, when you combine them, it turns out that we need only this term to represent it. When I combine them, I get this. So what has happened? Initially there are three variables, and now by combining two cells of size or a subcube of 2 power 1, therefore it is represented with, sorry, it is 4 variables, right? Initially it is a 4 variable function, and by combining two cells it is represented with 4 minus 1, which is nothing but 3 variables. That is how I got it. Now let us say I have a cell of size 4, then what does it mean? I have a cell of size 4, which means this one and this one. Now just now we have combined these two and we found out that the value is, what is the value we got? I think we got X Y prime Z representing this. Similarly, you can combine these two, and when I combine these two, I'll get a value of, okay, first of all, is it a subcube? Yes, it is a subcube because this size is power of 2, and next is every cell is adjacent to two cells, this one and this one. Every cell is adjacent to two cells, therefore it is subcube, and therefore I'm trying to see how many terms can be reduced by combining a cell of size 4. So if I combine a cell of size 4, which means this one, then what I get is these two, when I combine them, I am going to get X prime and then YZ, right? Therefore this cell is represented by this term and this cell is represented by this term. Now when I combine this entire thing, just check this. If I combine this, if I write a plus and if I combine this, because the function is actually a combination of all this, it turns out that we could even reduce further. Oh, I just wrote something mistake here. So this is X and this is Y prime Z, okay, and this is X and this is YZ. Oh, this is X, Y, Z. This is X. If you combine these two, you are going to get X, Y, Z. Okay. Now, if you look at this, this is changing and others are remaining. Therefore, if you combine them, the value turns out to be XZ. So, therefore, the function or the term which represents this entire 4 cells is now containing only 2 variables. Why? Because the total is 4 and I am combining 2 power 2 cells. Therefore, how many variables will get reduced? 2, right? So the resulting expression has 2 terms or 2 variables. Got it? So this is how we could minimize it. We shall see more points on this and then we can solve the problems. Let's see how to minimize using a K-map. A function f can be expressed as sum of those product terms which corresponds to the subcubes necessary to cover all ones. It means that first you take the K-map and in that K-map you put all the ones, the function ones. I mean wherever the min term is 1 in the function, in that location you put 1 in the graph, that K-map, and then a function f can be expressed as sum of those product terms which correspond to the subcube. Then you find the subcubes, all the subcubes, and then you find the expression representing the subcubes which are covering all these ones. If you write all those expressions, that is nothing but the simplification of the function, right? Or I'll just tell you with examples, it will be clear. Okay, even if you didn't understand, if you don't understand any statement now, you please write them down. Once I take the example and explain you, it will be easy for you. What I am saying is, a function f can be expressed as sum of those product terms. So if you want to express a function, you can express using sum of product terms which correspond to sub terms which are going to cover all ones. These are important terms, which means in the K map you put all ones and then you are going to find the subcubes, and for those subcubes you are going to get the product terms. Now you add all those product terms, that is nothing but the f. Simple, right? Okay, with example it will be clear. Next one is the number of product terms in the expression for f, which means if you apply this procedure, then how many product terms do you get? Each product term is going to represent a subcube, right? Therefore the number of product terms in the expression for f is equal to the number of subcubes. Obviously, if you are going to use the subcubes to get the function, then the number of product terms in the function will be equal to the number of subcubes, while the number of literals, which means how many terms are present in each subcube, that depends on the size of the subcube, isn't it? Then the number of literals in each term is determined the size of the corresponding subcubes, right? So now there are two things. See, you have a K map and then you have ones in that. Ones represent wherever the function is having ones. In the K map you are going to put ones, right? Now what is that, how to simplify it is, we are going to cover all these ones using subcubes, and for every subcube you are going to get a product term. Therefore a expression can be represented as sum of product terms where the number of product terms are equal to number of subcubes and the size of each product term is equal to the size of the subcube. Therefore if you want to minimize this function as much as possible, there are two things. See, if you understand this carefully, they are saying that a function can be expressed as two things. One is number of subcubes or number of product terms, right? And the second is number of literals in each product term, right? So the number of product terms depend on number of subcubes, first thing, and the number of literals in the number of literals which are present in the product term, that depends on the size of the subcube. So if you want to reduce the size of a function, then you should see that the number of product terms are less as well as the number of literals are less, which means the size of the subcube is more. So in simple terms, if you want to get the minimal function, then try to cover all the ones in the K map using very less number of subcubes and then as big subcubes as possible, right? That is simple terms. So therefore to obtain a minimal expression, what is minimal expression? The expression in which the expression which is you cannot find any expression which is smaller than that, that is minimal expression. So first thing is, every minimal expression is irredundant and irreducible, right? And a minimal expression is nothing but if you cannot find anything less than that, smaller than that, that is called minimal. Therefore every minimal is irredundant. Maybe if you want to see what is the relationship between irredundant and minimal, if this is the irredundant, this is the minimal, this is the minimal, this is the irredundant. How did we get this? Irredundant is nothing but from which you cannot decrease any number of terms. Minimal is nothing but smallest among all the irredundant terms is minimal. And how many minimal can be there? Many. So we shall see it. Okay, don't worry, we shall see it. For now just understand this. To minimize to obtain a minimal expression, we must cover all one cells, which means like this, all one cells with the smallest number of subcubes such that each subcube is as long as possible. So why should we have smallest number of subcubes is because the number of subcubes determine the number of product terms in the expression. So if you want to have less number of product terms in the expression, then have the smallest number of subcubes such that each subcube is as long as possible. Why should it be as long as possible is, why is this term valid? Why should it be as long as possible is, the longer the size of the subcube, the smaller the size of the product term. Got it? So decrease the number of product terms first thing, and then decrease the size of the product terms, then you are going to get the minimal expression, right? Let's take this example. If the function is given as sigma equal to 2675, so don't worry how I represent it here. Let us say I got this representation. Later I will show you how to represent it. For now understand that this is the function given, which means it is having one here, one here, one here, one here. Now try to cover these ones with as big subcubes as possible. Can I have a subcube of 4 here? No way, because these 4 are not actually adjacent to 2 each. If you have to have a subcube of 4, then every cell has to be adjacent to 2 cells. But then this cell is not adjacent to 2 cells. Therefore, a subcube of 4 is not possible. So next biggest is subcube of 2. That is why I am going to combine this one and this one, right? And now if I combine this one, so what is the sub? In order to cover all the ones, we need at least 2 subcubes, and the size of each subcube is 2, right? So therefore what you could observe here is the number of subcubes required is 2 and the size of each one is 2. Then we can represent this entire expression using 2 product terms, this one and this one. What is the product term representing this is? How to obtain it is, I'll tell you a method. Observe this. Now check these two. In these 2 cells, see what are the things that are remaining constant and what are the things that are changing. These 2 are having x as 0 and 1, isn't it? xy as 0 and 1. If you are getting confused, you can write it here. xy. The first one is having x as 0, the second one is having x as 1. Therefore, the value of x is changing. What is remaining constant? Y is constant and z is constant. And what is that value of y? Y is 1. That is why I am taking true form of y and then z. So in the z is nothing but z is constant and z is in 0. Therefore I am going to take complement of z. So this term is represented by yz bar. And what about this one? If you look at it, x is constant in both of them, which means x is not changing, but y is changing. Therefore you can whatever is changing, you can remove it. Y is changing, but z is constant, right? Therefore you remove y, and what is x? X is in its true form. In both of them x is 1, therefore represent x in its true form, and z is 1, therefore represent z in its true form, right? So these 2 terms are going to represent this entire function containing 4 ones or 4 minterms. So actually the initial function contains 4 minterms, in which every minterm is containing 3 variables. But now we are able to cover everything using 2 subcells. Therefore we got only 2 subcubes. Therefore we got only 2 product terms, and the size of each subcube is 2. Therefore I am able to reduce the size number of variables by 1. So if you look at each product term, the number of variables present is 2, because 3 minus 1 is 2. How? By having a subcube of size 2, I could reduce 1 variable. Got it? So now if you understood all this theory, it is fine. Otherwise, don't worry, forget it. Now we are going to do lots of examples, and every example I am going to take a new example, and I'll explain you how this actually minimization is going to work. So I hope that you have taken the notes till this point. Keep that notes with you, and whenever I am solving the questions, you just refer the notes once, so that you will understand each point even better. The reason is not every question in digital is going to be in numerical. There might be some theoretical questions. If you have to answer those, you should be understanding all this theory thoroughly. Otherwise, you will not be able to answer it, right? From now on, we shall see lots of problems, and each problem is supposed to answer touch some point which you didn't understand. Maybe if you didn't understand it, right? I am going to touch all the points, theoretical points, with one problem each, right? So entirely the summary is, if you want to minimize any expression, put it in form of a K-map, and then try to cover all ones using as less number of subcubes as possible, such that the size of each subcube is as big as possible. Okay. Now look at this, implicants. So before talking about implicants, let's talk about covering. So why is implicants important? Is when you're trying to derive the minimal expression for any given expression, we should find out all the subcubes which are called as essential prime implicants. So in order to find out essential prime implicants, you should first know what an implicant is, second you should know prime implicant, and third one is essential prime implicant, because these things play a key role in the minimization. So let's go step by step. So before talking about implicants, I want to talk about covering functions. So just see this. See, with this example, I'll tell you this, and then I'll tell you this point. You please make a note of it later. See. Now, if you look at this, let us say it is a 2 variable function. In 2 variable function, how many minterms will be there? Totally 4. Therefore 0, 1, 2, 3, 4 minterms are there. let us define g to be a function which is having a 1 at 1, 0, 1, which means at this point it is having 1 and at all the other points it is having zeros, right? Now if you look at f, the way f is defined, look at the way f is defined. F is having 1 1 here and 0 0 here. So whenever g is 1, f is 1. So you can say that f is actually covering g, which means inside f all the minterms that are present in g are already present. Or if you look at this, the f contains the minterm 0 and 1 and g contains the minterm only 1, which means whatever minterms are present in g are already present in f. That is the meaning of it, right? Now watch this. A switching function f x1 x2 so on xn is said to cover g x1 x2 so on x2 if f is superset of g, which means if f contains all the minterms which are already present in g, then it is called f is said to cover g if f assumes true value whenever g does, right? So which means whenever g is having true value, f is having true, right? Now if f covers g, if f covers g, it means that f is superset of g, and at the same time if g covers f, then it means that g is superset of f. When will that happen? When both are actually equal sets, right? Then we can say that both are equivalent. So if f covers g and at the same time g covers f, then f and g are called equivalent. Watch this one. Now let us say g is this, then how many functions are possible which will cover g? In order to cover g, wherever g is having 1, we have to have 1. Therefore I have kept 1 here, and all the others are optional. In the other places either you could put 0 or 1. Therefore how many functions are possible for f which are covering z is, in all the other possibilities we have two chances, 2 into 2 into 2. Therefore 8 functions are possible. In general, how can you find out number of functions covering a given function is, you find out all the minterms of the given function, and then in the covering function you put them as all ones, which means we don't have any choice there. In the remaining minterms, which means whichever are not there in g, let us say in the remaining minterms, the next function, the covering function could assume any two values. Therefore it is 2 into 2 into so on the remaining functions. Now let's see how to derive it. If g has x minterms and g is a function of n variables, if g is a function of n variables, how many elements will be there in this minterm? How many elements will be there in this table? If g is a function of n variables, 2 power n elements will be there, right? And out of which g is already choosing x minterms. Therefore how many remaining elements will be there for f to choose? All these x terms whichever are present in g should already be present in f. Therefore f does not have really any choice on x. Therefore f has choice only on 2 power n minus x, which means in the remaining minterms whichever g left out, f can assume any two values. Therefore 2 into 2 into so on these many times. So this is the total number of functions which will cover a function g, given that both the functions are in n variables and then g has x minterms, right? It is simple to derive, I think. See, wherever g is 1, f has to be 1. Therefore I am putting in there 1, and wherever g is 0, there f could assume anything. Then how many max terms are there in g, which is nothing but how many zeros are there in z? 2 power n minus x. Now all these chances at all these locations, f can assume either 0 or 1. Therefore 2 power n minus x. Got it? So these many functions are going to cover g, given any g. And see this example. I'll just show you. I'll just try to solve it. If f of x equal to wx plus yz, if this is the expression given, then how many functions will be covering f? In order to understand how many functions covering f, you have to understand how many minterms are there in f. So first of all, how many minterms are possible with 4 variables? The total number of minterms possible are 16, right? Now let's see, out of this 16, how many minterms has f already chosen? How can we get it? Given the function, convert it to canonical form, canonical SOPs form, sum of products form. Now in this wx, two terms are missing. What are they? Y and z, right? So wx is present here, y and z is present here, which means wx followed by yz, and now we don't have two terms. those two terms can assume any value, which means 0, 0, 0, 1, 1, 0, 1, 1. So what we could do is, in place of w and x, we could have 1, 1. The reason is both are non-complemented. See, I am telling you a method by which you can quickly arrive at the minterms, number of minterms present in a function. See, in place of wx I am putting 0, 0, and in place of y and z you have 4 combinations. Therefore 1, 1, 0, 0 or 1, 1, 0, 1 or 1, 1, 1, 0 or 1, 1, 1, 1. These are all the 4 combinations for, or they are all the minterms which are generated from wx, and then yz. Y and z are here, w and x are here. Therefore y and z is 1, 1, and then wx can take any number of choices. Therefore 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, right? So this is how you can expand it. So maybe you could keep it in mind. So whenever you want to expand it into sum of products, canonical sum of products, you just take the min term or the product term and you just write the combination for it, and in the remaining combinations, whatever is remaining, which means how many variables are remaining, in those combinations you try to put all the combinations in their positions, right? Now you see that it is already repeated and all the others are unique. See, 1, 1, 0, 0 is not repeated, and 1, 1, 0, 1 is not repeated, 1, 1, 1, 0 is not repeated, 1, 1, 1 is not repeated. So they are all unique. So how many minterms are present in f? F is already containing, out of 16 minterms which are possible, f is already containing 7 minterms. Therefore f is not containing 9, right? So what happens, if any function has to cover f, that function has to have all these 7 minterms. Along with that, it should have 9 more minterms. It could have any of the 9 more minterms, right? Or in case of subset set theory also, you could think of it this way. If a set is already containing 7 elements, then how many sets are going to be superset of this set? That is same thing, right? If the set is already containing 7 elements, the superset of it should also contain 7 elements. Then how many elements are remaining? 9 elements. In these 9 elements, the remaining set, the set which is going to cover this set, can take any value, which means the number of power sets possible with 9 elements, which is nothing but 2 power 9. Or if you didn't understand this, see, already f is having 7 minterms. Therefore the function which is covering f should also have all the 7 minterms, which means all the ones at the 7 locations. And how many locations are remaining? 9 locations. In those 9 locations, it could have 2 possibilities, right? Therefore 2 into 2 into 2 into 9 times. So 2 power 9 is the total number of functions which are capable of covering f. Anyway, we could find out the number of functions covering it, but my main intention in teaching about all this is to know about the implicant. So now let's talk about the implicant, and then prime implicant, and then essential prime implicant, and then minimization. Okay. Now watch this. If f covers g, then g is said to imply f. So if f is covering g, means wherever g is having 1, f is already having 1. If f covers g, then g is said to imply f. So it is written like this: g is said to imply f. So what is the meaning of it is, from f we can derive g. It is not that from g we can derive f. So you just get confused here. When g is implying f, it means that whenever g is true, f is true, but the reverse is not true. Okay, about this implication we shall again discuss in this logic we have in discrete mathematics. There I will talk about it clearly, but you just understand here. So g implies f doesn't mean that whenever f can be derived from g. No, it means that whenever g is true, f is true, right? Just keep it in mind. Now we can also say it as g is a implicant of f, which means whenever g is true, f is true. So in digital logic or in general logic, whenever I say g implies f, it just means that whenever g is true, f is true. But we cannot derive the entire f from g, which means we don't know what are the truth values of f. We can only say that truth value of f must be true whenever g is true. Now what is the relation between this implicants? What is implicant? If a function is covered by other function, if f is covered by g, then f is called implicant of g. Or in this case, if f covers g, which means g is covered by f, then g is implicant of f. So now I'll just tell you what is the relation between the function, the expressions, and then the implicants. Let us assume that f is a function of three variables a, b, c, and now the function is represented like this. The function f is a, b plus c, right? So what I did is I have written this entire all the min terms possible, and then I have shown you what ab is. So ab means all are zeros and only here there is 1 1, and c is nothing but the same c I copied here, right? So what you would think of is, now f is a combination of two functions. Let us say this is f1 and let us say this is f2. So therefore f1 is this and f2 is this, and f is a combination of f1 plus f2, right? So f is a combination of f1 plus f2. If you watch it, if you look at the f, now f is going to cover both f1 as well as f2, which means whenever f1 is 1, f will be 1, whenever f2 is 1, f will be 1. Therefore both ab and c are covered by f, which is ab plus c, or you can even say it as both ab and c are actually implicants of f, right? So the terminology is, since f is covering these two, right, so these two are implicants of this, which means every function can be written as if all the product terms are implicants of the function. If I have a function like this, sum of products, right, or any sum of products, then I can take each product and I can say that each product is an implicant of the function, right? And now what is the relationship between the each product and the function in terms of k map is, if you look at the k map, ab is this and c is this, right? So every product term can be written as a subcube here, right? Therefore every subcube is now an implicant of function. Now are you finding relationship? Every function is having product terms, therefore every product term is an implicant of f, because f is covering every product term, isn't it? And now every product term is also a subcube, therefore every subcube is an implicant of a expression. So now we derived that if you have a k map, then in the k map every subcube is an implicant of the function. Therefore how can you write a function as the sum of all these subcubes? Got it? Then what is a prime implicant is, see, every subcube is an implicant, every subcube is an implicant. Now what is a prime implicant is, an implicant, so I'll just tell you informally what a prime implicant is. Every subcube is a prime implicant, which means this is a prime implicant, this entire thing is a prime implicant, as well as this is a prime implicant because it is a subcube, right? And as well as this is a prime implicant, right? As well as this is a prime implicant, right? And this is a prime implicant. These many prime implicants. Sorry, these are all called implicants, not prime implicants. So every subcube is an implicant. Now what is the difference between implicant and prime implicant is, so if you have a biggest implicant, then that is prime implicant, okay? And moreover, okay, watch this, I'll tell you. So among all the implicants, if a implicant is not a subset of any other implicant, then that is called prime implicant, which means if you call it as a prime implicant, then it should not be completely covered by any other implicant. So in terms of subcubes, we can say it like this: a subcube is said to be prime implicant if it is not present as a part of any other subcube, right? So in this case, if you see all these implicants, these are present as a part of some other implicant, therefore they cannot be prime implicants. So only there are two prime implicants. What are they? This entire 4, a cube of 4, that is a prime implicant, as well as this cube of 2, that is a prime implicant. Why? Because these two cannot be part of any other implicant, and moreover this entire thing cannot be a part of any other implicant. Now in terms of this product terms and in terms of the subcubes, both of them we shall define the prime implicant. See this? An implicant P of f is said to be a prime implicant if P is a product term. First of all, it should be a product term. Why? Because it has to be a subcube, right? So product term. And second is, deletion of any literal from P results in a new product which is not covered by f. So what does it mean? If you try to delete any literal, so how can you delete a literal? If you delete a literal from a product term, let us say I have here AB. Now if I try to delete A or B, what happens is we are actually increasing the subcube, right? We cannot increase the size of the subcube because we are getting more cells into the subcube, and those cells may not be present in the function. Therefore, if you try to delete any literal from P, then we are going to get a term which is not covered by F, right? So if that is not the case, what is this meaning of this in terms of subcube is, if we have a subcube, then that should be the longest subcube possible, which means this subcube should not be part of any other subcube. So what is the prime implicant? It should be a subcube, and second thing is it should not be a part of any other subcube, which means it itself should be the longest subcube possible, right? That is called prime implicant. So now we have seen what is an implicant. What is an implicant? Anything that is covered by a function is called implicant. So in this function, these two are implicants. Now coming to the table K-map, these implicants turn out to be the subcubes, right? And these subcubes, if they are the biggest subcubes, they are called prime implicants. Simple. Now we shall define what is essential prime implicant, and then we shall see how to minimize the function, right? So implicant is a subcube that you know, and prime implicant is the biggest subcube which is not a part of other subcube, any other subcube. And now what is essential prime implicant is, if a prime implicant is covering at least one cell which is not covered by others, then that is called essential prime implicant. Why is it essential is, if you don't include it in the function, there is no way we could cover that one. Okay, again, implicant means a subcube. Any subcube is called implicant. Prime implicant means the biggest subcube which is not a part of any other subcube is a prime implicant. Essential prime implicant means it should be able to cover at least one minterm which is not covered by anyone else. Now why is it essential? If you don't include it in your function, then your function will not show that that particular minterm is present in your function. That is why it is very essential, right? So essential means you should definitely include it. And other prime implicants, you may or may not include it depending on whether they are covering any ones which are not covered by others, right? So let's keep it simple now here. A prime implicant P of a function f is said to be an essential prime implicant if it covers at least one minterm of f which is not covered by any other prime implicants. So let's take all these examples and see what are essential prime implicants, what are prime implicants, right? Now watch this one, first one. If you look at it, these four can form a prime implicant. So definitely they are implicant because they are subcube. Is it a prime implicant or not? How can you decide it? If it is a prime implicant, it should be the biggest one which is not a part of any other, right? So is this the biggest one possible? I mean, can it be, can it be a part of any bigger subcube? No, you cannot make it a part of a subcube of 8 because in fact there is no subcube of 8 here, right? Therefore it is a prime implicant, right? And look at this. This is again one more prime implicant. See, prime implicant is not the biggest biggest implicant is not prime implicant. Prime implicant means you cannot be, you should not be able to put it in any other implicant. That is called prime implicant. Now see this. This is a prime implicant. The reason is this subcube cannot be a part of any other subcube, right? So it cannot be kept in any other subcube having 4 sides. Therefore it is a prime implicant. This is a prime implicant, this is a prime implicant, this is a prime implicant. Now we got 4 prime implicants of size 2 and 1 prime implicant of size 4, right? Now my question is everything essential? So what is essential? Essential prime implicant means you should be, a prime implicant should be covering at least one which is not covered by anyone else. Just watch this. This one is covering at least one which is not covered by any other prime implicant, any other implicant, right? Therefore this is essential prime implicant, and this is essential prime implicant, this is essential prime implicant, and this is essential prime implicant. Now look at the major one, the bigger one, a prime implicant of size 4 in this. Actually it is not covering even one minterm. It is not covering even one minterm which is not covered by anyone else. Whatever it is covering is already covering by combinedly all by these 4. So I'm just going a step ahead and telling you how to minimize it. See, when you minimize it, if you write this function, this function, this function, this function, or these 4 subcubes, it is enough. You need not write one more subcube. Therefore the minimal answer will contain only 4 subcubes. We shall see it later how to minimize. I tell you these steps. Here just identify what are essential prime implicants. Now look at this. In this one, it is a prime implicant. How can you know? Because it cannot be kept as a subpart of any other implicant, right? There is no implicant of size 8 in this. Therefore it is the Definitely the prime implicant, even though that is not the reason, right? So what is the reason why it is not a prime implicant? Because it cannot be a part of any other implicant. That is why it is prime implicant. Now, is this a prime implicant? Yes, because it cannot be completely immersed in any other subcube. Is this a prime implicant? Yes, because it cannot be immersed in any other subcube. Now watch it. This is also a prime implicant. Why? Because it cannot be immersed completely either in this subcube or in that subcube, right? And even this is also a subcube, right? And which is a prime implicant. Therefore, how many prime implicants we got here? 1, 2, 3, 4. How many? You just count it. It is 1 and it is 2. This is 3 and this is 4 and this is 5. Yes, 5 prime implicants we have. And out of all these prime implicants, what are necessary or essential? So only this one is essential, because look at all the other prime implicants. Every cell covered by this prime implicant is 6 are there. One more prime implicant is there. See, every min term covered by this prime implicant is covered by someone else, right? Therefore, there is only one prime implicant which is covering some min terms which are not covered by other prime implicants. That is nothing but the prime implicant of size 4 here. Only this one is essential. In the previous one, all these are essential. In this one, only this one is essential. Now watch this one. Let's see which one is essential here. One interesting thing is, you might not see it directly, but when you have any bits at the corner, they can be combined, right? So you can combine this one, this one, this one and this one, and you can call it as a prime implicant. One more thing you should be very careful is, when you are having a prime implicant of size 2, you cannot combine this one and this one, or this one and this one, but you can combine this one and this one. If you are getting confused about what can be combined or not, you just always see this. When you are combining two min terms, those two min terms should have only one bit difference, which means only one variable should change in both the min terms. For example, let's write the numbers here to understand. 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0, right? Now what is the number corresponding to this? Row is 1 0 and column is 0 0, right? What is number corresponding to this? Row is 1 0 and column is 1 0. Now check this. Only one bit is changing between these two. I think the third bit. Only the third bit is changing between these two. Therefore, they can be combined to form a implicant of size 2, right? And what about these two? If you look at these two, or let's say I want to compare this one, which means this one, with this one. So what is this row? 0 0. What is the column? 1 0. Now check this. This one and this one, it is not one bit which is changing, it is two bits which are changing, right? So which means the first bit changing and then the third bit changing. Therefore, you cannot combine these two to form a implicant of size 2 or a subcube of size 2, but then you can combine all these 4 and you can form a subcube of size 4, because in all these 4, 2 of them will continuously change and 2 of them will remain constant. Or you just remember this way, you can combine the corner elements to form a prime implicant, but then you cannot combine two elements like this. You can combine two elements like this, but you cannot combine this like this. 4 you can combine and make it a subcube, but you cannot combine these two or these two, but you can combine these two and these two. Just remember that. Yes. Now we got a implicant which is of size 4. Is it prime implicant? Which means, is it the biggest one that cannot be kept in any other one? Yes. This cannot be completely immersed in any other thing. See, when I am saying that it is a prime implicant, it means that that entire thing cannot be a part of one particular subcube, but the entire thing divided into parts can be parts of various particular, which means, see this, here you might say that, this one, the main, the bigger subcube, you might think that this bigger subcube is not a prime implicant because it is a part of other prime implicants, but that is not the definition. The entire thing, if it is covered by one prime implicant or one implicant combinedly, then it cannot be. Okay, see this. What I mean to say is, if I have 1 1 1 1, it is a subcube of 4, it is a prime implicant if it is not present as a part of any other subcube, right? But then if I have this one, this is also implicant, but it cannot be a prime implicant because it is completely covered by one big implicant, right? This is prime, it is not prime, but both are implicants, right? So what is the relationship between implicant and prime implicant? Every prime implicant is a implicant, but every implicant cannot be a prime implicant, which means like this. If this is set of all implicants, then this will be prime implicants. Every prime implicant has to be implicant, but the reverse is not true, right? So what I mean to say is, let us say I have like this, then this is not prime implicant. That one you understood, right? Let us assume that I have this one, the diagram I am explaining. 1 1 1 1, here I have 1, here I have 1, here I have 1, here I have 1. Now this is this, right? Now this is a prime implicant, this is a prime implicant, this is a prime implicant, this is a prime implicant. The reason is they cannot be present or they cannot be immersed completely into other subcube, therefore they are all prime implicants. And moreover, this is also a prime implicant because it cannot be immersed completely into a single subcube, even though it is covered by all the subcubes together. That is not the definition. If it cannot be included in a single big implicant, then it becomes a prime implicant. Got it? So this is a prime implicant, this is a prime implicant, prime implicant, prime implicant, prime implicant. Now these four are essential because they are covering at least one which is not covered by anyone else. But then this one is not essential because it is not covering at least even one which is not covered by others. Got it? Okay. Now let's talk about it. So all these four ones together are going to form a prime implicant. Okay. And now you can combine these two and form a prime implicant, prime implicant, prime implicant, prime implicant. Why are these four prime implicants? Because they four cannot be kept completely inside any other prime implicant, right? Any other implicant. Now what about this? This is essential because this one. This is essential because it is not covered by anyone. This is essential because it is not covered by anyone. This is essential because it is not covered by anyone. This is essential because it is not covered by anyone, right? And what about the bigger one? The bigger one is not essential because it is not covering even one which is not covered by anyone else. Everything that is covered by the bigger one is already covered by all the rest together. Therefore it is not essential. Yeah, this is interesting. See this? This is a prime implicant because it cannot be a part of any implicant. This is a prime implicant, it cannot be part of any other. Prime implicant, prime implicant, prime implicant, prime implicant, prime implicant, prime implicant. All these are prime implicants only. They are not just implicants, they are prime implicants. You cannot immerse anything completely into other thing, right? And there is some specialty about this one. So if you look at any, see this, in this one nothing is essential because no prime implicant is covering even one min term which is not covered by others. If you look at any one, it is actually covered by two prime implicants. Take any one, it is covered by two implicants, right? Therefore there is no prime implicant which is actually covering one which is not covered by anyone else. So every one is covered by at least, here in this case, exactly two implicants, right? Two prime implicants. Therefore there is no essential prime implicant in this. No, nothing is essential, right? Which means it is not a rule that you should take a prime implicant, otherwise you are leaving out one. Even if you leave out a prime implicant, that can be covered by other prime implicants. Therefore nothing is essential. And even the same thing applies here also. See this? Prime implicant, prime implicant, prime implicant, prime implicant, prime, right? Now check this. In here also, every one is covered by two prime implicants. Therefore what can you say? In this also there is no essential prime implicant, right? So these two K maps are also called as cyclic K maps. Cyclic K maps. Why cyclic is every min term is covered by 2 and there is no every prime implicant is of same size, which means 2 2 2 2, and every one is covered by 2 prime implicants, right? And nothing is essential. If that is the case, then we can call it as a cyclic. So there is nothing special about it. Only thing is, you can remember that it is not containing any redundant terms. It is not a completely special K-map. I am saying that if it is not containing any essential, and if all the prime implicants are of same size, and if everyone is covered by at least 2, then it is called cyclic prime implicant. Got it? So now let's see some problems on this. Procedure for obtaining minimal SOP. So I'll tell you the procedure and I'll explain with an example how it works. Maybe by now you must have figured out how to find out the minimal SOP, right? But anyway, it is worth writing down the procedure so that you will not forget it. Before exam, you will again revise it. Determine all the essential prime implicants and include them in the minimal SOP. First step says that you find out all the essential prime implicants and include them in the minimal SOP. What happens if you don't include them? Because if you don't include a essential SOP, right, essential prime implicant, we know that that is the only prime implicant which is covering a min term, and if you don't include it in our expression, we are effectively leaving out one min term uncovered. That should not happen. That is the reason. And the second one is, remove from the list of prime implicants all those which are covered by essential prime implicants, right? Which means now, by including all the essential prime implicants, if a prime implicant is completely covered, which means whatever is covered by that prime implicant is already been covered by all of them. Therefore, it becomes redundant now. It is not going to do any favor for us, right? Anything which is covering a uncovered one is actually required for us. If it is already saying which is already said by everyone else, why do you want to take it? That is why leave it. That is where this minimization is going to, that is how we do minimization. We eliminate all the redundant terms, right? Now, if this set determined in the step 1, which means if you find out all the set of essential prime implicants, if the essential prime implicants itself covers all the min terms of F, which means by taking only the essential prime implicants, if you are able to cover all the min terms, then it is unique minimal expression. Which means by taking only the essential prime implicants, if you are able to cover everything, then nothing is required, and moreover that will be unique. That is minimal as well as that will be unique, right? Because anyway, if you try to form any other minimal expression, you cannot minimize it. The reason is, if you try to delete any of this, because since they are all essential, you are effectively uncovering some of the ones. If you try to delete a literal, you are essentially covering more, right? Therefore, you cannot reduce. Okay, I'll just prove it. Don't worry. Okay, I'll just prove it now. I'm saying that if every, let us say there are like this, AB plus BC plus CA, this is the final minimal expression you got, right? And now you cannot delete any of the product term. The reason is, if you try to delete any of the product term, you are actually uncovering, or you are actually not covering at least one of the min term which is covered by them. And remember, everyone is covering at least one min term which is not covered by others. Therefore, you cannot reduce the number of product terms, nor you cannot reduce the number of literals. If you reduce any literal, what happens is the size of the prime implicant becomes bigger. What happens when you reduce the number of variables? Obviously, the size of the subcube which is represented by AB is going to be doubled, isn't it? Now, whenever you decrease it, so by that you are actually getting more number of ones into the expression which were not there earlier. Therefore, once you have all the products which are essential, then if it is enough to cover everything, that is the minimal expression which is unique. No other expression will be minimal, and this is the minimal expression, right? In case it didn't happen, which means even after selecting or choosing all the essential prime implicants, if it turns out that they are not able to cover all the min terms, then what should you do? You should actually get some other, right? You should actually get some other subcubes which are covering the remaining ones, right? So see this. Otherwise means they are not able to cover everything. Otherwise, select the additional prime implicants so that the function is covered, which means we are going to add additional prime implicants, which means additional subcubes, so that the function is covered completely. Everything has to be covered, and the total number and the size of prime implicants added are minimal. Moreover, when you are adding more prime implicants, you should even see that the total number of prime implicants added and the size of each prime implicant added should be as minimal as possible. If you have a choice, like if you could choose from a set to cover any of the elements, then you please choose a set which will be minimal to cover all of them, first thing, and the elements, the literal should be less. So do you remember the constraint that we are using for minimization? Reduce the number of product terms, and moreover reduce the number of variables in each product term. That should happen. So in this, what is important is, first step is determine the essential prime implicants and include them. So essential prime implicants will always be included in any minimal expression. And next thing is remove all the prime implicants which are covered by prime, which means if they are covering some other thing, then leave it. Next step is, if there are any min terms remaining, then you just take the set and then cover it, and you just take extra cubes, subcubes, and cover it. I'll just take this example and explain you better. It will be easy for you with the example. Even if you didn't understand these points, please make a note of it. After doing lots of examples, these points will be clear for you. Now watch this. What I mean to say is, first you are going to cover everything with prime implicants. Prime implicant, prime implicant, prime implicant, and this is also a prime implicant, and all are prime implicants, which we have already seen. Now what are the essential prime implicants there? The essential prime implicant there is this one, this one, this one, and this one, and the cell containing 4 elements, that is not essential. It is not essential because it is not covering anything which is not covered by others. Everything that this one is covering is already covered by the essential, right? Therefore, what is the minimal expression? Once you pick all the essential prime implicants, there is nothing to be covered by the remaining one. Therefore, your minimal expression will contain only 4 product terms. And it is easy for this example, but for some other examples, just by looking at the table and deriving everything will be somewhat difficult. Therefore, I will tell you one more method called as prime implicant chart. So for now, just solve this one. So what is the minimal expression here? See, the question is 1, 5, 6, 7 and all this, and I have drawn the table, the K map, and now from the K map I am trying to get the minimal expression. So what is the step 1? You take all the essential prime implicants. So what is the essential prime implicant? This one, right? So what is the term representing this essential prime implicant? This one. So just check in these 2 cells what is not changing and you write it, and whatever is changing you can leave it. So in these 2 terms, what is not changing? W is not changing and it is 0, therefore W prime, and Y and Z are not changing and they are 0 and 1, therefore Y prime and Z. So it is W prime, Y prime, Z plus. Now in these 2 terms, in these 2 cells, what is not changing? If you look at it, W and X are not changing, therefore WX, and then in these 2, if you look at it, Y is not changing, therefore Y prime plus. I want to write this one. If you look at this one, W is not changing, therefore W, and then YZ are not changing in this, therefore YZ, and they are ones also, right? And I want to write this min term, this subcube. If you look at it, what is not changing is W and X are not changing, therefore, but then W is 0 and X is 1, therefore W prime X, W prime X. And if you look at these 2, Y is not changing, therefore Y. So by taking all these 4 min terms, it is enough, and we have covered everything. So there is nothing, all the ones have been covered by only these 4 subcubes. Therefore only these products are going to form the minimal expression, and in fact this is the unique minimal expression. You cannot find any other minimal expression which is smaller than this, and moreover this subcube is not required, it is redundant, right? So it is very easy. Coming to this example, you are just able to see this and put it there, but then sometimes the question might be, find out the number of minimal expressions in which in such questions, what happens is all the min terms will not be covered by the essential prime implicants. Then in that case you might have to include some other min terms. So I'll just take an example. I mean, for this one I'll just tell you how to use some other method so that your answer will be, you will be sure that your answer is right. At least I could tell that. Now let us see. This is called prime implicant chart. What are the min terms that you are trying to cover? All the min terms are this: 1, 5, 6, 7, 11, 12, 13 and 15. Is it okay? Now these are all the minterms that I have to cover. So let me just for the sake of correspondence, let me just put the no, I'm not dividing in them anything like this. It will be easy for you to understand which which row and which column are we talking about. Otherwise it will be confusing. And then how many some minterms are there, how many subcubes are there? All these are subcubes, right? So I'm writing all the subcubes. Either you can name the subcubes with A, B, C, D, or you can directly write the subcubes. Anything is fine. So let me write the subcubes since I have already derived them. W prime, Y prime, Z. And what about this subcube? W, X, Y prime. What about this subcube? W, X, Y, W, Y, Z. W, Y, Z, right? And what about this? W prime, X, Y. So all these are actually subcubes, and they are nothing but the implicants. Every subcube is an implicant. Remember, that is why it is also called as implicant, right? Implicant chart. Now you should not just write the essential prime implicants, you should write every implicant. Therefore, I should be writing even this prime implicant. Every prime implicant should be present here, and every minterm should be present here. It is called prime implicant chart because every prime implicant should be here. Now look at this. What is the prime implicant corresponding to this 4 cell? See what is not changing in the rows in W and X. In these two, X is constant. Therefore, X. Right, and in these two, Z is constant, therefore Z. So the minterm corresponding, or the product term corresponding to the subcube, this 4 is XZ, right? Now let me just put a correspondence here so that you will not get confused about what I am covering. Okay, now I want to see what are the minterms which are covered by each cube, each subcube, or each implicant. Now the implicant W prime, Y prime, Z prime, I think that minterm belongs to this, right? W prime, okay, W prime, Y prime, yes, W prime, Y prime, Z, it belongs to. What are the two cells that are covered by this prime, this minterm is 0, 0, 0, 1, which is nothing but 1, and then 0, 1, 0, 1. 0, 1, 0, 1 is nothing but 5. These two are covered. So are you getting this? This minterm, sorry, this subcube is covering these two minterms. That is why I am writing it. The columns are nothing but, in the question they have given all these minterms have to be covered by your function, or this is the function given which we have to minimize it. That is what I am writing here. And then the rows are nothing but all the subcubes that are present here, which are nothing but prime implicants. All the prime implicants are rows. Now what is that I am filling in is, what are the minterms covered by each subcube? That is what I am filling there. And next one is Wxy prime. So if you look at Wxy prime, what is that it is covering? I think Wxy prime is this one, right? So these two. Now it is covering 1100, which is nothing but 12, and this one 1101. 1101 is nothing but 13. Now Wxyz. So Wyz. So Wyz is nothing but, W means 1 and Yz means this. So I am talking about this mint cell, this subcube. This subcube is covering, one is 1111. 1111 is nothing but 15, and the other is this one, right? 1011. 1011 is 8 plus 3, which is 11. So it is covering these two. And next one, W prime xy. W prime xy means this one, right? W prime and then x and then y. W prime xy means this one. Now what is it covering? 0 1 1 1, which means 7, right? And this one is 0 1 1 0, which is 6. Correct? And now the final one, this one, the main one, the bigger one, it is covering, first one is 0 1 0 1. 0 1 0 1 means 5, fine. And then the next one is this one, 0 1 1 1, which means 7. And the next one is this one, okay, 0 1 1 1 is over, and this one is 1 1 0 1. 1 1 0 1 is nothing but 13. Okay, here 1 1 0 1 is 13, and then yeah, this one is 15. 1 1 1 1 is 15, right? Okay, now just find out which are essential. After see, you know already which are essential. From this diagram it is clear, but act as if you don't know which are essential. So as of now I have filled up all the implicants here, and I have filled up all the minterms there, and now I have covered, I just have kept what is covering what. Now act as if you don't know which are essential. Now what is the definition of essential? If a minterm is covered by only one prime implicant, then that will become essential prime implicant, isn't it? Now what does it mean? Go to a minterm, right, and you see if it is covered by more than one. If it is covered by only one, then there will be only one in the column. If you find such a minterm, the corresponding subcube which is covering is essential prime implicant. Okay, let me tell you here. See this. Now go to a minterm 1. Now see in this entire column how many are covering it. It is clear that only one is covering it, which is nothing but this one, isn't it? Therefore this is essential, right? So once you find out any essential, then you are going to include into our final answer. If you are going to include into your final answer, then whatever is covered by this essential are already covered, right? Therefore what are covered by this? 1 and 5 are covered, so I am ticking them. Follow this procedure clearly. Now I have taken one minterm, it could be any minterm, and now I have seen what are all the prime implicants which are going to cover it. But then I found out that there is only one prime implicant which is going to cover it, and remember that there will be at least one prime implicant which is going to cover it. If there is no prime implicant which is going to cover it, that particular cell which is containing 1 will itself become a prime implicant which is covering that, and that will be in the table. Got it? Now in this entire table, in this entire column, there is only one here, which means only one prime implicant is covering it. Therefore that prime implicant will become essential. Therefore it has to be included in our answer. Once you include this in our answer, what are the other what are the other minterms covered by it? 1 and 5. 1 and 5 are going to be covered, right? So 1 and 5 are covered. Similarly, go to the next one. Next one is 6, right? Now look at 6 completely. It is exactly covered once, right? So again, see, you need not worry about 5, because 5 has already been taken care by this essential prime implicant. There is no way you are going to avoid essential prime implicant, and once you have added essential prime implicant, it has already taken care of 5. Therefore you need not take care of 5 again. Now I am talking about the remaining minterms, and I am going to see which is essential. Now 6, look at 6. If you go through the line, 6 is covered by only one prime implicant, which is W prime XY. Therefore it has to be included. If I include this, what is it is covering? It is covering 6 as well as 7. Therefore 6 and 7 are covered. You need not think about them. So our answer is growing like this. It has to be included, and this has to be included, right? And now remaining, take the 11. See this? If I take 11, I see that in this entire column I see only one, which means only one is actually covering it, right? Therefore what is that? W by X. It is covering it. Therefore it has to be included. But if I include it, it will not just cover 11, it will even cover more. So 11 and 15, these two are covered. Now what are remaining? 12 and 13. Now take 12 and go through it. Now if I am going to take it like this, right, you will see that only one minterm is actually covering it, or only one implicant is covering it. What is the implicant covering it? W X Y prime. Therefore include this. If I include this one, then it is going to cover 12 and 13. Now again, in the remaining one, you find out any other minterm. Actually all the minterms have been covered. So if you see that all the minterms are covered, you can stop the procedure. In case if the minterms are not covered, you can keep continuing, right? So in this case, all the minterms are covered only by essential prime implicants. Therefore we get a minimal prime implicant, which is nothing but collection of all these essential. In case even after including all these essential prime implicants, if you get even more minterms, then you should take the remaining prime implicants in order to cover them. Then we are going to get more than one minimal expression depending on what you choose. Okay, I'll take examples and explain you. Maybe I'll just want to warn you one thing. You might feel that this method is big, and you might feel that you could have directly answered it without doing all this. Yes, you are right. You could definitely do it, but then it is wrong from my part if I don't explain you this part, because for some questions it is very important that you know it. Without knowing this, you may not be able to answer all the questions. For some questions you can directly go ahead and solve with this, but for some questions you should definitely be knowing this. right? So I just want to give you everything, all the tools available. It is up to you to use it. So in GATE exam, if you can directly, if you think that you have expertise to directly solve it, go ahead and solve it. But let me warn you, all the questions, they might be difficult to solve using this method directly by looking at it. If you have a lot of practice, you could do it. Otherwise, you please follow this. Even though it is looking as if it is going to take a lot of time, in exam it will not take more than 2 minutes, okay, with practice. Now we have seen what is the minimum sum of products till now. Let's see product of sums also. So how to minimize or how to get the minimal product of sums. Just like the sum of products, we can apply the K-map, everything as same, but then instead of ones there, here we are going to use zeros. Let's see this with two examples. Let us say W of x, W x y z is 5, 6, 9, 10, which means these four are given. And now the thing is, we have to find out both the minimum. Let's go with sum of products first. Let's find sum of products and then product of sums. Okay, whatever is both. I'm going to do both of them. So anything is fine. So since we are going to do both of them, let me put zeros also. So what does zero indicate? Zeros indicate the max terms. Max terms which are present in our expression, and ones indicate the min terms which are present in our expression, right? So when I was talking about the sum of products, I have taken ones and I tried to combine them into subcubes, right? Similarly, when I am talking about the product of sums here, now I have to take the zeros and have to combine them into subcubes. Rules are same. So what are the subcubes you could combine is, it is clear that this is a subcube, right? And then it is clear that it is a subcube, and then clear that it is a subcube, and then this is a subcube, right? So these are all the subcubes which are going to have all zeros there, right? Now for each subcube, we can represent it using a similar to that product of product terms. Here I could represent with a sum term. Why? Because they are all zeros, right? So how to represent it is, see this. Now what are the variables which are constant in this entire subcube is y and z, because w and x are keep on changing, right? So y and z are constant, and if you see that y is 0 and z is 0. Previously when I was talking about the product terms, whenever there is 0 I used to write the complement, whenever there is 1 I used to write the true form. But when I am talking about the sum terms, whenever there is 0 we write the actual true form, whenever there is 1 we complement it. And since here there are zeros, I am going to write the actual terms, which means y plus z is one of the sum term. So y plus z. Okay, one more thing, are all these subcubes essential? See this 0 is covered only by this subcube, therefore it is essential. This 0 is covered only by this subcube, essential. This 0 is covered only by the subcube, essential. This 0 is covered by only by the subcube, essential. All are essential only, right? And now once we find out the essential subcubes, for each subcube I am going to take a sum term. So for this one, the sum term turned out to be y plus z. And what about the sum term for this one, the column, this one? Only w and x are constant and y and z are changing, and here w and x are both 0 and 0. Therefore we have to write the true form, so which is nothing but w plus x. Are you following this? Why am I writing true form is because whenever there is 0 0 I have to take same true form, and since we are talking about sum terms, instead of writing w into x I am going to write w plus x. So these two are over. Now what about this one? See this, only y and z are constant and all the others are changing. Therefore if I take y and z and both are in 1 and 1, therefore I should take complement. So what is it? Y prime plus z prime. And what about this? W and x are constant and all the others are changing. Now if I take w and x and write it, both are 1 and 1, therefore w prime plus x prime. Now one thing you should worry about is, yes, we have included all the essential prime implicants, and in fact every implicant is essential here, therefore everything has to be implemented. So whenever all the prime implicants are turned out to be essential, then we get only one min term, which is unique min term, and we need not worry about anything. Directly write all the min terms and then put them there in the expression, that is over. In case if all of them are not essential, then we have to pick up the essential first, and for the remaining min terms or max terms, we have to pick the other prime implicants, right? Fine. So this is the minimal expression for this, right? And what about the other one? See this? So this is one minimal expression, and the other one is I just want to find out what is the sum of products minimal form. So here, if you look at it, we have only 4 elements, and these elements are not going to form any subcube greater than 1. So every element itself is a prime implicant, and for every element I have to represent a prime implicant. Now check this. For this element I have to represent a prime implicant, which is nothing but, what is the prime implicant? It is the prime implicant as well as essential prime implicant, right? Because there is no one which is going to cover it. So what is the expression for this? 0 1 0 1, which means W prime X Y prime Z. W prime X Y prime Z plus, and everything is essential, that is why I am writing everything, right? And what about this one? W X prime Y prime Z. W X prime Y prime Z plus, what about this one? This particular term, W prime X Y Z prime. W prime X Y Z prime plus, what about this last one? W X prime Y prime Z prime. W X prime Y Z prime, isn't it? W X prime Y Z prime. So this is the sum of products, and this is the product of sums, and you can see that for this particular expression, the number of literals, if you count all of them, 1 2 3 4 5 6 7 8 literals are required in product of sums, minimal product of sums, and here 16 literals are required in minimum sum of products. Does it mean that for all the functions this sum of products is better than product of sums? This product of sums is better than sum of products? It doesn't mean so. See, this is the minimal product of sums, and this is the minimal sum of products, right? Now let's examine if that is true. If it is true that always we get a better product of sums compared to SOP for any function. So let's say the same function complement. So what is complement of a function? Wherever the function is having 1 earlier, if you put 0 there, and wherever the function is having 0 earlier, if you put 1 there, then that is nothing but the complement. So see this, previously in 5 6 9 10 the function was having 1, and now in 5 6 9 10 the function is having 0 currently, right? And therefore all the remainings are obviously, see, whenever you write pi representation and give some values, it means that only for those values it is zeros, and what about the remaining values? They are all ones, they are all min terms, and they are all max terms. So it is as good as writing like this: 1 1 1 1 1 1 1 1 1, like this, right? And now I want to obtain both sum of products and product of sums here. So let us see what is the sum of products expression. So whenever you want to get the sum of products means kind of min terms, therefore you have to take min terms. So we have to, whenever you want SOP, we have to take the min terms and then ones, and then find the subcubes. So if I draw the subcubes, I find out that this is a subcube, this is a prime implicant, this is a prime implicant, this is a prime implicant, right? So I have got 4 prime implicants, and all the 4 prime implicants turned out to be essential, because there is at least one which is not covered by other and which is covered by only every prime implicant, right? So whenever every prime implicant is essential, you need not think about it, write all of them. That is going to be the minimal expression, which is going to be unique. In case if they are not, if there is anything which is not essential, then first you include all the essential prime implicants, and for the remaining min terms you try to cover them with the remaining prime implicants if required, right? So now let's see this. What is the expression for this? For this one, if you look at it, only if you see this entire row, only yz is not changing, and w and x are changing, and even yz is 0 0. Therefore when you are writing it as a product term, whenever there is 0, we have to complement the variable, right? So y prime z prime represents this entire row. And what about this one, this column? Here only wx is not changing and everything is changing. Therefore what can you write it there? W prime x prime plus, look at these two are over, right? Now look at this one. So what is constant? Wx is constant and all others are changing, and wx are 1 and 1. Therefore wx plus, look at this one. In this one only yz are constant and all the other are changing. Therefore we are going to write it as yz. And what about product of sums? Now check this. How many terms are there? There are actually 4 terms, and all these 4 terms cannot join with any other terms, which means the maximum, they are already present as the prime implicant. So the 0 itself is a prime implicant, prime implicant, prime implicant, prime implicant, and in fact there are essential prime implicants also, because that 0 is not going to be covered by anyone else. So how many prime implicants we have? 4 prime implicants, and all the prime implicants are essential, right? And moreover, why are they prime implicant? Because they cannot be part of any bigger subcube, right? So we have 4 prime implicants which turned out to be essential prime implicants. Therefore what is the minimal term? You have to take all the prime implicants here, right? So what are the prime implicant here? For this one it is 0 1 0 1, and you remember this, it is whenever there is 0 I am going to write the sum term, and when you are writing the sum term, if the value is 0 write the complement, write the true form. If the value is 1 write the complement, right? Now this term represents this one. I am talking about this one. This one represents 0 1 0 1, which is nothing but w plus x prime plus yx prime, because x is 1 and y is 0. Therefore y plus z is 1. So z prime product of sums, right? And now I am talking about this one, right? Wx, so w is true and x is 0. Therefore w has to be complemented, x has to be written as it is, and now y and z. So y is 0, therefore y has to be written as it is, and z is 1, therefore z has to be complemented. And this one, if you look at this one, wx yz, w is 0, y is 1, therefore w has to be written as it is, plus x is 1, therefore x has to be complemented, plus z is 1, sorry, y is 1, therefore y has to be complemented, plus z is 0, therefore it is written as it is, multiplied with, that is product, this one, right? It is 1 0, which means w is 1, therefore w has to be complemented, and x has to be written in the true form, plus yz. So y is 1, therefore y has to be complemented, plus z is 0, therefore z is written in true form, right? Now you compare these two terms, right? So if you compare this one and this one, you just complement it, you get that, which means you just take the complement of this expression, you will get this. You can check it. So y plus z is there it is y prime z prime, and w plus x is there it is w prime x prime, and then y prime plus z prime is there it is yz, and then w prime plus x is there is wx. Even this one also, if you can check it, w prime x yz, y prime z. So it is nothing but you just complement it and put the pluses, right? Then you are going to get this. So depending on the function, sometimes POS looks like better and sometimes SOP looks like better. Both are used, right? So it is not that always POS will be easy and then SOP will be having more terms. It is not that. It is not true. Depending on the function, it changes, right? So given any function, it is up to you to use either POS or SOP, depending on the logic you are going to implement in the electronic circuits. We shall see it later, which logic we are going to use. There is something called as product of sums and sum of products, which means AND followed by or followed by AND. We shall see that soon, okay? For now, think about this, both the forms are popular. Now whatever we did till now, that's switching theory, right? Like forming a function and then minimizing it and then finding out the minimal expression, redundant expressions. All these have many applications in various, maybe one of the application or the most popular application for this is logic design. Logic design means how are you going to design the electronic devices, right? Like our CPUs, like computers, CPUs, and all these electronic, like your mobile phones, all this, right? So how are we going to apply this switching theory to the logic design or to the construction of electronic devices, that is called logic design. Okay, see this, the main application of switching theory is in the design of digital circuits. It is also called logic design. And now these circuits are designed using basic elements called as gates. So in order to do this logic design, we are going to talk about some elements called as gates, basic gates, and using them we are going to implement all the functions, right? Any device is generally made of gates only, electronic devices, right? So I'll just tell you what the gates are. You must be knowing about this, but just quickly let's revise what they are. This is a AND gate represented like this. If I have two elements A, B, then it is nothing but A dot B. And this is a OR gate. OR is represented like this. A, B, it is nothing but A plus B. And similarly you have, this is AND only but with a bubble here, right? That is nothing but the NAND. So bubble represents NOT, which means A, B only, NOT, which is also A prime plus B prime, isn't it? So this is called as NAND gate. NAND gate, this you know, right? AND gate, and this is OR gate, and this is NAND gate, and one more popular gate is NOR gate. So similar to the NAND, we have a bubble after the OR, then we are going to get this NOR gate, right? So what is NOR? OR, which is complemented. And similarly we have, using this we can implement many other gates. And yes, one is NOT is already there. So it is NOT is represented like this, which means whatever you give here, that is going to be complemented. And then we have like this, it is exclusive OR, which means if I have A, B, then the output will be A exclusive OR B, right? So exclusive OR, you know that we have already discussed about all this. We discussed about the operations. Now I am showing you the gates. So and exclusive NOR is like this. Now these gates are actually used in the realization. Realization means implementation. So whenever you want to implement any digital logic, this is XNOR. Whenever you want to implement any electronic circuit, then what we do is we find out the function that has to be performed by the electronic circuit. A function is nothing but given the inputs, that one you have already seen it, right? Sigma. So I can represent a function, means the output is represented in terms of the inputs. Now once we have represented output in terms of the inputs, we have to actually go and design the circuit, right? Then there are two things you might have to concentrate on or focus whenever you are designing anything, any electronic device. Mainly two things. One is how fast is the device, the time, and second is how costly it is, right? So now when you are implementing any function using a combination of this, let us assume that your function is maybe A prime B plus AB prime, which is nothing but exclusive OR, and assume that we don't have that logic available, the direct gate available for exclusive OR. Let us say only these three gates are available, AND, OR, and NOT. Now I have to implement this. Then what I do is, this is nothing but sum of products, right? So first I'll try to form A prime B. So B can be given here, and what about A? In order to give A, I'm going to negate it, therefore it is nothing but A prime B. And then in order to create this A, and then I'll be giving B prime here, right? Then it is nothing but A prime B, and it is nothing but AB prime. I'm going to OR them, right? So using this collection of gates, it is called levels. Using these many levels of gates, 1, 2, 3, I'm going to implement any function, right? Like this. This is nothing but A prime B plus AB prime. Therefore, depending on the type of gates you have, you are going to implement any function using those gates like this, right? And now what is the cost and what is the time is A and B are, okay, one more thing, till now we have been talking about A and B, and in minimization and everything we are talking about Boolean expressions or Boolean variables, which means A and B are taking only two values, 0 or 1. It is also called as digital signal. Digital signal means we have only two values, and there is one more signal called as analog signal. Analog means the value of the A and B can be anywhere from, like a wave. So you can think of analog like this. Analog signal will be like this and digital signal will be like this, right? So till now whatever we discussed, they are all variables are all 0 or 1, which means they are nothing but representing the digital input. So one way to construct the electronic devices is, you could think that your inputs are only going to be digital, which means 0 1, or your input are going to be analog. But then in our course, this particular course, it is called digital logic because we have only digital inputs. Okay, therefore A and B are nothing but the signals, and the signals are digital signals, and the signal has to propagate through all the gates to come out. It is like this. You may think of it like this. You have a wire, and on one end of the wire you are going to apply some current, and that current is going to appear on the other end. So the time taken for it to move from here to here is propagation time, right? And now if a signal is here, it has to cross through all these gates to come out of it, right? What if this gates or this function is going to be input to other function? Then the output of this has to cross to all the gates which are there in the other function. Therefore the total time taken will depend on the number of levels we have in our digital circuit. If we have lots of levels and if our input has to pass through all these gates and come out, it is going to be slow, isn't it? That is called as propagation speed. Here I call it as propagation time or propagation speed. Generally, both are used. Let us say propagation time. So we want to minimize the propagation time. How can we minimize the propagation time? By decreasing the number of levels in the circuit. That is first thing. And second thing is the cost. That is main important, right? One thing is your device is very fast, but then how much are you going to pay for it, isn't it? So the second thing is cost. In order to keep the cost low, we have to use as minimum number of gates as possible. You have to keep the gate count very less. So depending on the number of gates that you are using in your electronic device, these electronic devices or these integrations are called with various names. So if you are dealing with some functions where let us say the total number of gates used is less than 10, so like this, you are using only very few, right? Then it is nothing but small scale integration. If it is anywhere from 10 to 100 in your logic, if you are using 10 to 100 gates, then that is called medium scale integration. If you are using anywhere from 100 to 1000 gates in your logic design, then it is called large scale integration. If it is greater than 1000, that is what our current day mobile phones, CPUs, everything is having thousands of gates, right? In fact millions of gates. And if you are having such an implementation, that is called very large scale integration, right? So VLSI is very difficult in the sense you have to integrate lots of gates on one circuit board, and then you have to analyze them, test them. Therefore lot of theory has to be used. Coming to that, switching theory is completely used there. How do you minimize it? How do you test it? How do you see that the function is giving you the right output or not? Lot of things are going to come into picture. But then here in this course, our main intention is to see the basic functionalities only, right? Which means how does a half adder work? How does a multiplexer work? How does a decoder? So I'm going to take small devices, and then I'm going to show you how it works using the combination of these gates. So these basic gates are the basic elements to build the other circuits. Now we shall see other circuits being made like multiplexers, and then the other circuits can be used in the manufacture of other circuits. Okay, so now we are not going to do VLSI. VLSI is very difficult. I'm going to show you only till some extent. Using the basic gates, we are going to devise small devices. We are going to manufacture small devices, and we shall see how many minimum number of gates are required and how many levels are required. All these things we shall analyze. So let's get familiarized with these terminologies. Let's get let's see how these gates when put together are going to work. Let's do some problems on that, which will help you in understanding how the gates are working when they are put together. Okay, and then we shall discuss about the circuits, combinational circuits, right? We shall go slowly. Fine. We know that any function can be minimized to either sum of products or product of sums. For example, if it is sum of products, then how does it look like if you minimize a function? Let us say it is a function of ABCD, and when you minimize it, assume that the sum of products we got is AB plus CD, something like this. Then if you look at this function, it is nothing but ORing of AND terms. So before applying the OR, you are supposed to apply the AND, right? Therefore you use the AND gate and then you AND them and let the output come, right? Let the output come and then you are going to OR them, right? Therefore any function which is in sum of products is easy to represent using AND or realization. It is also called as AND or realization, right? Therefore sum of products, it is easy to realize using AND or, right? And if you have a negative terms here, it is just a simple thing. If you have a prime, then you put a NOT gate here. We are not going to count that NOT gate anyway. So I mean, NOT gate is very simple, there is nothing much in it, so we don't care that much. But then AND OR, this is also called as AND OR. Even if you have a NOT, it is simply AND OR realization. The name is AND OR. And one other way to represent a function is, as you know, product of sums. For example, I can have f of a, b, c, d as product of two sums, a plus b into c plus d, right? Then how can I represent it? See, it is nothing but ANDing of OR terms. So before you put the AND, you are supposed to OR them, right? Therefore the best way to implement is first you OR them. ORing means using the OR gate and let the output come out, both the functions. First you OR them, let the output come out, and now take the output and you apply the AND, right? So these two are the popular methods. One is AND OR, other is, this is also called as OR AND realization, right? So any function can be implemented like this. You take any function, it can be written as sum of terms or product like this. But only thing you should keep in mind here is how many inputs are you going to give to one gate. That is called as fan in. Fan in means how many inputs are going to come. So if you have, let us say here ABC, right? And if you want to realize it in only two levels, so realizing it in two levels is possible only when you have any number of fan in. For example, if I have here A, B, C plus C, D, something like this. In order to implement A, B, C, you have to give the input as C also, right? In this case, we have fan in as 2, right? And if you want to have fan in as 2 only, then maybe you will not be able to implement it in two levels. First thing is you might have to AND AB and then AND the resulting with C. For example, if you have only two levels here, I mean fan is only 2, and if you have three terms A into B into C, then maybe you would like to have a AND gate like this and then BC, right? Or you could either put AB together and then C, or AC together and then B. It is up to you, but anyway what I mean to say is, depending on the fan in of the gates, right, the levels, number of levels are going to depend. But then if you try to increase the fan in of the gates, the cost is going to be increased. See, 2 input AND gate is cheaper than 3 input, and then it is cheaper than 4 input, like that. So if you want to implement it in less number of levels, you need a like this. What I mean to say is, if you don't want to use 2 levels of ANDs, you could have gone for a 3-way, I mean fan in of 3 for AND gate. But the problem is, it is going to be costly when compared to this, right? But if you go with this, it is going to be faster because the number of levels are less. See, the overall time required depends on the number of levels the signal has to pass through. If you are increasing the number of levels, the cost is going to be less, right? But then if you increase number of levels, the cost is going to be less, but then it's going to be slower. But if you increase the fan in, the cost is going to be high, definitely, but then it is going to be faster. So it is up to you to decide about it. And in our most of the examples, we are going to take with only 2 fan in. We suppose that every gate is going to have only 2 inputs. That is why we take the fan in as 2, and every output is going to be 1. So sometimes what you could have is, you can have 2 outputs like this, fan out. So generally most of the circuits will have fan out as 1 only, so don't worry about it. Fan out we don't consider, fan in we are taking it to be 2 unless specified. So if they don't specify anything, you think that fan in is 2. If they specify something, then you think that you have to take that accordingly, and then you have to solve it, right? So anything can be implemented like this. Now let's see. Then let us say I have to implement a function. Then how many gates as a manufacturer I should produce? Let us say I have to implement a function like this: a prime b plus cd, a function like this. Then how many gates are actually needed? One gate is AND gate, two gates of AND are required, and one gate is OR gate. OR gate is required, and other gate is not to negate it, I need the NOT gate, right? These many gates are required in order to implement this function, right? And how many AND gates are required? I think 2, right? And how many OR gates are required? 1. And how many NOT gate is required? 1. Therefore, as a manufacturer, I have to produce, one is AND, other is OR, and other is NOT. How many do I have to produce? Like, should I produce 1000? Is there is a guarantee that everything is going to be used equally? There is no guarantee, right? So sometimes some people will use more AND. If the entire world keeps on using more AND gates than OR gates, then the OR gates will remain at every factory, isn't it? Therefore, maybe using some other way, if I use only one single gate, and if I could implement anything possible, that will be beneficial. The reason is, you keep on producing only that gate, therefore the cost of manufacturing is going to come down, and then you can put them together and you can implement any circuit, right? So I want such a gate which I produce one that should be able to implement everything, right? So just watch this. We know that every function will have a sum of products expression. Therefore every function can be implemented as a AND OR realization. Now let's see, using this AND OR realization, can we convert it into a common gate? Just watch it. Assume that I have 2 gates like this, 3 gates. There is a OR gate here. Now I want to negate it here, output, and negate it here, and before it is given to the next gate, I want to again negate it here and negate it here. Will the function change? It will not change, because see, whatever you negated it, whatever you complemented, again you are complementing back. A complement whole complement is A. Therefore, whatever is the function output here, the same output is going to appear here, and whatever is the output here, the same output will be given to this gate. So putting a bubble here and putting a bubble here does not hurt anything. Everything is going to remain same, right? Now, by using such a thing, what is the advantage we get really? See this. If I have a OR gate to which I am going to negate the inputs and give it, if it is A and if it is B, let's see what is the output. It is A prime plus B prime, right? How can you write it? AB whole prime. Therefore, writing like this is again an AND gate, isn't it? It is not AND, isn't it? It is a NOT gate, right? So I could replace this particular gate with one more NAND gate. So if you are understanding this, what I could do it is, see, I bubbled it here and I bubbled it here, bubbled it here and bubbled it here. Then I got this. Now I am saying that this is simply a NAND gate. So I could have replaced this entire part, including these 2 bubbles also. They will also go into it. Entire part could be replaced with NAND gate, which means I could have written it like this. That's it, right? Therefore, what did you find out? Anything in the world, any function in the world could be now just implemented using one gate, right? Which is nothing but NAND gate. So using NAND gate, you could get NOT also. How can you get a NOT using NAND gate? See this. If you want to negate something, you want A complement, then what you do is simply you give A here and A here. Then what is that you are getting? A complement. Therefore, NOT is also implemented and any function is implemented. If I want to implement A prime B plus BC, then what I do is, first I will complement A like this, and then I will take that input and I will give it to the AND OR realization. That AND OR realization is again realized by NAND realization. Therefore, and or any and or realization can be realized. See, realization is nothing but implementation. Instead of saying implementation in this subject, I will be using the term realization. So realization means you just understand that we are going to implement a function using the gates, that is called realization. And or realization is also called as NAND realization. So what is NAND? Like this, which we have seen here, right? It is NAND realization. So what did you understand now? You need not manufacture AND gate, OR gate and NOT gate, and you need not worry about how many to manufacture. If you are a manufacturer, you manufacture in bulk NAND gates, and using that any function can be implemented. Therefore any circuit designer, if you have to buy some gates from you, you just make them only NAND gates and give them. They can implement anything, right? So why do you think that is working? Because NAND is nothing but, if you look at NAND is a combination of AND gate and NOT gate, and we have already seen that AND and when compared with NOT is a functionally complete set. That is why we wanted the functional complete set there, right? So I mean, even though there is no relationship between this concept and that concept, that is switching theory, which is applied here, there the functionally complete concept is going to be useful here in order to decide about what are the gates which are going to be sufficient to manufacture anything. Therefore, using that theory, we already have shown that using a AND gate and NOT gate, they are functionally complete. Therefore, you could go with just the NAND gate to implement anything. Similarly, the same logic can be applied for OR and realization. If I have OR and realization, what you could have done is, here you could put a bubble and put a bubble and put a bubble. Therefore, the meaning doesn't change. The function is as it is, right? And now if you observe this, only this particular gate, right? So how does it look like? There is a AND gate with this, right? Now what is this? If you give AB, it is going to be A prime dot B prime. Now other way to write it is A plus B whole prime. Therefore, it is going to again act as a NOR gate. So you could have replaced this with a NOR gate, right? Therefore, what did you understand now? Any function can be represented as product of sums, and any product of sums can be implemented as OR AND. Therefore, it can be converted to NOR gate. So anything can be implemented using NOR realization, right? Anything. Now we have just seen that OR AND can be realized with NOR. What if you want to use only as NOT gate? So if I have only NOR gate and if I want to use it as NOT, then simply you give both of the inputs as A. Then what do I get? A plus A whole prime, which is nothing but A prime. Therefore, NOT is possible and any combination of OR AND is possible. So OR AND realization is equivalent to NOR realization, and then AND OR realization is equivalent to NAND realization. Why does this one work? The same reason, because OR and NOT both are functionally complete. These two operations are functionally complete in switching theory. Therefore, these two gates are functionally complete to implement any device in logic design. Understood this? So switching theory is again applied here, right? So one thing I want to tell you is, all the manufacturers in the world, they are now confined themselves to building only NAND gate or NOR gate. So either you can, the reason is simple, either you buy everything NOR gate and write the logic and implement it, or NAND gate and write it and implement it. Both works, right? Now using these building blocks, we are going to design some other devices, and using those devices we are going to design the real-time machines like our computers and all everything, mobile phone, everything will be built from the second level of these machines. Now the main concept is how many NAND gates are required in order to design a circuit. So that these kind of questions will be possible. They'll give you a function and now they'll ask you, if you want to implement it in terms of NAND gates and NOR gates, how many gates you are supposed to use. We want to minimize it as less as possible, right? So why do you want to minimize it is, it is not just the cost. See, recently cost of gates have been fallen down to very less. They are very cheap, right? But then if you keep on using lots of gates, what happened is this circuit will unnecessarily grow in size on which you are going to put the gates, isn't it? So if you want to minimize the circuit size by, small is beautiful, right? So if you want to decrease the size of it, right, then you are going to decrease the number of gates. And moreover, if you have lots of gates, the heat produced will be very much high. So it is not just cost, it is the space also that we want to reduce it. So for any reason, there are lots of reasons. We have to reduce the number of gates to as less as possible. So next question is, instead of talking about how many AND gates are required or how many OR gates are required, they will be interested in asking about how many minimum NAND gates and NOR gates are required. Okay, let's see that. Now, what is the circuit represented by this? I mean, what is the function that this circuit represents? So one thing is, whenever you have NOR gates and NAND gates, it is really difficult to analyze it. So you try to simplify them. The simpler one is AND and OR, right? So now if you look at this level and this level, these two levels are nothing but NAND realization. So you know that NAND realization can be converted to AND OR realization easily. So I am just writing down into AND OR realization. By removing this and removing this, it is nothing but AND. Okay, and now this one could be converted to OR. This is AND OR representation, right? And now let's analyze this, what we get out of it. So here I am going to get P, and here I am going to get, it is a NAND operation, right? PQ whole prime. See, output here, what I get is PQ whole prime, right? And I could write it as P prime plus Q prime, right? Therefore this one is going to get P prime plus Q prime, this one is going to get P prime plus Q prime, and this one is Q. And what is this? It is P concatenated with P prime plus Q prime, and this is Q concatenated with P prime plus Q prime, right? Then what do you get here? P concatenated with P prime is 0 plus P concatenated with Q prime, and here is Q concatenated with P prime plus Q with Q prime. Therefore the final answer here is PQ prime plus QP prime. P Q prime plus P prime Q. Writing like this will be will make some sense there. Now what is that function? It is nothing but exclusive OR. Therefore this entire circuit is going to represent exclusive OR. So remember this question, the minimum number of NAND gates required to perform exclusive OR. See this. So now I am talking about exclusive OR, and exclusive OR is minimum, is implementable in the minimum sense using NAND gate. So just remember it like this, exclusive OR NAND gates. How many? 4. Similarly, I could change the same question into one more question like this. The minimum number of NOR gates required to implement exclusive NOR. So which means, see this, instead of that, if I use the same logic like this, tell me what does this one represent, then you'll understand it. NOR gate, again NOR gate, if I have P and Q here, now what is the output of this? Now again if you look at this, these two levels are NOR, and you know that NOR is close to OR AND, isn't it? Therefore NOR can be converted to OR AND easily. So how? Convert this to OR, convert this to OR, and convert this to AND, OR AND, right? This is nothing but OR AND. And now let's see what is the output represented by this. See, this one is nothing but P, and this one is nothing but Q. And what about this one? P plus Q whole prime. Then you could have written it as P prime Q prime, right? And what about this? P plus P prime Q prime. And what about this? Q plus P prime Q prime. Now what is this? ORing. You can write it as this one as P plus P prime into P plus Q prime, right? And what is P plus P prime? 1, and P plus Q prime will remain there. Therefore here this entire term resolves to P plus Q prime, right? And what about this one? This one, Q plus P prime into Q plus Q prime. So Q plus Q prime, you already know that it is 1, and therefore what is remaining? q plus p prime. So q plus p prime. Now you multiply this and get the 4 terms. See this? It is nothing but pq plus this will lead to 0, p into p prime, and q into q prime will lead to 0, and other is p prime q prime, which is nothing but exclusive NOR, right? So what do you understand from this? In order to implement exclusive NOR, right? So what I need is NOR gates. Number of NOR gates required is 4. So minimum number of NOR gates required for exclusive OR is 4. Sorry, minimum number of NAND gates required for exclusive OR is 4, and the minimum number of NOR gates required for exclusive NOR is 4, right? And what about if I want to implement exclusive OR using NOR gates, like this? Exclusive OR I want to implement as NOR gates. So one thing you should understand here is one interesting thing is, let us say I have pq plus p prime q prime. It is nothing but XNOR, and if I take the complement of it, then what do I get? P prime p, this one, into p prime q prime whole prime, right? Then what is it? P prime plus q prime into p plus q, right? Then what do you get? P into q prime plus p prime into q, which is nothing but exclusive NOR. Therefore, either if I take exclusive OR and negate it, complement it, or I take exclusive NOR and complement it, I can get the other one, right? Therefore, see this. Now so you understood that both are complements of each other. Now if the question is about if I have to implement exclusive OR using NOR gates, then how many NOR gates are required in minimum, right? Then how can you solve it is, instead of implementing exclusive OR, you can implement exclusive NOR directly with 4 gates, and whatever output you get, you can negate it using one more NOR gate. See, using only NOR gates, you can implement this exclusive NOR, and whatever output you got, finally let us say the output is here. Let us say you have written like this, and then like this, NOR gates, and finally you got the output, and output can be again negated using one more NOR gate, right? I can use one NOR gate like this. See this. If I use one NOR gate like this, the output will be negated, right? Then what I do is I construct the exclusive NOR using NOR gates, and whatever answer is, I negate it using one more NOT gate. Therefore 4 is required to construct this one, plus 1 is required to negate it to get this one. Similarly, exclusive NOR can be formed by using NAND gates. How? First you construct exclusive OR by using 4 NAND gates, and then you use one more NAND gate to negate the output. Therefore you need 5 NAND gates, right? So just keep this in mind, it might be asked in gate. Okay, so the number of, because exclusive OR and exclusive NOR are very important gates, and then these can be implemented using these gates, right? So just remember it, write it somewhere and remember it. What does this represent, this circuit? If you watch it, we have already seen half of it, right? This entire part is going to represent, or F1 is going to represent, see, 2 inputs are there and 2 outputs are there, F1 and F2, and if you can watch it, F1 is directly representing the exclusive OR. Therefore F1 is P exclusive OR Q, that we have already seen it. Sorry, F1 is P exclusive OR Q, and what about F2? So F2 is actually this part. At this point it is P, this point it is PQ whole prime, right? Why? Because it is NAND gate, therefore and then NOT. So PQ whole prime, and now this is going to be taken and given to this gate, therefore it is again a NOT gate. So PQ whole complement, again complement, therefore F2 is nothing but PQ, right? So now what does these two collectively implement? So if this is the circuit which you have built, which is going to take 2 inputs, and I don't know what is present inside, and is going to give me 2 outputs. You tell me what is the behavior of it, which means how is it behaving, and what is the use of this. So if you watch it, I could, let's see all the combinations. P, Q, F1 is nothing but exclusive OR, and F2 is nothing but simply ANDing, right? 0 0 0 1 1 0 1 1, and what is exclusive OR? Modulo 2 sum, which means 0 1 1 0. And what about F2? Simply adding 0 0 0 1, right? So if you watch it, it is nothing but a half adder. What is half adder? Is adding 2 bits. If I add 0 and 0, the answer is 0. If I add 0 with 1, see, adding is different and adding is different. I am talking about add, and this is going to act as half adder. So what is half adder? Is it will add only 2 bits, and what is full adder? Is it will add full adder. It will add 3 bits, right? So if I want to add 2 bits A, B, then I use half adder. If I want to add 3 bits A, B, C, then I use full adder. Now here it is going to add P and Q, taking each one as a number. 0 plus 0 is, plus means it is not OR, it is AND. So 0 plus 0 is 0 and then 0. And 0 plus 1 is, answer is 1, therefore 1. And 1 plus 0 is, answer is 1, therefore 1. But 1 plus 1 is 2, which is nothing but 1 0. Therefore you are going to write this sum as 0 and carry as 1. So in fact it is acting as the sum and it is acting as the carry, right? So what is sum? Sum is when both of them are 1 and 1, then only we are going to get the carry as 1. That is why it is implemented using AND gate. And what is sum? Sum is nothing but when there are either odd number of ones or odd number of zeros, then we are going to get 1. Or if it is an odd number, the remainder is going to be 1, right? So 0 1 is going to add up to 1, and 1 0 is going to add up to 1, and 1 1 is going to add up to 2. Therefore 1 0 is 2 and 0 0 is going to add up to 0. Got it? So now it is nothing but the half adder. Now this is half adder. So instead of having the connection here, so from here, if I take this connection from this point and if I connect it, tell me what does this F1 and F2 represent? You know already that F1 is same, which is exclusive OR. Let's see what does F2 represent. So first one is, this one is NAND, right? So that is fine. NAND, P and this, and then this one is going to be Q. So one input is P Q prime. I'll write it as P prime plus Q prime. See, PQ whole prime is P prime plus Q prime, and now the other one is Q, and now I have to do the NANDing, right? So what is this? ANDing followed by complementing. So P prime plus Q prime ANDed with Q followed by complementing. Then what do I get? P prime Q whole complement, and this is the output here. So it is P prime Q whole complement is present here, right? And now this one will be given to this. It is nothing but again complementing, which means the final F2 is complement of this. So which is nothing but P prime Q. So F2 is P prime Q. Now let's see what does the F2 in this function represent. P prime Q. See, P prime Q means like this. So P prime Q is 0 and P prime Q is 1. P prime Q is 0. P prime Q is 0, right? So only for this combination we got 1, and for all the other combinations we got 0, right? So if you observe it, it is a kind of half adder. It is a half adder, not kind of, it is definitely half adder. It is definitely, sorry, half subtractor. Sorry about that. Half subtractor. So what is half subtractor is, we are going to subtract one bit from other bit, or we are performing subtraction on only 2 bits. What is half adder? We are performing addition on 2 bits. What is full adder? On 3 bits. What is full subtractor? Okay, there is nothing like that. Now we are going to subtract from this one, one from other. See this, 0 minus 0 is 0, 0 minus 1, that is where the problem is. From 0 you cannot subtract 1 unless you borrow a 1. Therefore it is going to act as a borrow, right? So we are going to borrow 1, which means, see this, from 0 I cannot subtract 1, therefore I am borrowing a 1. So when I borrow 1, this entire number becomes 2, and now 2 minus 1 becomes 1. That is why the answer is 1 and we have borrowed 1. That is the reason, that is meaning of it. So observe this carefully. See, from 0 if I subtract 0, the answer is 0 and no carry is required. From 0 if I subtract 1, okay, leave it. Now let's see this one. From 1 if I subtract 0, the answer is 0. The answer is 1 and no borrow is required. From 1 if I subtract 1, Answer is 0, no bar is required. But only exception is from 0 when I try to subtract 1, then how are you going to do? Borrow a 1, therefore the entire number becomes 2. Now 2 minus 1 becomes 1. Got it? So that is why we needed a borrow of 1, right? So from 0 when you subtract 1, the answer is 1, provided that we have a borrow of 1. So it is nothing but half subtractor, right? So now we have seen what is a half subtractor and what is a half adder, and using the exclusive OR circuit only, we didn't do anything much. Using the exclusive OR circuit, I just modified few things and I got it, right? Okay. See this? It is again multi-input, multi-output function. Let us say P and Q are the inputs and this is circuit given. Now what can you say about it? First of all, it is very clear that these are all like NOR gates, right? So NOR gates, when they are kept like this, I already told you that this F2, at least F2 you should be knowing by now. We have seen the examples, right? F2 is nothing but this exclusive NOR. So what is it? P prime Q prime plus PQ, right? So F2 is definitely exclusive NOR. If you have any doubt, you please go back to the exclusive NOR and exclusive OR operations and check it. I implemented it previously. And now I want to find out what F1 is, right? So how to find out what F1 is? See this? Now output of this gate is given to this one, and then this P is given to here. P is straightforward, and output of this gate is given here, and now there is nothing but NOR of these two. Now what will be the output of this? NOR of these two, right? So which is nothing but P plus Q whole prime. So here it is nothing but P plus Q whole prime, which will be equal to P prime Q prime. Therefore here the input given is P prime Q prime. Therefore the output will be P plus P prime Q prime because of this OR complemented. Now what is that? If you check this, it is nothing but see P plus P prime, which is 1 into P plus Q prime. So it is P plus Q prime whole prime, which is nothing but P prime Q, right? So F1 is P prime Q. Then what is F2? Sorry, F3. F3 is, check this, again here Q is going to come, and this one is same P prime Q prime, and this is NOR of this. So it is nothing but Q plus P prime Q prime whole complement. Then what is it? Q plus P prime into Q plus Q prime. You know that Q plus Q prime is already 1. Then what is remaining? Q plus P prime whole prime. Then what will this be? P Q prime, right? So one is P prime Q, other is P Q prime, and F2 is this. Now let's see what does these three combinedly signify. If I have a circuit like this which is having 2 inputs and 3 outputs, what does each one of them signify, or what does they collectively signify? Now P Q, actually in the title of the video I might have written it as the name of it, therefore there will be no suspense, right? Okay, watch it. 0 0 0 1 1 0 1 1, and F1 is exclusive. F1 is nothing but these two are exclusive NOR. So what is exclusive NOR? This is 1, this is 0, this is 0, this is 1. That is exclusive NOR. And other one is F2. So this is F2. Sorry, this is F2. And what about F1? If you look at F1, F1 is P prime Q. So P prime Q is nothing but 0 here, 1 here, 0 here, 0 here, right? And F2 is F3, and F3 is PQ prime, right? So what is PQ prime? 0 here, 0 here, 1 here, and 0 here, right? Now if you compare these two, so F2 signifies if P equal to Q or not. Whenever P equal to Q, it is going to say yes, both are equal. And F1 signifies P is less than Q, right? So whenever P is less than Q, F1 is going to say it is less than. And F3 signifies P is greater than Q. So P is greater than Q. So these three combinedly are going to say whether both are equal or not, and then whether both are equal or not, which one is greater, right? So let us say you have given some input as 0 0. Then out of these three, there is only one, and one more thing, these are all the mutual exclusive. Check this. Mutual exclusive means if one of the function is 1, other function will be 0. So if you give 0 0 as input, output will be 1, which is saying that the output is here. In this case, the inputs are both are equal. When you give 0 1, only f1 will be 1, which means that p is less than q. Like that we can find it out, right? Therefore it is a kind of comparator, right? It is going to compare the bits and say which one is greater and are they equal, which one is lesser, like that. So it is a comparator. Now watch it. Multiplexer. A multiplexer is a electronic switch that connects one out of n inputs to output, which means if you have you can visualize it like this. I'll have many inputs and now it is a kind of electronic switch. See, now let us say it is output and they're all inputs. I1, input 1, input 2, input 3, input 4, right? Now what will output generate? If you take this switch and connect it, touch it to this, if you touch it like this, then output will be I1. In case if you touch it to this one, output will be I2. Touch it to this one, output will be I3, like that, right? So whatever you touch this switch, the output is going to be that. That is why it is an electronic switch that connects one out of one output out of n two outputs. So if you have n inputs, you are going to get one output. Second point is, it cannot change the logical level of the input. It only provides the connection between input and output. So if let us say this is 0, this is 1, this is 0, this is 1, right? Now if you connect this output to I1, then the output produced will be 0. If you connect it to I2, output produced will be 1, which means whatever is the value given to input, only that output will be produced without any change. So it is not like any indicator. It is not indicating anything. There are indicators, means if some event happens, then it is going to output as 1, show output as 1, indicating that the event has happened. But here the multiplexer is simply going to take a input and just giving it at the output. So whatever you give in the input, that is going to be shown as the output. It is not going to change anything, right? And next one is, it is functionally complete. That is, all Boolean functions can be realized with only multiplexer without using any gates. So it means that if you want to implement any circuit, you have to buy only multiplexer. So using multiplexer, it is as good as you can implement anything. Functionally completeness means you will be able to implement and you will be able to implement or, you will be able to implement not. In fact, any function can be implemented with this. If you can implement those three, and or not. If you can implement this, you can implement anything, right? So I'll show you how does this multiplexer look like and what is it exactly. So the block diagram of the multiplexer looks like this. Let us say it is a 4x1 multiplexer. So what is 4x1 is, you have 4 inputs and 1 output. Now you need to choose any one of this input to be shown at the output. Let us say input is I1, I2, I3, I4, and you can choose any one of them so that it will be shown at the output, and output is going to be any one of this. That is why it is called 4x1, right? And now if I have to choose 1 out of 4, then how many bits are needed to represent these 4? 2 bits, isn't it? If I have to choose 1 out of 4, if I have to select one of them, then how many bits should I choose to name them or to represent them or to get them? 2 bits. If I have 2 bits, 0 0 0 1 1 0 1 1, I can get 4 combinations, and I can use each combination to represent one of the inputs, so that I can choose it and show it at the output, which means I could have 2 select lines, S1 and S0, so that these 2 select lines will decide what is the input that is connected to the output. In case if the select line is 0 0, it means that the output has to be, let us write them as I0, I1, I2, so that it will be consistent with numbering. I0, I1, I2, I3, right? If the select lines are given 0 0, then the output is going to be I0. So whatever is in the I0, it will be shown out. If the select lines are given as 0 1, then the output is going to be I1. If it is given as 1 0, then the output is going to be I2. If it is given as 1 1, then the output is going to be I3, right? So depending on the select lines, you are going to choose you are going to get the output. That is why we need 2 select lines. Got it? See, why do we need 2 select lines is, since we have to choose among 4, one of them to connect it. Therefore, depending on this one will get connected. In case if it is a 2 power n by 1 multiplexer, what does it mean? The inputs are 2 power n lines and we have to select one of them and then give it to the output. Then how many bits are required to choose one of 2 power n combinations? N bits, right? Therefore this 2 power n, this n represents the number of select lines, and the multiplexer is going to be represented like this, right? Now this one is called characteristic table, which means what is the output in terms of the input. Actually what I should have written is, okay, see, this is why it is called characteristic equation is it actually behaves the way this table is shown. Now if we want to write output in terms of the equation, not in terms of the table, it is called characteristic table, right? Maybe you can write it down, characteristic table. Now I want to see how does the equation look like, which means if this is the characteristic table, how does the characteristic equation look like? I want to write it in terms of the equation. Watch it. 0 equal to, sorry, this is output, right? So instead of writing this as 0 or O, let's write it as F. Now output F equal to, when these two are 0 0, then the output is going to be I naught. Therefore you should say that output is completely going to depend on I naught, right? So what can you say? When S naught S1, if these are 0 0, then the output is going to be I naught. So it is one way of saying it. Why? Because output will be equal to I naught only when these two are 0 0. I'll tell you, I'll just write it down and I'll tell you. See this? And the next one is, if the select lines are 0 1, which means this is 0, this is 1, then the output is going to be I1. If the select lines are 1 0, which means like this, then the output is going to be I2. If the select lines are 1 1, which means S1 S0, then the output is going to be I3, right? So that is how we get the output. Now how is this equation justifying this table, or how does it behave? Is if you have any doubt, you can give this 0 0 to the select lines. If S1 S2 equal to 0 0, just check what is happening. If S1 S2 equal to 0 0, this entire thing becomes 1, right? And if this becomes 0 0, this entire thing becomes 0, and this entire thing becomes 0, and this entire thing becomes 0, right? So finally what did you get? So F1 equal to I naught, right? Similarly, if you give S1 S2 as any other combination, let us say 1 0, then you can check it out. Then only thing which will be selected is I1, right? Therefore F equal to I1. So depending on this S1 S2, one of the input is chosen, selected, and is shown at the output. That is why these are also called as select lines. So these two are called as select lines, right? And this is called as inputs, and this is output, right? So now if I have 2 power n by 1 multiplexer, it means that the input is 2 power n and the select lines are n always, right? So now how to realize it? So what is realization? Realization is nothing but the implementation. So it is if you look at it, it is like sum of products, isn't it? And what are the product terms? Each one is a product term. Now you can represent this sum of product terms using two-level realization. You already know that, right? So it is nothing but AND OR realization or NAND realization. Let us see AND OR realization to implement this. I'm talking about AND OR realization, okay? So now how many terms are there? 4 terms. Therefore how many AND gates do I need? 4 AND gates. Let me do it here. I have 4 terms, therefore 4 AND gates. Right? And now for one of the AND gate, it is responsible to take the input from I naught and then it is going to give it to output, and other AND gate is going to take the input from I1 and giving to output, and other one is taking I2 and the other one is taking I3, right? So this is the responsibility of each one. This one is responsible for I1. Now when do you think that if I have other inputs here, when do you think that this signal will cross the AND gate? Always a signal will cross the AND gate if all the other signals are 1. Otherwise this signal will not cross the AND gate. If any of the other signal is going to be 0, then it will never cross the AND gate, right? So now output has to be either I0 or I1 or I2 or I3. Output has to be one of them, right? Therefore it is AND or realization. Now how are you going to decide which one is going to come out? That depends on what is the select line you are giving it, isn't it? So I am going to use something called as select lines, as I said before, and now I am going to provide that select lines here, right? So let me say select lines are like this, right? So two select lines are, let me say, by convention we always write select lines below the multiplexer. So just to follow that convention, I am writing it here. Hope it is visible to you. S1, S0. I could have written it even here. So it means that this signal is propagating like this. Now, when are you going to select this I0 as the output? Only when these two are 0, 0, right? So when S0 and S1 are 0, 0, you are going to select this output as this I0 as output. Then what should happen is, whenever these two are 0, 0, this gate should get from here 1, 1, then only this one can come out, right? Therefore I am going to put a bubble. Bubble is nothing but negating. So understand this. Whenever the input is 0, 0, this entire lines will contain 0, 0, and now since I negate it, these two will contain 1, 1. Therefore whenever all the outputs, all the other inputs are 1, 1, then the output of this AND gate will depend on I0. So here I get I0. Whenever I give 0, 0 here, see, whenever I give 0, 0 here, then these two will give 1, 1. Therefore the output will be I0. That is how we get it. Understood that? Similarly, now we want the output to be I1 outside. I1 should travel outside. Therefore I1, if it has to come, then these two should produce 1 and 1 here, right? Now when are you going to select I1? I1 is selected whenever S0 is 1, which means this one is 1 directly, and S1 is 0. So that is why the reason is, if it is 0 here, S1 is 0, then it is going to be 1, and if it is 1 here, it is going to be 1, which means when it is 0, 1, then definitely these two are 1, 1, and the output selected will be I1, and the output that will be coming out will be I1. That is the reason, right? So similarly you can take the other one also, right? So what is it? The other one are 1, 0, 1, 0, and the other one is 1, 1, 1, 1. Got it? So that is how we can implement it. So this is the realization of it. This is entirely the multiplexer. So what is the, check it. So multiplexer is going to take 4 I0, I1, I2, I3 as input, and along with that it is going to have two select lines and is going to produce one output, and that output is equal to that equation, right? You can check this. And don't worry, I have written the lines to be overlapping. It doesn't mean that the signal will get interfered. You can just use the meaning of it to derive it. Now let's see how to implement various functions using this, right? So if you have understood this, I'll just show you. Next time I'm not going to use this diagram. From now on I'm going to use the block diagram. So it means that internally there is AND OR represented, but I'm going to use the block diagram like this. 4 by 1 means 4 inputs and 1 output and 2 select lines. From now on 4 by 1 will be represented by block diagram, or anything will be represented by block diagram only, and on this block diagram we shall solve the problems. How is it functionally complete and what is the meaning of each one, okay? Now let's see how multiplexer is functionally complete. When can you say a set of operations or anything is functionally complete? If it could derive some set of operations which are already known to be functionally complete, right? So what are the set of operations which are already known to be functionally complete? If I have and if I have and not, if I can derive these three by using any set of operations, then those set of operations are called functionally complete. Or even a smaller set is and not, or and not. If you can derive any of these three or any of these two, you can say that it is functionally complete. Now let's take a small multiplexer and show and see how it is implemented. Let us say the multiplexer is 2 by 1 multiplexer, okay, and these are the inputs and this is the select line. Now I want to find out if it is capable of implementing NOT first, which means if I give a variable x, right, the output should be x complement. So if I give x here, output should be x complement. So let's write the characteristic equation for this. What is the characteristic equation? Output, this f output is equal to select line when it is 0. So let us say this is I naught. So select line when it is 0, which means x prime into I naught plus x into I1. So try to understand this. It is simple. See, whenever this one is 0, what should be selected? What should be sent to the output? I naught. Whenever this one is 1, x is 1, what should be sent to the output? I1. That is how I got it. Now, in terms of these, I want to see what should I be giving to I1 and I naught so that I'll get x prime. If it is 0, if it is 1, it is 1 and it is 0, right? Then how can you write this one? Now you can write it as x prime is, see, x prime is, it is nothing but x prime into 1 plus x into 0. I could write it like this, right? See, it's nothing, simple. I just written x prime equal to x prime, right? And then I wanted to write in terms of x also, therefore I am writing like this. So what did you understand? If in place of I naught, if I give it 1, and if in place of I1, if I give it 0, then which means here 1 and here 0, then it is going to act as the NOT gate, right? So I got NOT. Now what I wanted is, so using a 2 by 1 multiplexer, we are able to get NOT. So let us assume that NOT is also available for us. By using a 2 by 1 multiplexer, I can get it. So using NOT and the multiplexer, now I should be able to get and or any one is enough, right? So assume that I have two variables here. Assume that I have two variables, a and b. Now I want to get the output AB represented by this, provided that I have even NOT gate available for me. Then 0 0 0 1 1 0 1 1. Then what is AND? 0 0 0 1, right? Then how can you write AND? So AB, this is the function I wanted to implement. Let us call it f. The function f is equal to, see, a prime b prime is 0, or let me write it like this. Okay, so first decide about what we are going to give to the select line. Let us say I want to give b to the select line and I want to decide upon what should be given to I0 and I1. So first let us write what is the characteristic equation for f. So f is, when it is b prime, then output is I0, and when it is b, the output is I1, right? Then what is AND? AND is nothing but whatever what I wanted to implement is the function AND is nothing but a into b, right? Now what you can write it like this, that equal to b into a, which means I came to know what should be given to I1, but then I don't know what to be given to b prime, right? So I don't have the term b prime, therefore I am writing it as b prime into 0. See, why am I writing like this? I am expanding it like this so that I could get into this form, and then corresponding terms are going to be I0 and I1. That is why I am writing like this. So even AB is like this. I have expanded it like this so that now you can clearly see that I0 equal to 0 and I1 equal to A. So if I0 equal to 0 and I1 equal to A, definitely the output is going to be AB. So now using the single 2 by 1 multiplexer, I am able to find out the AND. Now you can even find out OR also, right? So how can you get OR? See this? You can write OR like this, A plus B. Now in terms of the equation, if you have to get this, where is it? Yes, in terms of the equation you have to get this, it is better you go with the table. A B 0 0 0 1 1 0 1 1 A plus B. Then what is it? 0 1 1 1. Then how can you write A plus B? A plus B equal to, you can check this one. See, this one is A prime B plus, isn't it, plus AB prime plus AB, right? And now you have to pull out as common B prime and B, so that you can find out what is I0 and I1. So if you pull out B prime, so what do you get? If I pull out B prime, I get A, and if I pull out B, I get A plus A prime, which is nothing but 1, right? Therefore, if you apply A to I0, check this. If I apply to I0 the value A, and if I apply to I1 the value 1, right, it is going to act as OR gate, isn't it? Here if I apply this, and here if I apply this, it is going to act as OR gate. So I got AND I got OR, as well as I got NOT using a multiplexer, nothing else, right? Therefore multiplexer is a functionally complete device. It can be used to implement any functions. Now we have even seen the implementation of the functions also, right? Now I want to put a on-off switch to the device, multiplexer. On-off switch means whenever I switch it on, it should work like exactly like multiplexer, and if I switch it off, whatever inputs I give, it should not produce any output. I just want to put a on-off switch, right? So how can I put it is, see this. For that we should understand the realization of multiplexer. How are you going to realize it? Using 4 AND gates. I am talking about a 4x1 multiplexer. There are the 4 AND gates to which I0 is given, I1 is given, I2 is given, I3 is given, and there are 2 select lines. Right, and now let's see how to implement it. This is I0, I1, I2, I3. So assume that this is S1 and S0. Then how are you going to put this? 0, 0 is this, and 0, 1 is I1, and 1, 0 is I2, 1, 1 is I3, right? So 0 means the bubble means complementing. That one you know already. Now what I want to do is, all of them should produce some output, which means whenever I give some select line and then give some inputs here, it should work only when I switch it on. If I turn it off, it should not work. Then what I do is, to turn off all the AND gates, I am going to give one more input. To all the AND gates commonly I am going to give one more input. So I call it as E, enable input. So it is called as enable input. So what does enable input mean? Whenever you enable it, then only you are going to see the input, then only you should give the input and see the output, right? That is also called as enable input switch, right? Then how am I going to, how is it going to work is, whenever E equal to 0, then all the AND gates are going to get one of the inputs as out 0, then definitely the output produced will be 0, right? And whenever E equal to 1, then only it will take, every AND gate will react to the inputs as well as select lines and give the output. Therefore it is acting as a switch. Whenever E equal to 0, if you switch it off, then nothing will be produced in the output, it will always be 0. Whenever E equal to 1, then only the multiplexer will react to the inputs and it will show you the output, right? Now how does the output look like in terms of E? So does anything change? So F equal to, previously what is F? I0 will be selected when it is 0, 0, S1, S0 when it is 0, 0, or I1 will be selected when it was 1, 0, I2 was selected when it is 0, 1, and I3 will be selected, I3 was selected when it is 1, 1, right? Okay, let me put S1, S1. Fine. This is the previous output. Now along with E, everything will work only when E equal to 1. That is why I am putting it here, right? Therefore enable input, enable is going to work as to the entire function you multiply with this, so that Whenever e equal to 1, the function will be acting as multiplexer. Whenever e equal to 0, the function will be acting as 0, which means it is switched off. Now based on this enable, so what we could do is we could actually connect one variable here, other variable here, and we could put one more variable here. It doesn't mean that we are implementing 3 variable function, but then there could be some questions on that, saying that if enable input is given so and so input, then what is the output? Some kind of questions will be like this. I'll just take some questions and explain you now. Now a 4x1 multiplexer is given and they are asking what is the minimized value of the function represented by this. So first of all, you should guess what the function is and then you should minimize it. So whenever such a question is given to which inputs are given and here, then what is the best way to do it is always write the characteristic equation, and then in that equation you are going to substitute all the variables. That is the best way to do and the only way to get the correct answer. Maybe you could apply some shortcuts, but I really don't suggest that here. So you better write down the characteristic equations and then substitute it. It will not take a lot of time. Okay. So what is the characteristic equation for this? Just see. Moreover, enable input is also given. Just keep that in mind. So characteristic equation, you could write it as like this. So f is, one is in terms of S1 S0, I0 S1 S0 plus I1 0 1 plus I2 1 0 plus I3 1 1, right? So this is the output, and now once you understand this, enable is also there, therefore E has to be there. So once you understand how to write the characteristic output, then you can just take the variables which are given to each one and you substitute it here. Then it is very straightforward, right? Now what is the input given to E? It is taking Z prime, therefore it is Z prime in place of E. And what about I0? I0 is X, right? And what about this S1? This S1 and S0. So S1 is, it helps if I write it here directly. So S1 is Z, and S0 is Z, and S1 is, it is coming from here. So which is nothing but Y prime, right? See, S1 is coming from here. This is Y prime, and therefore S1 is Y prime. And what about enable input? Enable is, it is coming from here, Z prime. E is Z prime. And what about I? I is again Y prime, I3. And what about I2? I2 is Y. I1 is X. And I1 is X. So I just want to substitute all these values here and then see what the values are. So what is it? I0 is X. And then S1, S0 are, actually S1 is Y prime. And again prime is Y. And Z is S0 is Z, and it is S0 prime, therefore this one, plus I1. What is I1? X. And what is S1 prime? S1 prime is again Y. And what is S0? S0 is Z, plus what is I2? Y. What is S1? Y prime. See, this is I2 is Y, and S1 is Y prime, therefore you need not think about anything. This one could just simply be 0. Y concatenated with Y ANDed with Y prime is 0. And plus I3. What is I3? Y prime. And what is S1? Y prime. And what is S0? Z. Got it? So these are all the combinations we have, right? So these are the 4 terms we have. Then just try to minimize it. Now look at these 2 terms. If you could directly minimize it, just try it. Why not? Now it is both the terms are containing xy and z plus z prime. Therefore z plus z prime will go to 1. So what will remain? It is z prime into xy plus, here it is y prime z. Now you try to multiply over it. Now z into z prime will become 0, right? So what will be remaining? X, y, z prime. So this is the function represented by this. Got it? See, and one more interesting question is, sometimes Some functions will be constant functions like this. If I have like this, if all the inputs are given as 1, then what will be output? Output will always be 1, right? Or if all the inputs are given as a, then what will be output? Output will always be a. These are called constant functions. They can be implemented by multiplexers as well. Okay. So depending on the input, it is going to change. So one thing you should understand here is it really implementing all the 3 variable functions? Since we are giving, we are having enable doesn't really provide us with all the minterms possible. Enable is just going to be helpful in order to implement some functions, which means we are not going to make use of enable in any function design as it is. Generally enable is a on off switch. So since this one is connected, I am just finding out what value it could represent. Okay, generally we don't make use of enable in the functional implements. So since we want to understand how it is working, we have taken this example. It doesn't mean that in our real world we are going to use the enable also in the function implementation. It is a kind of on off switch. Okay, fine. Anyway, this is the answer. Now the question is, we have to implement this function, and this implementation should be done in such a way that, okay, the question is given as implement it by a 4x1 multiplexer in such a way that in one question S1 is B and S0 equal to C, and in other case S1 equal to C and S1 equal to B. So depending on what you give to the select lines, the input lines will vary, which means sometimes input lines might change. So let's see how to implement it. The function is that one 2, 3, 5, 6, 7, and the select lines are going to be B and C. So let's see how to do that. So the function is one term is 2. 2 means A prime B C prime plus 3. 3 means A prime B C plus 5. 5 means A B prime C plus 6. A B C prime plus 7, which means A B C, right? So A prime B C, yes, it is 2, 3 and 5 and 6 and 7. And now what we are supposed to see is select lines should be taken as B and C, right? So if I take out select lines as B and C, these are all the select lines, right? There should be all the combinations. One is, I'll pull out what are all the combinations where B prime C prime is there in the term. Therefore they correspond to 0 0, right? So let's see what are all the terms which are having B prime C prime. There is no term, therefore I am going to write it as 0. Plus I am going to pull out B prime C. What are all the terms having B prime C? So these are the two terms having B prime C, and how is it? How the two terms are having the same one? 5 and then 6. Okay, it is not B prime C. It is BC prime. Yeah, B prime C is also not there. B prime C. Yeah, it is here. Only one term is there. Okay, let it be A. This is B prime C plus BC prime. Now find out BC prime. See, BC prime is in two places, right? These two, and one is having A prime and other is having A. So you could add A plus A prime, then you are going to get 1. So here you are going to get 1, and then BC prime plus BC. For BC we are going to get A, right? Now check this. So how to implement this which one is I0, I1, I2, I3? That actually depends on what are the select lines, right? Now assume that select lines S1 equal to B and S0 equal to C, right? If this is the select lines, then this S0 S1, S0 S1, S0 S1, right? So if I put S1 S0 here, then it is going to be 0, therefore it is I0. In that case it is I0. For this case I0 is nothing but 0 because of this, right? And what about 0 1? So 0 1 means 1, right? 0 1 is nothing but B prime C. B prime C is here, therefore I1 is going to be A, right? And what about 1 0? 1 0 is here, right? So what is the input? 1, therefore 1. So I2 equal to 1. And then 1 1. 1 1 is here, therefore what is it? I3. I3 equal to A. These are the inputs whenever S1 equal to B and S0 equal to C. Let's see the other case where let's write it here, S1 equal to C and S0 equal to B. In this case, if I have 0 0, which means B prime C prime again, then what is I0? For B prime C prime it is 0, right? And in case if I have 1 0, or let us say 0 1, so 0 1 means C prime B. See here, C prime B corresponds to I1, which means C prime B corresponds to I1, therefore here I1 becomes 1, right? That is the difference, isn't it? See, now what is I1? I1 is generally when this one is 0 and this one is 1, right? Which means you have to take prime to S1 and leave S0 as true. So S1 is C, therefore C prime B. That is why C prime B is I1. Similarly, what is I2? I2 is 1 0, right? So 1 0 means C B prime. C B prime. This is I2. So I2 is A. So that is what I am talking about. See this? Now the inputs are going to change depending on what you are going to give to the select lines. If the select lines are different, if you exchange the select lines, sometimes input might change. Input might have to be changed, right? So if these two are symmetrical, which means if for this value the whatever is given here and whatever is these two are equal, then it is okay. I mean, whether you give to this combination or this combination, both are going to give the same answer. But then in some of the functions, the answers might be different. Now see about I3. What about I3? So I3 is here, right? I3 is 1 1. It doesn't matter which one you give it. Both are 1 1. Therefore, it is going to be A, right? So this is how you could implement it. So if the question is, if we give it like this and if we give it like this, are all the inputs same? The option is all the inputs are not same. They depend on this assignment. Fine. Adders are the most frequently occurring circuits in a computer. Any operation that you take is actually implemented in terms of addition only. So in order to discuss about binary adder, we shall go in steps. First thing is, I'll discuss about half adder. I'll discuss about half adder first, and after half adder I'll discuss about full adder, and after full adder I'll discuss about binary adder. So we first discuss about half adder, and then using half adder we construct full adders, and using full adders we construct binary adder. That is the reason I am discussing like this. Okay. So why is the name half adder and full adder is? Why are these circuits given such a name, such weird names, half and full is? Because using two half adders we are going to construct a full adder. That is the reason. We take two circuits which are representing half adders, and from this we are going to construct the full adder. That is the only reason behind it. Okay. So half doesn't mean that we are going to leave the addition in the middle and leave it there, and full doesn't mean that we are going to complete the addition. These are named so that it will be the functionality is like that. Two half adders are going to be put together in order to generate the full adder. Now let's talk about half adder. So half adder is mainly a two input two output circuit. It is going to take two bits, add them both, and it is going to say what is the sum and what is the carry, what is the carry generated and what is the sum, like that. So its main operation will be like this. It is going to take two inputs x, y, let's call inputs as x, y, and it is going to give us two outputs, the carry and the sum. What is the carry generated and what is the least significant bit of the sum. The sum doesn't represent the total sum, it represents the least significant bit of the sum, and carry represents the normal carry, the most significant bit of the sum. So now let's see how it is done. If we add 0 and 0, we know that the answer is 0 0. If we add 0 and 1, we know that the answer is 1, isn't it? 0 plus 1 is 1, 1 is nothing but 0 1, in which the most significant 0 is representing carry and the least significant 1 is representing sum. And if we add 1 and 0, the sum is 0 1, 1 itself, right? And if we add 1 and 1, the sum is 2, which means 1 0. Therefore the least significant bits are represented as sum and most significant bits are represented as carry. Okay. Now if you look at this, if you observe this clearly, you can say that S is, you can write S in terms of min terms. S is nothing but x prime y plus x y prime, and then carry is nothing but xy. Alright, so you cannot minimize it further. So if you try to implement this in terms of a circuit, you can get a circuit something like this. X prime y and then x y prime. This is sum, and the carry is simply xy. Got it? So this is how half adder can be constructed. So if you watch this one, this is nothing but exclusive OR. So if you have an exclusive OR gate, it is very simple to construct a half adder. So using exclusive OR gate, half adder can be constructed simply like this: xy using exclusive OR gate and then AND gate. It can be simplified this way. That's it. Sum and carry. So xy is given as the input and sum and carry you get as output, and this is how half adder can be constructed. Okay, now we put these half adders together in order to get the full adder. Now let's discuss about full adder and then construct it. Okay, now let's see about the full adder. So half adder is about adding 2 bits, but full adder is about adding 3 bits. So why do we need to add 3 bits is, when you are adding a binary number, you will understand it. Let us say we have a binary number like this, 1101 and maybe 1001, something like this. Okay, so initially half adder is enough to add these 2 bits. Let us say when I add these 2 bits, then the carry generated is 1 and the sum is 0. Now next time when I have to add, I'll have to add 3 bits. So this is the reason why we need a full adder. So full adder is required to add 3 bits. Okay, now let's see how to add these 3 bits. So whenever I add 3 bits, the result can be 2 bits. Therefore full adder is a 3 input 2 output circuit. Inputs will be 3 because 3 bits have to be added, and the outputs will be 2 because sum and carry are generated. Now see this, in case of full adder we have x, y, z, let's say is input, and then carry and sum is the output. So how many combinations we have? I'll write this truth table and then we shall go for the K maps and then write the equation, that expression, and from the expression we can try the implementation. Okay, this is the process. Now if you are saying that these three are the inputs, then combinations for inputs will be 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Now what about the sum and what about the carry? All zeros is going to produce only 0. This is going to put only 1 1 is there, therefore the sum is 1. Only 1 1 is there, sum is 1. So 1 plus 1, there are 2 ones, therefore sum is 2. 2 is nothing but 1 0, therefore the least significant bit of the sum happens to be s, which is 0, and the most significant bit happens to be carry, which is 1. And here also the sum is 1, and here the sum is 2, here the sum is 2, here the sum is 3. Okay, now it is clear that by looking at this you can observe few things. So let's do one thing without guessing anything. Let's go for the K-map implementation. So K-map for S, X, Y and Z. 0 0 0 1 1 1 1 0 0 1. So if I write the min terms there for the S, you are going to get something like this. Okay, you can check it later. So I already told you that whenever you get such adjacency, you can just check this. The number of min terms is equal to number of max terms, and you can see that there are ones exactly whenever there are odd number of ones, odd number of ones, odd number of ones, odd number of ones. and odd number of ones. Therefore we can say that this is actually exclusive OR, right? So what is exclusive OR? Exclusive of OR of these three: X, exclusive OR Y, exclusive OR Z. Therefore it is exclusive OR of these three. Now coming to the carry, if you are designing this circuit, carry will look something like this. X, Y, Z, and you'll get something like this: 0 0 0 1 1 1 1 0. So with practice I am just writing it, but then you can directly see this and then you can form it there. So what about the prime implicants? 1 2 3 prime implicants are there. So you just write what they are. This one represents, one is Z and other is Y. This one represents YZ, and this one represents, one is Z and the other is XZ, and this one represents, one is X and other is Y. Therefore C happens to be XY plus YZ plus ZX. Okay, so one other way of writing it is, okay, see, what does it mean? It is saying that you will get a carry whenever any two of the bits happen to be 1. That is true, isn't it? Any two of them happens to be 1. See, when you are adding 3 bits, if any two of them happens to be 1, that is enough that we get a carry, any two of them. So if only one of them happens to be 1, then there is no chance that we get a carry, because the sum is going to be 1 and the carry is going to be 0. If all of them are going to be 1s, then of course we are going to get carry. Sum is, that also has the case that two of them is 1s. So this expression indicates that if any two of them is going to be a 1s, then we are going to get carry, right? Fine. And what does this expression indicate? This expression indicates that if we have odd number of 1s, right, then the least significant bit of the sum is 1. So why? If I have odd number of 1s, then it means that either there is 1 1 or 3 1s. If there is 1 1 only, then the sum is going to be 1 and carry is 0. If there is 3 1s, then the sum is going to be 1 and carry is going to be 1. That is the meaning of this. Now, one other way of interpreting this is, I can write it in some other form also. The reason why I am trying to write this in other form is, I want to design this circuit of full adder as if it is a combination of two half adders. So just to make it possible, I am going to write it this way. See, so whenever any two of them is equal to 1, we are going to get a output as 1, carry as 1. That is true. Now one other way of writing it is, if Z equal to 1, then if that is the case, then either if X equal to 1 or Y equal to 1, then I get two of them as 1. Understand this? If Z equal to 1, then already we got 1 1, then from out of X and Y, if any one of them is 1, that is enough. Therefore if Z equal to 1 and out of X and Y, if any one of them is 1, then it is enough to get a carry. Or else, if both X and Y are 1, then irrespective of Z, I will get 1 carry. Understand that? So this one and this one both are equivalent. If you didn't understand this, you can expand it and simplify it, you will get that. Okay. So what is that I am trying to say is, this expression is saying that if any two of them are equal to 1, then carry will be generated. That is true, isn't it? Now I am just rewriting this one in the other form. If Z equal to 1, then any one of X and Y, if they are equal to 1, that is enough to say that Z equal to 1, or else, that is enough to say that carry equal to 1, or else if both X and Y are equal to 1, then also we can say that carry will be equal to 1. So that is one other way of writing it. So why I am writing this in this form is, it is very useful form. Later I will tell you, in detail again. But here for this explanation, why I am trying to do that is, I want to write a full adder. I want to implement a full adder in terms of two half adders. That is the reason. Okay. Now we already know that a half adder looks like this. Just in the previous video we discussed about this. A half adder looks like this: X, Y, So this is sum, which is x exclusive or y, and this is carry xy. This is how a half adder looks like. Now I want to convert two half adders into a full adder, which means I am trying to place one more half adder here, and then I want to convert these two half adders into a full adder. Okay, so try to understand this. Now what is this half adder? So I am going to add these two half adders. These two are half adders and an OR gate to implement a full adder. Now see this. Now this sum S has to be x exclusive or y exclusive or z. Therefore I am going to introduce the third input z here, and now this third input has to be given to this. Right? Then what do we get here? X exclusive or y exclusive or z, which is nothing but the sum output of the full adder. Got it? Now what about the other one? So the other one is z and x exclusive or y. Therefore this one is x exclusive or y. I am going to give it to AND gate, and then this is z. I am going to give it to AND gate. Then what do we get here? X and z and x exclusive or y. This is what I got. Now z and x exclusive or y plus xy. So xy is already here. So this one I am going to give it to OR gate. This OR gate, right? Now what do we get here? Here I get z and x exclusive or y plus xy, so which is equal to carry. Got it? Therefore using two half adders and an OR gate, I am able to design a full adder. So that is why we discussed about half adders first and then the full adder. Understood this? So what is half adder? Half adder is useful to add 2 bits. And what is full adder? Full adder is used to add 3 bits. Why is the name half adder? Because we are putting together two circuits to make it complete, to make it full. That is why this one is called half, this one is called half. That is why they are called half adders. Half adders are used to add 2 bits, and using them and an OR gate we are able to form a full adder. Okay, so let's now discuss about how to use these circuits in building big circuits. Okay, now let's see how to add the binary numbers using the adders that we have designed till now. We have designed half adder and full adder. Use these components in order to add the binary numbers. So before going ahead, I want to discuss about the conventions that I will be adding, I will be using throughout this topic. Okay, so the conventions are like this. Let us assume that we are talking about 4-bit adder. 4-bit adder means the number will contain 4 bits. So let us assume that we have two numbers, and two numbers are like a and b. So each digit of a and b I am going to represent like this, each digit. So a3, a2, a1, a0. Similarly b3, b2, b1, b0. These are the two numbers that I am going to write like that. Okay, and I am assuming that to these numbers some carry C0 is already given. Okay, some carry C0 is already given. Either that C0 could be 0 or 1. So what is the importance of C0? Later I will tell you when we discuss about the subtractor. This C0 is going to play a crucial role when we use an adder as a subtractor. So I'll tell you later, okay, when the topic comes. For now you can assume that these are the two numbers that are supposed to be added, and for them a carry may be provided. In most of the cases this carry will be 0 unless the number that is going to be added is a negative number, or we are going to perform a subtraction using this adder. And now assume that the carry that we get out of this stage and that we are going to pass to this stage, let us call it as C1. And similarly the carry that is going to be generated from this and that is going to be given to this, let us call it as C2. Similarly, the carry that is going to be generated to this, given to this and generated here, let us call it as C4, C3, okay, and then from here let us call it as C4, right, and this C4 will be provided in the output, and along with that we are going to give this sum let's call it as S3, S2, S1, S0. This is the sum, right? Therefore, if you have to add 4 bit numbers, then how many inputs are there and how many outputs are there? If you simply want to construct this circuit, then the number of inputs are going to be A0, A1, A2, A3, B0, B1, B2, B3 as well as C0, and the output is going to be S0, S1, S2, S3 and then C4. So if you want to design this, it is going to be like this. So it is A0, A1, A2, A3, B0, B1, B2, B3 and then C0, and it is S0, S1, S2, S3 and it is C4, right? So if you want to design this circuit, this adder using conventional method, normal methods, then the inputs are going to be 9, right, and the outputs are going to be 5. So for this 9 input 5 output system, you are supposed to design the truth table, and the truth table is going to contain as many as 2 power 9, which means 512 entries will be present in the truth table, and it is going to take hell a lot of time to design this. So instead of doing that, we use our already formed full adders to do this. Okay, now if we observe this, at every time we are going to add 3 bits, and whatever result we get, we are passing it on to the next stage, and at the next stage again we are adding 3 bits. Therefore this addition of 3 bits can be done one after the other, right? So for that reason we are going to use the building blocks as full adders as building blocks. So before going ahead, I'll just take an example and I'll discuss what I mean to say here. So let us say the number that we want to add is 1011. It is going to be added to 1001, something like this. Then how does the addition take place? Let us say this one is 1. Okay, so initially let us assume that the carry provided here is 0. Then I'll add these two, and the result, the sum is going to be 10, right? Therefore the least significant bit of the sum is written here, and the carry is going to be written here. So carry is going to be 1, right? Carry is 1. Again 1 plus 1 is added, and the carry we get here 1, and again we get 0, which means the carry from here is written here, right? And again 1 plus 1 is added, the sum is written here as 0, and the carry, it will be written here as 1. Okay, and again all 1 1 1 are added, we get a sum of 1 here and a carry of 1, which means this is the answer, right? This is what we wanted. Now if you observe this, it has happened in such a way that we have added 3 bits here, and the carry is passed on to the next stage, and we have added 3 bits here and the carry is passed on to the next stage. Like that we have passed it, right? And so if we want to see how it is happening in terms of full adders, you can watch it here. See this. So we are going to have a full adder. Let us say this is a full adder, and to this full adder I am going to initially provide A0 and B0. So A0 and B0 is provided along with, let us say, C0. Okay, and now this is going to produce a sum of S0 here. Along with that, it is going to produce a carry. Carry is, assume that it is C1. That is what it is, right? And now this one is given to the next full adder. Next full adder, it is going to take the inputs as A1, B1, and it has got the carry C1. So it is going to produce a sum of S1, and it is again going to generate a carry of again C2, and this is going to be given to the next phase where C2 is added with A2 and B2, right? It is going to generate the sum S2, and again it is going to generate the carry C3, and C3 is going to be added with the most significant bits A3 and B3, and we are going to get the carry C4 as well as the sum S3. So this is how it is going to happen. Now if you observe this, the main problem in this one is, look at the way the carry is going on. Carry C0 has to be given and it has to propagate through this full adder, and then we generate C1. So initially without C0 we cannot generate C1, and once C1 is generated, then only this phase has to work. Even though we are going to have 4 full adders, all the full adders are not going to work at the same time. First this full adder will work and it will generate C1. Till that point this full adder has to wait, and once C1 is generated, then only this full adder is going to work. And once this full adder is working, till that time this one has to wait. This one has to wait till C2 is generated. Similarly this one has to wait till C3 is generated. Got it? Therefore this carry is slowly going to pass through all these full adders. That is why it is also called as the ripple carry adder. Ripple carry. So ripple carry adder. The main disadvantage of this ripple carry adder is it is going to take a lot of time. How much time? It has to go through all the full adders. Therefore the time taken in order to add n bits using n full adders is going to be n into time taken for each full adder. So find out the time taken for each full adder. So we have to wait for this full adder to execute and then produce this one, then this full adder, then this full adder, then this full adder. Therefore even though we have these many full adders, we are not going to use them all at once. We have to use them one after the other. So the disadvantage of this one, this ripple carry adder, this is called as ripple carry adder. Ripple carry adder is, it is going to take a lot of time. So now in order to correct this disadvantage, what is that we are actually waiting for? In every stage we are waiting for the carry, and the carry we are not able to get unless the previous stage has completed. It is how we generally add, even on pen, using pen and paper we do the same thing, isn't it? Therefore just to correct this delay, see, the main problem in this one is we are going to get the carry only after a stage, a finite automata has a full adder has completed its execution. So till that time we are supposed to wait. Just to correct that, just to modify that, what we are trying to do is, without waiting for the carry from the previous stage, at every stage we use some circuit in order to generate the carry required. That is called as carry look ahead adder. The disadvantage of ripple carry adder is it is going to take a lot of time for us to generate the answer. So just to correct it, what will the carry look ahead adder will do is, it will generate the carries on its own at every stage. Using that method we can solve this problem. Okay, so you can take this one and say that the disadvantage is it is very slow, and in order to correct this disadvantage we are going for carry look ahead adder. Okay, the main problem with this ripple carry adder is the carry is going to propagate till here, and then this one is going to propagate till here like this. So our main intention is to see that I want to break these links, which means for every stage the carry required should be generated directly without waiting from the previous stage. So how is it possible? Let's see that. So in this one I'll just show you how it is working. Okay, so in this one C1 is nothing but, if I want to get this carry out, it is C0 into A0 exclusive or B0 plus A0 B0, right? So what does it mean? The carry C1, so this is the formula which I have written earlier also. So carry C1, which means the carry that we get into this stage can be either because of the input carry. So if this C0 is 1, so I am just telling you how the carry is generated from out of this stage and given to this stage, right? How is that possible? If C0 is 1, and either one of these a naught and b either one of these a naught b naught is 1, then carry will be generated, or if a naught b naught is 1, then carry will be generated, and that will be called C1, isn't it? And similarly, how do we get C2? C2 is either if C1 is 1 and one of these A1 and B1 is 1, or if A1 B1 is 1, right? And similarly, what is C3 here? C3 is, so look at this, C3 either C2 is 1, which means if the earliest stage has got a carry which is 1 and one of these two is 1. So if this is 1 and if one of these two is 1, then carry will be generated. That is when we get C3, right? So A2 exclusive or B2, or if these two are 1, then also we get a carry C3, isn't it? A2 B2. What about C4? C4 is, how do we get C4? If C3 is 1, if this carry is 1 and one of these two are 1, which means A3 exclusive or B3 plus, or which means either this one is 1 and one of these two are 1, or these two are directly 1, A3 B3, then also we get the carry C4, right? So this is the equations we are following. So in C1 is depending on C0 and C2 is depending on C1. This is the reason why C2 has to wait till we get C1, and C3 is depending on C2. This is the reason why C3 has to wait till we get C2, and finally C4 is depending on C3. That is why C4 is depending till C4 has to wait till we get C3. So I don't want these kind of dependencies. I want everything to directly be available. So what I'll try to do is I'll try to keep on back substituting. See this, in place of C1 I'll substitute this entire value, then C2 will only depend on C0. Okay, once C2 depends only on C0, then in place of this C2 I'll substitute that C2 whatever I got, then C3 will also depend only on C0, then I'll take this one and substitute here, then C4 will also depend on only C0, and since C0 is directly available at the beginning, we are not having this chain. So in order to just simplify this procedure, I am going to introduce two new variables, because writing this one is too big. That is the reason I am going to introduce two variables. So let us call gi equal to ai bi, okay, and then pi equal to ai exclusive or bi. Okay, so I am using two variables. So yg and yp is, g means the generation function, p means the propagation function. I'll explain you. First you try to understand this entire thing. I'll explain you one more time. I'm not sure whether you understood this or not. I'll just explain you. See, in order to get the carry C1 from this stage, if C0 is 1, if any one of these two are 1s, then I'll get a carry. If C0 is 1 and any one of these two ones are 1s, then I get a carry. This entire term represents that thing. What is that? C0 is 1 and exclusive OR means any one of them is 1, right? Either this or this, that is exclusive OR, right? Or if these two are 1s, then independent of this, either if it is 1 or 0, I don't care. If these two are 1s, I get the carry. That is how I get C1. Similarly, if I have to get C2, how will I get C2 from this stage? If this one is 1 and if any one of these two are 1s, then I get C2, or if both of them are 1s, then irrespective of what C1 is, I get C2. Likewise, I have written all this. Got it? And now, just to simplify everything, I am just introducing new terms gi and pi. Now if I substitute in place of all this gi and pi, what we get is, observe this. So in place of these terms, I am going to substitute gi and pi. So see that. Now what can we write? C1, I'll write here. So I am just copying it there. Okay, let me copy it here. So C1 is equal to C0 into, what is A0 exclusive or B0? It is nothing but P0. P0 plus G0. Similarly, C2 is equal to C1 into P0 plus C1 into P1 plus G1. C3 is equal to C2 into P2 plus G2. C4 is equal to C3 into P3 plus G3. Okay. Now, what does it mean? See, I just written it in a shortcut. So, what does this actually mean is, in order to get a carry C1, it could either be generated in the stage G0, or it could have been provided as C0 and propagated through the stage P, 0. So, if you call this one as stage 0, in order to get this C1, it must have been generated in stage 0. Generated means by these two, right? If these two are 1 and 1, it might have been generated from there, that is by G0, or it must be C0, which is 1, and it must have got propagated through this. How will it get propagated through this if any one of them is 1, right? That is the propagation term. Therefore, propagation term represents if any one of them is 1, it has the property that the carry could propagate through it, right? And what about this one? If both of them are 1 and 1, it has the property that they could generate the carry without without the need of propagation. That is the meaning of it. Try to understand this. It is very important that you understand this. They will ask you such this question in the gate. Very important that you understand this. So what about C2? C2 means carry generated in stage 2. C2 it can either be generated in stage 1, which means if these two are 1 and 1, it could be generated in stage 1, or C1, which was 1, could get propagated, that is why C1 P1, and similarly C3 could be generated in stage 2, which means if these two are 1 and 1, it could have it could have been generated. Otherwise, it was just C2 which propagated through this. How will it propagate? When one of these are 1, that is why P2 term here. Got it? Similarly, C4 would have been generated here, that is by G3. In stage 3 it would have been generated, otherwise it would have been C3 which got propagated. So it would have been C3 which got propagated through this state, right? So that is how we have written this. Now let's just try to get rid of all these dependencies and write every equation in terms of only C0. Instead of having C1, C2, C3 here, instead of making these dependencies, let's back substitute and eliminate everything and get only in terms of C0. Okay. So we let C1 equal to C0 P0 plus G0. So it doesn't contain any carries. C0 is nothing but the initial carry provided, no harm in that, leave it as it is. Now coming to C2, in place of C1, in place of this C1, you substitute this entire equation. Then what do we get? C0 P0 plus G0 into P1 plus G1. Now just expand it. What do you get? C0 P0 P1 plus G0 P1 plus G1. So what do you understand from this equation? In order to get the carry C2, the carry would have been C0, which is initially provided, which gets propagated through 0 stage and then stage 1. So this means that in order to get this carry, this would have been carry C0, which got propagated through this stage and then to this stage and reached here, or means plus. Otherwise, the other way is it would have been generated in the stage 0, G0 means in the stage 0, and then propagated through stage 1 P1, which means it is not the case. The other case is it would have been generated here. How will it get generated? When both of them are 1 1, then it came here and it got propagated through the stage 1. How? Either one of them is 1, then we got this. That is the next case. Otherwise, the other one is it would have been generated in stage 1, which means it would have been directly generated in stage 1 because both of them could be 1 and 1. These are the three cases. Are you getting this? Okay. Next, Let's go for C3. C3 equal to C2 into P2 plus G2. Therefore, in place of C2, I am going to substitute this entire thing. What does it mean? C0, P0, P1 plus G0, P1 plus G1 into P2 plus G2. See, if you understand the way I am writing it, you need not by heart it. In the exam, they will ask you to write these equations. Then you know if you don't understand how I am trying to do this, you will have to by heart it. So just understand this. It is very easy. Now you just expand it. Then what do we get? C0, P0, P1, P2 plus G0, P1, P2 plus G1, P2 plus G2. Now try to understand this. They are saying that in order to get the carry C3, what are the various possibilities? This one is saying that the C3 could have been whatever carry you have given initially that got propagated through stage 0, stage 1 and stage 2. It means that the C3 would have been, we would have got the C3 from C0, which got propagated through stage 0 and then stage 1 and then stage 2 and got here. That is the meaning of it. It is C0 which got propagated through 0, 1, 2, or it got generated in stage 0 and then propagated through stage 1 and stage 2, which means it got generated because of these two being 1, and then it got propagated through stage 1 and stage 2 and reached here. Got it? Otherwise, it got generated in stage 1 and propagated by stage 2, which means it got generated by stage 1, these two being 1, and then it got propagated through stage 2 and it reached here. Otherwise, it got simply generated in stage 2, which means it got simply generated here and we got here. Got it? And similarly, now you can write C4. So what is C4? In place of C3, you are supposed to substitute all this. Then what do we get? C0, P0, P1, P2 plus G0, P1, P2 plus G1, P2 plus G2 into P3 plus G3. Just expand this. What do we get? C0, P0, P1, P2 plus G0, P1, P2, P3 plus G1, P2, P3 plus G2, P3 plus G3. Now check this. Now what does it mean? Carry would have been generated in stage 0. Carry would have been given to stage 0, which got propagated through stage 0, stage 1, stage 2, stage 3 and finally came out as stage 4. Otherwise, carry would have been generated in stage 0 and it got propagated through stage 1, stage 2, stage 3 and finally got to C4. Otherwise, it would have been generated in stage 1 and propagated through stage 2 and stage 3. Otherwise, it would have been generated in stage 2 and propagated through stage 3 or generated in stage 3. Now, whatever it is, if you observe these equations are written only in terms of the three terms. One is G, other is P and other is C. So, if you have only these three terms, what is the advantage of it? So, C0. So, it means that every carry C1, C2, C3, C4, these are depending only on C0 and not on each other. Therefore, since this is depending only on inputs A and B, this is depending only on inputs A and B, and this is depending on C0. So, the entire carry terms are now depending only on the inputs and they need not wait for the others. So, using this AND OR gates, we can generate them easily. Okay. So, what I will show you is I'll just erase this and I will show you how to construct this C0, C1, C2, C3, C4, and then using that how to construct the adder. Okay, I will just draw the diagrams and explain. So you can copy this one, and I'm going to erase it. I'm going to put it in terms of the circuit. Once I design the circuit, it will be easy. So what you have to learn from this is how are these generated and carrying. So they might ask you some equations like this. So they'll miss you one of the terms and they'll ask you to fill it. Unless you understand it, you will not be able to answer it. Don't by heart these equations, they are very simple. Now I'll try to design this circuit using these equations. Okay. Now assuming that these p terms and g terms are already available, because generating p terms and g terms are very simple from the given input. For example, if you want to generate pi, so pi is nothing but pi is nothing but ai. It is exclusive, alright. So let's say gi. So gi is nothing but ai ending with bi, and then pi is nothing but exclusive or. So if I have ai bi, then I get pi, right? So assuming that these g terms and p terms are already available, then we can design this circuit to generate the carries, and once the carries are available, we can directly do the addition. Okay, so what I'll do is I'll tell you how to design or how to generate the carries using this circuit, and later after we are done with this, I'll tell you, I'll put everything together, like how to design this adder completely right from scratch. So let's see how to generate the carries. So we know these equations. What is the equation for C1? What is the equation for C2? What is the equation for C3? We need not generate C4 because it is not required. It will be generated as the addition. For example, what I mean to say is, if you are having 4-bit adder, so 4-bit adder means, let's say this is A1, A2, A3, A4, and then B4, B3, B2, B1. If I have this 4-bit adder, C4 is nothing but the carry coming out of this stage, which is not used by any other stage. Therefore, we need not generate it well in advance. But then C1 has to come out of here and it is required by this stage, and C2 has to come out of here and it is required by this stage. Therefore, C1, C2 and C3 has to be come out of it and it has to be required in this stage. Therefore, let's discuss about how to get C1 and how to get C2 and how to get C3. C4 is not required, so I am not going to implement it. Now if you observe this, these equations are written in terms of one is C0 and other is P and G. So all these equations, if you observe them, finally I have written them in terms of one is the carry which is provided to them as internal, I mean from outside, and second thing is only using these terms A and B bits, I have generated one is G and other is P. So all the equations I have written in terms of C0, G and P terms, and G and P terms can be generated straight away. So after that we can use this circuit, this logic, in order to implement this. So if you look at this, these are all the terms I needed in order to generate C1, C2, C2, C3. These are the terms I need. So I am providing all of these, and then I am using a 2-level logic. Why? Because it is sum of product expression, isn't it? Therefore, I am going to find out the product terms and then I am going to put them together. This is how we can generate this carry lookouts, isn't it? So we are generating the carries without depending on the previous stage. So before we start the actual addition, all the carries will be available at the required stages, and therefore we can add them directly without waiting for them. So there is no ripple here. All of them are directly generated. But what is the disadvantage of this compared to the earlier one? In the earlier ripple carry addition, we don't have this extra logic, but here we have to have this extra logic, and the complexity of this circuit is going to increase based on the size of the numbers. If the size of the numbers are going to increase, see this. So the AND gate, the number of inputs for the AND gate are going to increase, and the number of inputs for the OR gate are going to increase based on the size of the input. Therefore, it is more complex and costly, but then it is faster compared to the normal ripple carry addition. Therefore, it is the most popularly used. Okay, so what I'll do is, I have explained all this in parts. Now I'll try to put everything in one diagram and I'll show you how this entire thing actually works. Okay. Now let's see this total overall implementation of carry look ahead adder. So the heart of it is carry look ahead generator, and how to generate this carry look aheads I already given you in the earlier example. In the earlier video I've shown you how we are going to use two level AND or logic in order to generate the carries using these G and P terms. Okay, so now in this diagram I'm putting the all the circuits together and I'm showing you how the adder looks like. So this is the adder, this is the carry look ahead adder in the final form. Okay, now initially we are supposed to generate G terms and P terms. We know that G is nothing but ANDing of the corresponding bits, and then P is nothing but exclusive OR of the corresponding bits. Now you generate all of them, and now internally inside this box, even though I am not showing you, you can replace this internal box with the earlier circuits AND OR logic. So if you put that AND OR logic, then this internal black box is going to give you outside all the carries. What are all the carries? C4, C3, C2, C1. You can generate all of them. Okay, and anyway you don't need C1, C3 to C4 to be given to anything, so directly give it to output. And now we know that the sum S3 is A3 exclusive OR, B3 exclusive OR, C3, and already we have done this A3 exclusive OR B3 here. A3 and B3 exclusive OR is already done, which means P3. Therefore I am directly giving that P3 to this. That is what is happening. Okay, P3 is directly given, so what can you say? It is exclusive OR C3. And also one interesting thing here is, since it is 3 inputs and 3 inputs are given to exclusive OR, even if you replace these symbols with exclusive OR, there is not going to be much problem. Okay, and and similarly you can find out S3, S2, S1 and S0. Okay, so that is how we can design this complete adder. So what is the advantage of this is, the main advantage is there is no waiting at all. So if you see this, there will be AND OR gates and then directly this one. So the internal circuit is going to be a bit complex, whenever this number of inputs are going to increase. Let us say instead of 4 bits, if you want to add 8 bits, yes, it will be complex, but then there is no rippling effect, which means no one is really waiting for, if you in order to find out S2 we need C2, but then in order to perform this C2 we need not wait for the previous phase to send the output. It is directly available, therefore it is faster compared to the ripple carry adder. Okay, so this is how we can look at the carry look ahead generator. So if you understood this, it is fine. Otherwise, how we can visualize it is this way. See this. So one other way of visualizing it is, let us say you are giving all the inputs to this. One is C0, other is number A and other is number B. Okay, and let us say this is carry look ahead adder generator. Carry look ahead generator. Now carry look ahead generator will give you all the carries like C0, C1, C2, C3, let's say C4. All the carries are generated. Now you can take these carries and you can take these numbers and you can give them to the adders, actual original adder. Okay, so you can give it to full adder. So what do you want to give it to full adder? You can give C0 and then A1, A2 and then C1 and then A2, A1, like that. So you can take the corresponding carry and you can give it to the full adder, and full adder will give you the output. That is what is happening here. So where is the full adder here? I didn't show you the full adders. Do you see any full adder here? Yes, so full adder is here, isn't it? It is simply here in this case exclusive OR. Since carry is already generated, you need not generate the carry, you have to just generate the sum. Okay, so that is how it is implemented. Fine. Now there are advantages and disadvantages to both the adders. One is ripple carry and other is carry look ahead. So what about this ripple carry adder is, if you look at ripple carry adder, so it has got one advantage. What is it? It is simple to design and it is cheaper, right? And what is the disadvantage of this? It is slow. It is slower compared to the other one. Now what about carry look ahead adder? In carry look ahead adder, the disadvantage is it is complex. It is complex to design and it is costly to implement. And what about the advantage? It is fast. It is faster compared to ripple carry adder. Therefore, since both of them are having advantages and disadvantages, whenever we get any such system, we generally combine both of them and try to get some hybrid with both the trade-offs. So what we do is, I'll just take an example and I show you how we can work with that. Let us say we are supposed to add 8-bit number. Okay, so A and B, A7, A6, or let's say A8, A7, A6, A5, A4, A3, A2, A1. This is number A, and the other number is B. B8, B7, B6, B5, B4, B3, B2, B1. Okay, and now we are going to supply to this the carry from outside C0. Why do you want to supply that carry even? No, generally if you are going to add two numbers, that C0 is going to be 0. Then why are we still including it? Later I'll explain you. Later, just in some next few videos, I'll explain you that concept. For now, understand that it is important. Okay, and now from this one carry C1 is going to come out, right? And from this one carry C2 is going to come out and it will be given to the next phase. And from this one carry C3 is going to come out, and from this one carry C4, and from this one carry C5, and from this one carry C6, and then C7, and finally C8 is going to come out. So now if we use the ripple carry adder, then this is the concept. So the carry has to come from the earlier stages, so it is very slow. Now if you observe this carry look ahead adder, then what happens is, for the same kind of addition, yes, so it is going to be S8, S7, S6, S5, S4, S3, S2, S1. Okay, now for the same kind of numbers, if you want to add the same kind of numbers, and if you are looking for the carry look ahead adder, how does it work is A8, A7, A6, A5, A4, A3, A2, A1, B8, B7, B6, B5, B4, B3, B2, B1. Now we provide C0 directly, and using the carry look ahead generator, all the carries will be generated: C1, C2, C3, C4, C5, C6, C7, and C8 will be generated. So all the required carries are directly generated and they are not coming from the earlier phases. That is where it is fast. Therefore we get the result directly. So it is faster. But the problem is, in order to generate these carries, the time taken is going to be more, isn't it? In order to generate these carries, the not time taken, the circuit required is costly. Now the one solution is, let's combine these two methods. Let's not go with the purely carry ripple carry adder or purely carry this look ahead carry generator. Let's combine both of them, so then we get a hybrid model. So what I try to do is, watch it now. A4, A3, A2, A1, B4, B3, B2, B1. Now I'll use 4-bit carry look ahead adder to add these 4 least significant bits, and once I use it, okay, so the reason is, if I have only 4-bit adder, if I design only 4-bit carry look ahead adder, the circuit required to generate the carries will be lesser, because I need only 3 carries or at most 4 carries. I need not wait for the other one, right? And here also I'll add one more 4-bit. So A5, and then B5, A6, B6, A7, B7, A8, B8. Okay, so now using this 4-bit carry look ahead adder, I'll add them directly using the carries. So carry is C0, C1, C2, C3, and then once this C4 is generated, right, I'll not directly start adding them. What I'll do is I'll finish off this addition, okay, and to the same adder, to the same 4-bit adder, again I'll give all these as inputs and carry it, which means I'll finish off this addition first and then save this carry, right, and then apply this carry as C0 and again these 4 bits, and I can get the answer, which means I'm using it as if it is a ripple carry adder. Why? Because I'll finish this entire phase, wait, and then finish this entire phase. Therefore it is actually a kind of ripple carry adder, and we can have 4 such 4-bit adders in order to implement 16-bit addition, and you can have 8 such 4-bit adders in order to implement 32-bit addition. Now what is the advantage of this? It is not as slow compared to it is not as slow as this ripple carry adder, as well as it is not as costly as this 8-bit carry look ahead adder, because it is simply 4-bit carry look ahead adder. Therefore it is a trade-off. So we generally use these hybrid models, which means we are not going to have 32-bit adder. What we have is generally 16-bit adders in most of the cases, or if you can spend money, yes, you can go with 32-bit carry look ahead adder, but the best thing is go with 2 16-bit adders, add the least significant 16 bits, and then whatever carry you get out of it, you save it and again give it as the input for the next phase, the next 16 bits, the most significant 16 bits. Likewise, you can add them in phases and then reduce the cost and increase the speed, right? It is the example of hybrid adder. Okay, fine. If you observe all the adders that we have seen till now, so first one is we have seen half adder, and then using 2 half adders we have designed a full adder, and then using many full adders we have designed binary adders, isn't it? So what is binary adder? When we have to add not just bits but numbers. Then when we are putting many full adders together, we are trying to put many full adders together and we are getting the binary adder, right? So we have seen 2 types of adders. One is carry look ahead adder and the other one is ripple carry adder. So both of them were actually using many full adders, right? If it is n-bit adder, n-bit ripple carry adder, then we are actually using n full adders. If it is carry look ahead adder, then depending on that we are having more than 1 full adder. So depending on the capacity, okay? Now, if we have only 1 adder and we don't have any other, one full adder, only 1 full adder we have, and using 1 full adder we are supposed to add 2 numbers, then what are we supposed to do? Let us say we are supposed to add 2 4-bit numbers, then how to add them? So if we have to add these 2 4-bit numbers, then we are supposed to have 4 full adders, isn't it? Then only we can add 2 numbers. But then if I use only 1 full adder, then also I can add them, but then only one step after the other, which means, see this. So look at the organization. I am having only 1 full adder which can take 3 bits at a time, and it will compute the sum and carry, okay? And these 3 bits are going to be, one is 2 bits from the numbers and the third bit is carry from the previous stage, and using these 3 bits we are going to produce the sum and carry, right? So to tell you what we are trying to do here exactly, we are going to use registers here. The numbers that have to be added are going to be stored in the registers, and the bits are going to be given to the finite full adder one after the other, and then the sum is going to be stored here and it is shifted. So we are going to use here shift registers. So I'll explain you the concept here, how it is working, then we can again go back there. Okay, it is an example of sequential circuit. What is a sequential circuit? You please watch the sequential circuits topic, there you understand it. It is actually an example of sequential circuit. Okay, now I'll show you what is happening here. Let us say we have 2 registers here, A1, B1, A2, B2, A3, B3, A4, B4. Now these 2 bits are first added and the sum is stored in the result one. So these two are initial registers, and this one is the output register. So these two will be added, and the sum S1 will be stored here, and whatever carry is generated out of them, which is here in this case A1 and B1 is added, and C1 will be generated, and that particular sum will be stored in the memory for the next stage. And once the sum is available here, I'll shift all the registers one step right. Then what happens here is, see this, if I shift all of them one step right, A2 will come here, A3 will come here, A4 will come here, and 0. If I shift all of them right, then B2, B3, B4, 0. And if I shift all of them right, then here it is going to be, S1 is going to be here, and whatever is going to be here, it is going to be there. Okay, so either it doesn't matter, earlier whatever was there, it will be there, and now this particular location will be idle, and in the next step these two will be added along with the carry generated, which is C1. Now these two will be added, and the sum S2 will be written in this location. Okay, and whatever is the carry generated, that will be stored in the memory, which will be overwriting the earlier carry, which means C2 will be stored here. And after this computation, again everything will be moved right. Then what happens here, A3 will move here, A4, 0, 0. Similarly B3 will move here, B4, 0, 0. If you observe it, I am just shifting them right. Okay, and now these two will be added. I hope you are getting why only these two bits are added, because only these two bits which are present in the least significant position in these input registers are actually provided as input to the finite automata along with the carry from the earlier stage. That is how the entire operation is happening, and the result whatever we are getting is going to be stored here initially, and later we shift it. Okay, and again this will also be shifted, which means S1 will go here, S2 will go here, and this one will be idle, empty. Now A3 B3 will be added along with C2. Okay, then whatever result we are going to get here, that will be stored here, S3, and carry will be C3. Got it? So that will be stored appropriately, and afterwards everything will be moved, which means A4 will come here and 0, 0, 0, and similarly B4 will come here to the least significant position, 0, 0, 0, and these will be moved, which means S1 here, S2 here, S3 here, and this position will be vacant. Okay, vacant in the sense there will still be this. See, why am I actually writing here 0 is, there will not be 0. See, if you are shifting them one bit right, either you can fill it with 0 or you can fill it with some other bits. That depends on what type of right shift you are using. Okay, so I am not interested in what type of right shift operations we are using here. What I wanted to show you is how the information is moving and how the corresponding addition is going on here. Okay, and now these two will be added, A3, A4 and B4. When these two are added, then S4 will be produced and C4 will be produced as the result, right? Finally we got the required answer there, right? So using just one full adder and a memory element, so because of this particular memory element, the output is acting not just as a function of input but also as the function of output of the previous stage. That is why it is also called as sequential circuit. So later in sequential circuits, that particular topic, you can know more about it. Here I am not discussing about it. You would read it so you will understand about it. Okay, now what are the important points here is, it is a serial adder. Serial adder means one after the other it is going to add. Okay, and it is very slow compared to all the adders, because we can add at any time one bit. So if we have n bits, I can add first one bit, next one bit, next one bit, next one bit. Therefore time taken for this will be equal to the time taken for adding these many n into full adders, right? And also the movements have to be allowed, so in inwards and then outwards. So it is very slow, but still it is a good example because it is the cheapest one. You need only one full adder. In the earlier examples we needed more than one full adder, right? Okay, now you design a binary adder, whatever method you use, either carry look ahead adder or whatever means you use. Let us say you have designed a binary adder but with just a minor modification. the input, one of the input A is given as it is, and the other input B is given through exclusive OR gates, which means actually binary adder has to be given two numbers, and two numbers can be each one can be of n bits, but here I am taking an example of 4-bit binary adder. So 4 bits of one number are given, and the other 4 bits of the other number are actually given through the exclusive OR gates. Okay, and the one of the input for the exclusive OR gates is B, the number, second number, and the other input is a bit X. Okay, so if you observe this, I am giving the input B to the adder through the exclusive OR gates, but then it is also given one more input to the exclusive OR gates as X, and X is also given as the other input C0. So C0 is nothing but the initial carry we provide. Now I want to analyze what does this binary adder acts as. So if you don't have these gates and this X, and if you directly give B's as it is, then it is simply going to act as a binary adder, which we know till now. But then with the placement of these exclusive OR gates, it is going to change slightly in its functionality. Let's see what are the changes. Okay, so before watching it, I assume that you have already watched, or if you didn't watch, please watch the number system and then come back to this topic, the number system topic, which is right below this topic. After this combinational circuits, I think there is this sequential circuits. After sequential circuits, there is number system. You please watch number system and again come back to this, then only you will understand what I am trying to do here. Okay, so otherwise you skip this video for now, finish off the number system and again come back here, otherwise you will not understand it now. Fine, now let's analyze this. So in general, if I have a bit B and if I am exclusive OR, if I do exclusive OR with 0, then it is nothing but A exclusive OR B. Then we know that it is A into B prime plus prime into A. So this is the formula, isn't it? B exclusive OR 0 is B 0 prime plus B prime 0, which is nothing but B. So what did you understand from that? If you exclusive OR any bit with 0, the result is going to be same bit. Now the other case is B exclusive OR 1. Now what do you get with that? So which is nothing but B prime, which means if I exclusive OR any bit with 1, that particular bit is going to be complemented. If I exclusive OR any bit with 0, we are going to get the same bit. So it is, exclusive OR can be used to complement a bit given that other input is 1, or to send it as it is if this number is same. Now if you observe it, just try to observe this one. In case if X is going to be 0, in case if X is going to be 0, then we are going to get a 0 here, and all these bits are going to be as it is, which means B4, B3, B2, B1. Are you getting this? If this exclusive OR is 1, if this exclusive OR is 0, all of them are going to be same, and this one is going to be 0, which is nothing but binary adder is going to get two numbers. One is from A1 to A4, other is from B1 to B4, and when we add them, it is simply nothing but A plus B. So one case is if X is equal to 0, that particular X is equal to 0, then this adder is going to perform A plus B. And the other case is if X is equal to 1. Let's analyze what happens if X is equal to 1. If X is equal to 1, all these are going to be complemented, alright, and here also we are going to get 1. So what does that mean? If X equal to 1, then it is nothing but A plus, all these are going to be complemented, or if when all the bits of a number are complemented, it is nothing but 1's complement, isn't it? Then it is nothing but 1's complement of B plus 1. Why? Because in place of carry we are providing 1. Therefore A is going to be added with 1's complement of B plus 1. Now when we add 1's complement of B to 1, which is nothing but A plus 2's complement of B, right? and in 2's complement number system, a plus 2's complement of b is nothing but a minus b. Got it? Therefore, this particular adder has the capacity to work as two things. One is when x equal to 0, it is going to perform a plus b, and the other is when x equal to 1, it is going to perform a minus b. Therefore, it is also called as binary adder cum subtractor. So we can use a binary adder as both adder as well as subtractor. This is the reason, the main reason why we are interested in 2's complement number system is when we go into that, we can use the same adder as both adder as well as subtractor by putting these exclusive OR gates, which means we need not design a completely different circuit for subtraction. Once adder and subtractor is available, we can do multiplication as well as division. Therefore, all the basic mathematical operations can be performed just by using one circuit, which is nothing but adder, right? And it is not just this only use. Okay, let me ask you few questions on that, right? I'll just ask you a few questions. Let's see this. The above circuit is not just going to be used as adder and subtractor. Using this circuit, we can do various other functionalities as well. That depends on what are the inputs we are providing. Now, for example, as an input A, if you are giving a BCD, and as an input B, if you are giving 0 0 1 1, which means 3, and if you are giving 0 as x, then what will be the function of it? So try to understand it. As one of the input A, if I am giving BCD number, and the other input B, if I am giving the number 3, and as x, if I give 0, what does it do? What does this circuit do? It is simple. Since x is equal to 0, the entire circuit is going to act as adder, isn't it? Now what will be added? BCD will be added in number 3, and the output will be BCD plus 3. So what will be that output then? Then the entire circuit actually functions as XS3 adder. Therefore, the function of the entire circuit is BCD to XS3 converter. Why? Because if you are giving BCD as input, it is simply adding number 3 to that and producing that result. So which is nothing but BCD to XS3. Now to the same one, if you try to apply this, which means XS3 is given as the input, and 0 1 0 0, 3 is given as the other input, and 1 is given as x, then what will happen? We already know that when x equal to 1, the circuit acts as a subtractor, right? Therefore, subtraction will be done. What will be subtract from what? From XS3, 3 will be subtracted, isn't it? See, whenever you have x equal to 1, the circuit is going to act as a minus b. Here a minus b is nothing but XS3 minus 3. Now if you subtract it from XS3 the 3, then what will remain? BCD. Therefore, this circuit will function as XS3 to BCD converter. Now look at the next example. Now if you have 1001, 1001 is 9, which means in place of A, you are supplying 9, and the B is given BCD, and X is given as 1. So when X is given as 1, what does it mean? This circuit acts as a subtractor. So now the circuit is going to act as a subtractor. Then what is being subtracted from what? From A, B is going to be subtracted, isn't it? So what is A? 9. And what is B? 9 minus some BCD number. Therefore, the result is going to be 9 minus some digit, some BCD digit. Then what is that mean? 9 minus something is nothing but 9's complement of B. Therefore, this circuit is going to function as is going to find 9's complement of B, which means given input B, you can find out the 9's complement of B if one of the input A is 9 and the other input X is 1. Got it? And the other one is, let us say here 10 is given. So 10, and the other one is 1 is given here. So if you have 1 here, it is going to act as a subtractor. Now what is being subtracted from what? 10 minus B, isn't it? From 10 B is subtracted, therefore it is nothing but 10's complement of B. Got it? So we are going to use this one as 10's complement of B, right? Fine. So till now, whatever gates we have seen, AND gate, OR gate, NAND gate, and whatever circuits we have built with them, using them, they didn't involve anything called as feedback or the entire output has been only the function of the inputs, which means you give some input and we get the output, and that is the circuit. Now we are going to look at the sequential circuits, in which it is not just the input that is going to affect the output, it is also the previous history. History means what has been done till now and what are the various outputs produced, and depending on the entire history, the new output is going to depend. So I'll just show you what it is. See this. Now you know this combination circuits. Combination circuit means it is simply containing that AND gate, OR gate, and which does not take anything back. Okay, that normal combination circuit, whichever we have seen. For example, the decoder, encoder, all those are combination circuits, multiplexer, and maybe the functions which we implemented using AND or realization. Everything is combination circuit. Now to that combination circuit, we are going to use the inputs. Along with that, what are we going to give is the output produced in the previous state or output produced till now has been represented or has been stored in memory element, and now this memory element is going to be giving back that input to the combination circuit, which means now the combination circuit is going to take the inputs as well as the outputs produced from the previous state. This is called previous state, and next time we get the next state, right? Or you can call it as the present state, and then we get the next state next time. So what I really mean is, we are going to use some external inputs as well as we are going to use some inputs which are nothing but the previous outputs, and using that we are going to get the current output, right? Therefore here output is not just depending on the input, it is also depending on what has happened earlier, right? And moreover, if you look at it, it is not just one state, it is a collection of entire history, which means, see this. Now let us say we have state. State means what we have been giving from the initial part when we start this circuit. Now let us say it is S1. So out of this state we get some output, right? Now this output is going to be given to the next state also, right? Therefore again we get the output, some output, and now this output will be given to the next state. Therefore if you look at it, at any state it is not just giving the output from the previous state, it is giving the output from the entire history. Okay, I'll take examples and explain you, so don't worry about it. If you didn't understand anything from the block diagram, I'll take lots of examples and explain you, and I'll make it very simple. Now just take these notes as of now. First one is, the external output of the sequential circuit depends on the external inputs. That is what we know. Even the combination circuit is also going to do the same thing. External output depends on the external input and on the present contents of the memory element. It is very important. The difference between combinational circuits and sequential circuit is the presence of memory element. Till now I didn't discuss anything about how to use the memory elements in building of a circuit, right? So now we have something called as memory element. Next one is, the present contents of the memory element are called present state, which means whatever is present in this memory element is called the present state, right? And the new contents of the memory elements, which means, see this, I am going to give it back to here, and now again the new contents are going to get into this, right? That is what they are calling. The new contents of the memory element are obtained by taking external inputs. External inputs means this one, and present state. Present state means this one, right? Therefore that is called as next state. So initially whatever is present in this is called present state, and now we are going to use the present state as well as the inputs, and now next time whatever we get and whatever we store in this memory is called as next state. Got it? Now this next state will become the present state for the next state, right? Okay, I'll just take an example and explain you. It is very simple concept. If you understand everything in a sequential manner which I discuss from now on, it will be very simple. Otherwise, if you get anywhere confused, you please stop it and then again go back from the beginning, right? It is very simple topic. Okay, fine. We shall see examples. Now since we want the memory part to be present in the sequential circuit, now let's see how to build the memory, or what do I really mean by memory. See, We already know that the memory means you might have seen that hard disk, right? That is the first memory. Initially people, how they used to store the information is they used to have punch cards. So they used to have a paper kind of thing, and on that they used to punch, right? Punch means they make holes. If there is a punch, it means 0. If there is no punch, it means 1. So that used to be the long back, that used to be the way. And next thing is, after that they have built the tape recorder and tapes. You might have seen it, right? And next thing is they have built the hard disk, and that is where they are going to store the information, right? And then slowly, using the electronic circuits also, we are able to save the memory. So this is what is used in our RAM, so random access memory. And the smallest part or the building block of the memory is called as a flip-flop. Flip-flop is going to hold 1 bit of information. So we are going to discuss about the basic memory elements, which are flip-flops. Now first see this. A memory element is some medium in which 1 bit of information can be stored or retained until necessary, which means you can store 1 bit for any longer, and whenever you want to see what you have stored, you can definitely store it, take it and see it, and thereafter its contents can be replaced by the new value. If you want to change it, you can change it. That is the property of the RAM. What is ROM? We have already seen ROM, which is used by this, implemented by this decoder and then matrix. There the property is you can only save it, but then you cannot modify it. But now the flip-flop is a different kind. Here in this you can save it forever, or if you want to modify it, you can modify it, right? And now the basic binary or digital memory circuit is known as flip-flop. So the building block, the smallest part is known as flip-flop. Now millions of flip-flops will be put together to form a 1 MB memory, like that. So flip-flop is a very small device in which you can store one bit forever, provided that you are supplying it the signal. Okay, we shall see it later, but for now it is nothing but the smallest memory element. So remember it, flip-flop is the name of the smallest device which is able to hold only 1 bit. Either it could be 0 or 1. And interestingly, since it is able to hold 0 or 1, you should not say that it is capable of holding 2 bits. At any time, it can either hold 1 or it can either hold 0. Therefore, it has only 2 states. One is 0 state and other is 1 state. See this? It has 2 stable states. Stable states means it can be there forever. That is called stability. Now, it has 2 stable states which is known as 0 or 1. So, when it is holding 1, you can call it as it is in 1 state. If it is holding 0, you can call it as it is holding 0 state. So it is called as bistable multi-vibrator. It is also called as bistable. Bi means two stable multi-vibrator. Vibrator means it will move from one state to the other state. Now how are we able to actually store the bits inside the electronic circuit? That is interesting, right? Now we are able to store it as well as we are able to modify it, and we can let it be there forever, right? So how is it being done? So let's see, I'll just give you the basic idea, the building block. See, in order to build the memory like RAM, see, ROM is different. I'm talking about RAM, random access memory. In order to build such a memory which is readable and writable, we need the smallest element which is called as flip-flop. And now in order to build the flip-flop, we need even to know what is the basic concept used in inside the flip-flop so that it can save a bit. The basic concept used is this one. This is the circuit which is used. So generally it is shown as the NAND gate, right? So we use both NAND gates as well as NOR gates in the implementation of flip-flops. Even you could use AND gate and OR gate also. The reason is, NAND gate and NOR gate are functionally complete. If you are using NAND gate, you can use AND gate and NOT gate, isn't it? Therefore, you can use any gate as long as they are functionally complete to build the flip-flops. But then here I am going to use NAND gates because they are most frequently used gates. And this is the building block which will actually build a flip-flop. See this? Now, how is it going to store a bit is, assume that the output of this gate, let me say this gate is G1 and this gate is G2, and let me say the output of this one is Q and the output of this one is Q prime. Why Q prime? I'm just guessing that whatever output is produced by this one, the complement of it will be produced by this one. I don't know, I'm just guessing it. That is my assumption. Let me see if I'm right or wrong. And now assume that the value that will come to this point and this point is a1 and a2, and it is very clear that a2 is nothing but equal to q and a1 is nothing but equal to q prime, isn't it? So I don't know what these values are and I don't know what is the present value of it. I'm just assuming that if there is some value here, then here it must be a complement of it, just my assumption. Now let me test whether I am right or wrong. Let me say I don't know how the value got here. I'm assuming that the value here is 1. I don't know how it got there at the first place. I'm not interested in. Okay. Now if it is 1, then tell me what will be the value at a2. a2 will be 1, isn't it? Now when a2 equal to 1, then what is this? NAND gate is taking only one input, which is nothing but NOT gate. So this is as good as a NOT. So 1 is given to a NOT gate, and what will the output? It will be 0, right? And now this 0 is present at q prime, right? So I think it is agreeing with what I assumed, right? My assumption was that if there is 1 here, I might get a 0 here, so I am right. I think it is agreeing with my assumption. And now I'll take a 0 here, then what happens? The 0 is going to be present here, right? Therefore 0 will be complemented and I'll get 1. Wow, again I get 1, and again this 1 will be here, and again I get 0, and again I get a 0 here, and it will be giving me 1, right? Therefore this element is going to remain in this state forever. So forever. But then there is a small problem here. When I say forever, the assumption is that there is no signal loss because of the resistance, but then because of this electrical wires and the electrical wires inside it, there will be resistance, and so this 1 might slowly die, isn't it? So after some time this 1 might slowly die, and it might become 0 and it might become 0, right? That could happen. So as long as the signal is strong, this is going to maintain this state forever, as long as the signal is strong. So observe this. Now if you see this, we are able to store 1 bit here. You might think that we are able to store 2 bits. Why? Here there is 1 and here there is 0. No, if we are able to store 2 bits, I should be able to store every possible 2 bits, right? I'll be able to store only 1 0 or 0 1. Whatever is here, I'll be able to store its complement only. I'll not be able to store 1 1 or 0 0. Therefore it is not storing 2 bits actually, it is only storing 1 bit, right? And now and the second point is this bit, whichever is there, will not change until you change it. But then here there is no way I can change it, because it is all inside one circuit and no input is given, or there is no facility given to the user in order to change the inputs. Therefore it is called as latch. Latch means lock. It is also called as lock or latch. Latch means the bit whichever is there is locked. See, on the other hand, just assume this, if there would have been 0 here, just say what happens. If there is a 0 here, then the value here will be 0, and therefore the value here will be 1. Again it is agreeing with our assumption that whatever bit is here, its complement is there, and now this 1 will be here, right? And therefore it will be complemented, and again I get 0, and again 0 will be here, it will be complemented, I get 1, right? And now this circuit is actually latching 0. So either it could latch 1 or it could latch 0. That is up to you. But then once it is there, we are not really able to change it. That is called as latching. Now I want a memory device which I should be able to latch it, which means I should be able to store something there, as well as I want to change it, right? And that is called as flip-flop. Now the difference between latch and a flip-flop is, this is latch. Using latch we can build a flip-flop. What does it mean? The user should be able to change its value, and the user should be able to save it forever. If I can give such facilities to the user, which means somehow if I can provide a facility through which you can give some input, and once you give the input it can get into the latch mode, then it will be useful, right? That is called as flip-flop. Now let's see the flip-flops one by one. There are lots of flip-flops. Let's see them one by one. Now what happens with this SR flip-flop or any flip-flop in general is, because of the external disturbances, whenever there is noise outside, the input signals will suddenly fluctuate, and because of that fluctuation the output will change, and sometimes the output will change and will remain there, right? So what we are supposed to do is, we should make the inputs work only during some time, and we should not let it change during the other time. So what I mean to say is, so already you know what SR flip-flop is. Just now we have seen it, SR, right? and to that I am going to apply a signal called as clock. A clock looks like this. Clock is nothing but it will vary between 0 and 1. For some time it will be 0, for some time it will be 1, for some time it will be 0, for some time it will be 1. It is called as a clock, right? And depending on the frequency, this is called the time period. So one clock is nothing but this, right? It is nothing but the time period. And now what does it mean is, what is the advantage of having a clock to this SR flip-flop is, now whenever the clock is 0, see this, whenever the clock is 0, whatever you give at S and R, they are not going to be taken, and the output is going to be 1 and 1 here. And as you know, output whenever it is going to be 1 and 1, it is as good as SR are going to be 0 and 0, isn't it? So when did we get here 1 and 1? Whenever SR and R are 0 and 0. Therefore, whenever clock is 0, here I am going to get 1 and 1, because anything ANDed with the AND gate is going to be 1, right? So it is 0 here, and anything ANDed with the 0 in the AND gate is going to be 0, and complement is 1. So understand this, whenever clock is 0, here we are going to get 1 and 1 irrespective of what is present in S and R. Therefore, it is as good as in the normal SR giving 0 and 0 here, right? So what happens in the normal SR if you give 0 and 0? That is nothing but the if you give 0 and 0 in the normal SR, it is nothing but 1 and 1 here, right? So what is 0 and 0? That is latch mode. So whenever the clock is 0 0 in this particular flip-flop, right? So we are actually latching the output there. So it acts as a latch. So nothing will change as long as clock is 0. And whenever you want the output to change, or the bit values present there to change, depending on the S and R, you are supposed to give 1 here, right? So only during this phase, right, your output is going to respond to the inputs. Otherwise, it is not going to change. So only for this particular diagram, this particular SR flip-flop, this mode 0, it is called as latch mode, and this part is called as transparent mode. Transparent mode means output will depend on the input, right? So latching mode and transparent mode. So whenever your output is going to depend on input, that is called transparent mode, and whenever it is not going to depend on input, it is called as latch mode. So there are various ways you can use the clock. Sometimes what you could do is, instead of giving it a positive, this is called as positive edge. See, now in this clock, this part is called as positive edge, and this part is called as negative edge, right? So instead of calling it as edge, let's call it level. This part is called as positive level, this part is called as negative level, and see this, whenever there is a edge, this is called as edge, right? This is called as edge, and this is called an edge, and this edge is going from 0 to 1, that is why it is called as positive edge, and this edge is going from 1 to 0, that is why it is called as negative edge. So understand this, this is called as positive level, and this is called as negative level, and this is called as positive edge, and this is called as negative edge, right? So there are various ways we can see that a flip-flop will be activated only during positive level or only during negative level, or sometimes we can even design the circuit in such a way that they are called as master slave flip-flops. I am not going to show that because it is just a waste of time, but then we can design it in such a way that even your flip-flops are going to behave or going to take the input only during the edge time, which means very less time. So whenever this edge is there, only during that time your flip-flops will take the input, and all the other time it is going to be in latch mode, right? So what is the advantage of having this clock? See this, now your output will depend on the input only for some part of time, and for the remaining part it will not depend on it. So see this, depending on this, there are some questions like this. If this diagram is showing positive level triggered, it is also called as positive level triggered flip-flop. The reason is the flip-flop is going to be triggered only when there is a positive edge, right? So positive level triggered says that only during this time you are going to react to the inputs, otherwise we are not going to react it. And negative level triggered says that only during this time they will react to the input, otherwise they are not going to react. They are not interesting, but then the interesting fact is the edge triggered. Edge triggered says that if I have an edge like this, right, if I have a positive edge triggered, it says that only during this time, small part of time during the entire clock, only during this time the output will depend on input, and all the other time it will be irrespective of the input. Then what happens is, what is the advantage of that is, only during this time the flip-flop is open and all the remaining time it is closed. Closed in the sense, whatever you give, even if there are disturbances outside, it will not react at all. Therefore, it has very less effect by the noise outside. Since it is closed for most of the time and there is only one point at which you can give the input and change the output, if you can guard only that point and only that point, if you give the input, you need not worry about the remaining time. Even if there is external disturbance, it will not react at all. That is why most popular flip-flops are edge triggered. Edge triggered means they will not change all the time. Only when you give them some particular edge, they are going to be triggered, right? So this is nothing but positive edge triggered. And what is negative edge triggered is, if I have the clock, only during a negative edge it will react. Only during this part, small part of time, whatever is the input, to that input it will react, and the remaining time it will not react at all. So depending on that, we can classify flip-flops to be 4 types. I'll take examples and show you, but then just understand here, we have 4 types of flip-flops depending on the triggering. It is called triggered. The terminology is like this: TRIGGRED, triggered. So triggered means how are we going to enable the flip-flop, right? And this one is called as positive level triggered, this diagram, right? Now depending like this, we can have negative level as well as positive edge as well as negative edge. So in exam, they'll just give the diagram and they'll not tell you what the triggering used is. So from the diagram, you should be able to find it out. See this? Now whenever this is the block diagram, generally they represent it like this, flip-flop. Now it is SR flip-flop with a clock, and the clock is a straight line with nothing there. Then it is nothing but positive level triggered, which means this one is what they are talking about. And here the output will change only when the clock is positive level, otherwise it will not change, right? Otherwise it will be in latch mode. Now it is called negative edge. Whenever there is a negative edge, it will have an arrow. So whenever you see arrow, understand that it is negative edge. So only during a negative edge, the flip-flop will be in transparent mode, and in the other way it is a latch mode. And this one is called as, there is a bubble here, right? This one there is a bubble, therefore it is negative level. So this is a negative edge and it is negative level, sorry. So bubble means negative level, so this is positive level, bubble means negative level, and this arrow means the edge. So what is edge is this one, this edge. This is nothing but positive edge, right? And here positive level means this part, the center part is positive level. Here negative level means this part, the center part is negative level, right? And this one is negative edge. Negative edge is nothing but this part is negative edge, right? Therefore there are 4 types. One is positive level, other is negative level, and other is positive edge, and other is negative edge. So how can you find that out? Whenever there is arrow, it is edge. So whenever there is a bubble, it is negative, right? This is positive edge, and then it is negative level, sorry, positive level, negative level, and positive edge and negative edge, right? I'll take the examples and I'll show you for each one of them how does the output vary depending on the input. Okay, I'll just show you now. Now let's see how the positive edge triggered SR flip-flop will react to the inputs. So what do you mean by positive? Okay, it is not positive edge. Let's talk about positive level first. Positive level, that will be easy. Let's go step by step. Edge will be confusing you. Let's take positive edge first, positive level first. Now positive level means in this is the clock. Clock is 0, 1, 0, 1, 0, right? So what is the positive level here? This part. So this part is going to be transparent mode, which means only during this part our flip-flop is going to react, and this part is going to be latch mode. So latch mode is nothing but the flip-flop is going to have whatever value it already had, so it is not going to change. So this is transparent mode and this is latch mode, which means transparent mode means we are going to react, and latch mode means we don't react to input, right? So see this. Now this is the S signal. S means the S and R, you know that. So it is SR flip-flop, right? So actually in SR flip-flop, what is S and R is? S means set, R means reset. The reason is whenever S is 1, output is always going to be 1, and whenever R is 0, R is 1, output is always going to be 0. Set and reset. And whenever both are 0, 0, output is going to be in the latch mode, right? That is why SR name is given, like understood that? Set and reset. Okay. Now watch this. First thing is, the input S is going to be 1 for a long time, and suddenly it is dropped down to 0, and again it is going to be 1, and again it is dropping down to 0, and then it is remaining like that, right? And R is, it is suddenly going like this and then raising up, and then from 0 it is raising up to 1 and again dropping down and again raising up to 1 and again going like this. Now if this is the scenario, then how does the output change? Let's see this. Let's see how does the output behave. First thing is, I don't know what is the present state of the output, so I am assuming that the output is present at a 0 level. So this is Q. Q is the output, right? And we know that this is latch mode. Latch mode means as long as the clock is at level 0, negative level, that 0 level or negative level. Now as long as it is at negative level latch mode, we are going to see the same output. Therefore Q is going to be constant. And now once we reach this, it is the transparent mode, right? So at this transparent mode, depending on the inputs, the output should react. Now what is the input? Input is 1 0, right? So what is 1 0? 1 0 means set. Therefore output should be 1. Therefore at this point output is going to become 1, and it is going to be 1 till the point where SR are showing 1 0. This is 1, this is 0. Therefore 1 0 is nothing but output is 1. Why? It is set mode, right? And now suddenly at this point if you observe it, at this point S is 0 and R is 1, which means now it is 0 1, right? So whenever S is 0 and R is 1, it should reset. So definitely it is going to drop down and it is going to be 0. And suddenly at this point again the input is changing, and since everything is happening in the transparent mode, you are supposed to react, right? So your reaction will be like this. See, now it is again 1 0, which is nothing but set. Therefore it is going to be 1, right? And it is going to be here. Now till this part, see how the reaction is. Only during the transparent mode our output is going to follow the input, which means whatever input is saying we are going to take it. Initially it is 1 0, therefore it is set, which is 1. Then it is 0 1, therefore it is reset, which is 0. Then again it raised to 1 0, therefore it is again set, which is 1, right? And now after that this is completely latch mode. In latch mode, whatever is the output previously, which is nothing but 1, that will continue continuous till here, right? And again we are entering the transparent mode, and whenever they are transparent mode, we are supposed to listen to the input and then check it, right? So see this. Now it is going to be 0, it is going to be 1. Then what is 0 1? 0 1 is nothing but 0, therefore it falls to 0, right? And now in this latch mode it is going to continue like this. Got it? So that is how we can obtain the output. So what they could ask you in the exam is how many times the input has changed, or how many times the output has changed, right? They will give you this and they will ask you how many times the output has changed, or they will say that at this point of time, at some point of time, what is the input. They will ask you like that. Some questions will be like that. And now if you observe it, one of the advantages of having the clock is like this. If it is a positive level clock, right, then what happens is sometimes one input will arrive very early, right, and sometimes the other input will arrive late, right? Then see, this input has arrived very early and the other input has arrived very late, but then both of them are going to wait till the transparent mode, then only both of them are going to react. So whenever you have uneven delays, if you have to make one signal wait for the other signal before you apply it to the flip-flop, then you can have it as some level triggered or edge triggered, so that only by that point both the signals will arrive, and simultaneously at that point we are going to look at it. Now this is how it works. Let's see how the edge triggering works. For the same example we shall see it. Let's watch this. Instead of this positive level, now let's see what happens if it is positive edge. Positive edge means now the transparent mode and latch mode will change. So what are the positive edges? Whenever you are changing from 0 to 1, this is positive edge, this is a positive edge, and this is negative edge, this is positive edge, this is negative edge, right? So only during this part is transparent mode now, and all the rest is latch mode, and only these two parts. Even though I am writing it as a big cycle, this entire part is not the transparent mode, only that particular line, one single line, that is a dot in the line, right? That is a dot in the timeline. Only for that small duration of time our flip-flop will enter into transparent mode and it will react to inputs, and suddenly it will come out of it and will not react. So what is the advantage of this is, only for small part, that small window of opportunity, you are going to react to the inputs. So even if there is a lot of disturbance, you need not worry about it, because your flip-flop is not going to react to the disturbance outside the transparent mode, and the chances are that the disturbance will affect only that point is very, very less. You know that, right? Probability of a point in a continuous uniform distribution is 0, right? Now these two are transparent modes. So only during this time our output is going to see the spun, what is the input, and then it is going to change, and other times it is just not going to change. Let us assume that it is 0 first Q, so Q is at level 0, and by this time we reach this point, right? It is nothing but S is 1 and R is 0, so 1 0 is given. Then what will be the output? Output will be 1. So exactly at this point output will be 1, and immediately it will enter into latch mode and it will continue. So only this part is transparent mode and all the other parts are actually latch modes, and everything else is latch mode. Only other than this whatever I have written, only these boxes are transparent mode, right? And now what about this? It is latch mode only, so it will continuously not change. And again at this point it is transparent mode, therefore at this point it will check the inputs. So what is the input here? So input is 0 1, so whenever it is 0 we know that it will fall down to 0, right? And again it will go like this in the latch mode. So this is the output produced if our flip-flop is positive edge triggered. So I have given you the example of positive level triggered, but then I didn't give you any example of how to build the positive edge triggered, because it is not required. There is something called as master slave flip-flop. You need not worry about it because that is not required. In case if I have time at the end I will do it, but then it is not required, leave it, okay? So in the exam they will give you this that it is a positive edge, and then they will give you such question and then they will ask you, right? So you can know about it. This is how positive level works. And you can even do the same for the negative level also. If you want to do it, negative level also works the same, isn't it? So in negative level this part is transparent mode and this part is transparent mode, and the other parts are simply latch mode. Therefore what happens is Q, till we reach this point, where is it? This point, till we reach this point Q will be constant latch mode, and once we reach this point then Q will check this input. So it is nothing but 1 0. So what is 1 0? Set. Therefore at this point it will keep on setting, and again till it reaches this point it is going to be in latch mode, and once it reaches this again it will check the input. So what does the input say? 0 1. 0 1 is nothing but reset, which is nothing but it will again go like this, right? So this is how we can think about it. So positive edge means this one, right? It is the next one is negative edge, right? Negative edge. So depending on this you can solve all the equations. Anyway, we shall see about this how to work on these clocks later again with some other example. This example is enough here. See this is same as JK is same as SR flip-flop with J equal to S and K equal to R, which means it's exactly going to behave as if it is a SR flip-flop. Only one difference is, in SR if you remember it, we didn't define the this SR for 1 1, which means we didn't say what happens if S and R are 1 1. But in JK we are even going to define what happens when J and K are 1 and 1. So what happens is, when J and K are 1 and 1, the flip-flop performs the complementation. So whatever is the actual present state there, it is going to complement it. Okay, I'll take the function table and explain you. How does it function is, this is the function table. JK, it is going to behave exactly like SR. 0 0, then what is going to be next state Qn plus 1 is, it is going to be latching, which means whatever is the earlier state, which is Qn. If it is 1 0, it is going to set. So 1 0 means you know that, right? In SR what is 1 0? It is set mode. Therefore it is going to be set mode, which means output is going to be 1. And what about 0 1? It is going to be reset mode in SR. Therefore it is going to be 0, right? And only difference is 1 1. 1 1 is not defined for SR, but for JK 1 1 is defined, and in fact it is defined as if it is going to complement it, which means it is going to say Qn prime, right? So this is what is the function table of this. This is how JK is going to behave. It is going to behave exactly the same way as SR for these three chances, and for the last one, whenever JK is 1 1, it is going to behave differently from SR and is going to just complement it. Now let's see what is the characteristic table and then construct the characteristic equation and then try to realize it. Now characteristic table is like this: J, K, Qn. If these three are the inputs, what is Qn plus 1? Characteristic table, right? I want to find it out. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, right? Let me divide it depending on J and K, right? Okay, now see this. Whenever J and K are 0 0, it is nothing but S and R are 0 0, which is nothing but latch mode. So what is latch mode? Qn plus 1 is equal to Qn. So whatever is here, I am going to write it. And whenever we have 0 1, it is nothing but SR or 0 1, which is nothing but reset mode. Reset mode is independent of Qn, we are going to write 0 0, right? And whenever J and K are 1 0, right, which is nothing but the set mode, by S and R are 1 0, right? Therefore, independent of the present state, we are going to have 1 1 here. And this is interesting. So whenever J and K are 1 1, S and R are 1 1, but for SR it is not defined, but only difference is for J and K we are going to define it. So we are going to define it as if it is complementing. Complementing means 1 0, right? This is the characteristic equation, table. And now from this we shall construct the characteristic equation and then we shall realize it. Let's minimize it. Let's find out the characteristic equation here. So Qn plus 1 is a function of J, K and Qn. 0 0 0 1 1 1 1 0 0 1. Now check this. Whenever Qn plus 1 is 1, so where is it 1? 0 0 1. So where is it? It is 0 0 1 is here, right? And again here. So what is it? 1 0 0. So 1 0 0 is here. And again 1 is here. So what is it? 1 0 1. 1 0 1 is here. And again it is here. So what is it? 1 1 0. So 1 1 0 is here, right? Isn't it? Yeah. Now let's see. Let me check it. So here it is 1, which means 0 0 1. Yeah, 0 0 1. And here it is 1, which means 1 0 0 1 0 0. Yes, right. And here it is 1, which means 1 0 1. Yeah, 1 0 0 is yes here, and then 1 0 1 is here, and then this one is 1 1 0. Yes, fine. Now let me minimize it. So how can we minimize? Find out the prime implicants. One prime implicant is this, another prime implicant is this, another prime implicant is this, right? So we have 3 prime implicants, out of which 2 are essential. This one is essential and this one is essential. The reason is they are covering a 1 which is not covered by others. Now if you pick up these 2 essential prime implicants, this one will become redundant, that is not required, right? Therefore you can write it as Qn plus 1 equal to, why? Because this one, right? Qn plus 1 equal to, what about these 2? It is nothing but J and then Qn prime plus 1 prime implicant plus the second prime implicant. Now if you look at the second prime implicant, in these 2 it is nothing but K complement K prime, in these 2 it is K prime into Qn, right? So this is the characteristic function for the JK flip-flop. Now we can realize it easily, right? So what is it? It is nothing but sum of AND terms, right? So you can take 2 AND gates like this, right? And then it is sum of OR terms, therefore I am going to have a OR gate like this, fine. And now one input is going to be J, okay, let me put J inside, okay, fine. So one input is going to be J, okay, another input is going to be K prime, which means I am going to take this K, so K prime. And now this other input is going to be Qn prime and Qn. So for this one is going to be Qn prime, another is going to be Qn. So from here I am going to get this signal, which is nothing but Qn and I'm going to give it to this, which is nothing but Qn prime, and other one is Qn, right? Therefore this is Qn prime and this is Qn, right? So this is how we can realize the JK flip-flop. Understood this? So these three gates are required to realize the JK flip-flop, right? So that is how we constructed it. So only difference between SR and JK is this last state, right? Whenever it is 1 and 1, we are going to complement it. Let's see the excitation table. So what is excitation table? When we want to change the output from one state to the other state, then what should be the corresponding inputs given? Qn plus 1, which means if I am here and if I want to it is called excitation table, okay? Now if I am 0, I want to change it to 0, or if I will be in 1, 0, I want to change it to 1, or if I am in one state, I want to change it to 0, or if I am one state, I want to make it as 1 itself. Then what are the corresponding J and K inputs so that you will achieve this? Now watch this one, J and K. See, 0 to 0. So 0 to 0 is, we get 0 to 0 here as well as here, isn't it? 0 to 0 and 0 to 0. Check this, only at two places we are going to get this one, right? So now see this, it is going to be either JK are going to be 0 0 or 0 1, which is nothing but 0 and don't care. Just like SR, we got 0 and don't care. Why do you think that we got this? So when I am in 0 0, it is nothing but latch mode, so 0 is going to remain as 0, and when I am in 0 1, it is nothing but reset mode. Whatever it is here, I am going to get 0 anyway, right? And here lucky that here already there is 0, therefore I am getting, so you make J as 0, you need not worry about anything, right? K is not required there. And next one is 0 to 1. So see this, when are you going to change it to 0 to 1? Here, here and here, here, right? Now check this. So when we can change it to 0 1, either it is J and K are 1 0 or J and K are 1 1. So what does it mean? Either you set it, you are going to get as 1, or you complement it, you are going to get as 1. Therefore it is nothing but 1 and don't care. Understood this? Either you set the flip-flop, you are going to get 1, because setting is nothing but output is 1, or you complement it. Complementing means whatever is there already, you can complement it by using 1 1, right? And next one is 1 to 0. So how can I change from 1 to 0 here, right? So this is 1 to 0 and this is 1 to 0, right? Check this, either you give 0 1 or you give 1 1, which is nothing but don't care and 1. Don't care and 1. What is the meaning of this? If we, it says that if you have to get an output as 0, either you reset it or complement it, right? So for resetting, you know that it is 0 1, and for complementing 1 1, that is why we got it. And what about 1 1? You can guess it at least now. So 1 1 is nothing but latching. So what is latching? 0 0, or 1 1 is nothing but setting. What is setting? 1 0. Therefore we get don't care and 0. Or if you didn't understand it, just check this one. Now where is 1 1? 1 1 is here, right? 1 1 is here and then here, right? So which means either it is going to be 0 0 or 1 0. Therefore it is don't care and 0. Don't care and 0. What does it mean? If you want the output to be 1, either you set it to 1, which means 1 0, or you leave it as 1, which is already present in the input, which means latch mode 0 0. So this is called the excitation table. This is the excitation table for JK flip-flop. Got it? Maybe you can even sometimes they will even give you the state diagram. So let's see the state diagram. So what is state diagram is, I'll just tell you what are the two states for the flip-flop. I already told you that every flip-flop is going to have two states. One state is 0, other state is 1, because it is either going to carry a 0 or it is going to carry a 1, right? So one state is either going to be 0 and other state is going to be 1, right? Now let's see what are the various combinations for JK, all the other combinations, right? Let's see what happens if I get each combination. If I am initial state is, as in initial state can be either 1 or 0, I don't care. Now as long as I see 0 0, I'll be in the same state, isn't it? And similarly here also, as long as I see 0 0, I'll be in same state. Why? It is latch mode, right? Or now in this state, if I see a 0 1, I'll be in the same state. Why? Because if I see a 0 1, okay, see, How you could do it is, from the excitation table itself you can take it and fill it, but then don't worry, I'll just explain it here. See, if you are in state 0, if you see a 0 1, then you are going to be in the same state because it is reset, right? And if you are in state 1, if you see 1 0, you are going to be in same state because it is set is nothing but again is going to set it as 1, right? And now if you are in state 0 and if you see 1 0, you are going to go to state 1 because it is going to set it. And if you are in state 1, if you see 0 1, you are going to come back, right, which is nothing but reset, isn't it? And did we miss out any other inputs? I think these are the inputs. So in every state we can get any of the 4 inputs. One input is 0 0, one input is 0 1, other input is 1 0, other input is 1 1. So what happens to 1 1? 1 1 is also complementation, right? So 0, it is going to be here, right? And here also we are supposed to get 4 inputs. What are the 4 inputs in this state? Either you get 0 0 or 1 0 or 0 1 or 1 1, right? So if you get a 1 1, it is going to be complementation, right? Now this is nothing but the state diagram. So understood this? So first one is I have drawn here, I erased it, function table, and then characteristic table, and then characteristic equation, I minimized it, and then realization, right? And then excitation table. Excitation table is if I have to go from one to other, what is the inputs, right? And then finally this is the state diagram. So you can draw them in any order, no problem, as long as you should be able to do it. So in the exam they can give you any one of them, and then they will ask you what happens with this, what happens with that, like that. Okay. There are 2 interesting variants of JK. Let's see them. Let us assume that this is a JK flip-flop. Okay, JK, and maybe some clock triggered, I don't care, Q and Q prime, right? And assume that I'm going to combine JK together, right? And I'm going to give it a single input. Then what happens? Either J and K both are going to be same 0 0, or J and K both are going to be 1 1, right? Then let's see the behavior of this. So now we have only 2, let us say this is T, I'm calling this as T, right? Now let's see how does this one behaves. So we already know that now the input is single input, right? So now we already know that J and K are going to be here 0 0 or 1 1, right? So whenever T is 0, both are going to be 0 0, and whenever T is 1, both are going to be 1 1. So how does it function? The functional table is going to look like this. Now whenever T is 0, both are going to be 0 0, then what happens to the Qn plus 1? It is going to be in latch mode, which means whatever is previous state is going to show the same one. And whenever T is 1, both are going to be 1 1, then what happens? What is J and K 1? It is complementing, which means Qn plus 1 is Qn complement, right? This is the function table. Now how does the characteristic table look like? So what are the inputs now? One input is T and other input is Qn. Now how does this Qn plus 1 look like? Qn plus 1, 0 0, 0 1, 1 0, 1 1. Whenever T is 1, J and K are 0 0. Therefore Qn plus 1 is the same as Qn, which is 0. And whenever T is 0, then again J and K are 0 0. Therefore output is 1. What about T equal to 1? Whenever T equal to 1, we are going to get the complement of Qn, which is nothing but here it is 1 and here it is 0, right? So now I want to find out, this is the characteristic table. Now I want to find out the characteristic equation. I just want to minimize it. So what is Qn plus 1 here? Qn plus 1 is these 2 minterms, right? Which is nothing but T prime Qn plus T Qn prime, which is nothing but T exclusive OR Qn, right? How can we realize it? Using an exclusive OR gate. So I can have an exclusive OR gate, isn't it? And now I can give one input as T and the other input as Qn. This is it. So this is nothing but the T flip-flop, right? Understood this? Then what about the excitation table? What is the excitation table? If I am in Qn and if I want to change it to some other Qn plus 1, then what is the input that you are supposed to give? If I want to change it from 0 to 0, it is nothing but latch mode. So what is the latch mode here? Whenever T equal to 0. If I want to change it from 0 to 1, it is complementing, which means T equal to 1. And whenever I want to change it from 1 to 0, complementing, which is nothing but T equal to 1, right? and whenever I want to change it from 1 to 1, it is nothing but latch mode. Are you following it? How am I writing it? See, if you are not understanding how I am writing this one, I am just writing it from the characteristic table. See this? Whenever it is 0 to 0, it is nothing but 0. That is why t equal to 0. And whenever it is from 0 to 1, right, it is nothing but 1. That is why 1. And whenever it is 1 to 0, it is nothing but 1. That is why 1. And whenever it is 1 to 1, it is nothing but 0. Right? Got it? That is why I am writing this. Now, if you observe it, there are only two things. One is it is latching or it is complementing. That is why it is also called as toggle. Toggle flip-flop. Toggle flip-flop means it is just complementing or it is going to maintain the same thing. That complementing state is called as toggling, right? And what is the other important thing about this? So you could even construct the state diagram like this. See? Now what are the two states possible? Either you will be in state 0 or you will be in state 1. Now what are the inputs? Input is only one input, right? Two inputs. Either t can be 0 or t can be 1, right? Previously it is jk, two inputs, right? Now here it is either t can be 0 or t can be 1. So whenever t is 0, we are going to be in the same state. Whenever t is 1, I am going to complement it. And whenever t is 0, I am going to be in the same state. Whenever t is 1, I am going to the other state, right? So these inputs are nothing but t. In the previous example, in the jk state diagram, I have also given you like this, right? 0, 1, and then I have given you some transitions like this, right? Maybe 0, 1 or something like this. There 0, 1 means it is j and k, right? Don't get confused. There 0, 1 means j and k, and maybe I might have given you something like this. Here also 0, 0 means j is 0, k is 0. But since here we have only one input, I am talking about t. So t is going to behave like this. So it is nothing but the t flip-flop. This t flip-flop is very useful. Later I will show you where it is going to be useful. Okay. Now understand this. These are the functionalities of t flip-flop, right? One other modification to jk flip-flop is like this. Assume that is the jk flip-flop, and this is q and this is q prime. And if you connect both jk like this, so, and then you call it d, then it is going to act as a new flip-flop which is called as d flip-flop. So what is the main characteristic of this d flip-flop is, whenever you give 0 to j, the corresponding output on the k, the other corresponding input to k will be 1, and whenever you give 1 to j, the corresponding input to the k will be 0, which means j and k can now take only two possibilities. Even though there are four possibilities possible, but by connecting like this, it can take only two. See, if you remember in t flip-flop, the toggle flip-flop, even though j and k can take four possibilities, by connecting both of them, we restricted it to use only two combinations, right? What are they? 0, 0, 1, 1. And similarly here also we can restrict j and k to represent to use only two combinations. One is 0, 1, other is 1, 0. So watch this. Now what happens, how does it behave is, the functional table is like this. Now whenever d and qn plus 1, whenever d is 0, then what happens, j and k is 0, 1. So whenever j and k is 0, 1, the same state is maintained, isn't it? Or in fact it is going to be 0, sorry. So whenever j and k is 0, 1, it is reset, which is nothing but 0. And whenever d equal to 1, then j is 1 and k is 0, right? Okay, if you are not understanding it, see this. Whenever d equal to 0, then what happens? J equal to 1, j equal to 0 and k equal to 1. Which is what is this? Please keep that jk table beside you and then refer to it. Whenever I told you that j and k are 0, 1, it is nothing but the reset. Reset means the output should be 0. That is why it is 0, right? And whenever d equal to 1, what happens to j and k? J is going to be 1 and k is going to be 0. So what is this? It is nothing but the set state, right? So whenever it is 1, output is going to be 1. You please refer to jk characteristic table, then you will understand what is happening there. Okay. Now that is the characteristic table, sorry, functional table. Now let's write the characteristic table and then find out the characteristic equation and then excitation table also. Now characteristic table is like this. If input is d and already existing state is dn, then what is the next state? Qn plus 1. So 0, 0, 0, 1, 1, 0, 1, 1. If input is d and qn is 0, then what is the output state? So input is 0 means J and K both are J and K are 0 1, isn't it? Input is D means J and K are 0 1, right? So whenever J and K are 0 1, what happens? It is always that we are going to get output as 0, therefore it is 0. And again here D is 0, therefore J and K are 0 1. So whatever is Qn, I don't care, output is going to be 0, right? And what about this? D equal to 1. Whenever D equal to 1, J and K are 1 0, which is nothing but the set state. Therefore whatever is the present state, we are always going to get 1. And again here also same. Whenever D equal to 1, J and K are going to be 1 0, and therefore it is going to set, right? Now I want to find out the characteristic equation. What is the output in terms of the input? So if you watch it, Qn plus 1 is like this. Qn plus 1 is having two minterms. One minterm is this and other minterm is this. Only because here and here we have 1 and 1, right? Then what do we get? D Qn prime plus D Qn, right? Then I pull out D. Then what do I get? Qn prime plus Qn, right? Then what is it? D. Therefore Qn prime is simply D. Sorry, Qn plus 1 is simply D. So it is very, very interesting. Till now we didn't get anything like this, right? So output is directly depending on the input. There is no need of memory element at all. There is no feedbacking. See, sometimes that is also called as feedbacking. If the output is depending on the input as well as the previous output, that previous output is nothing but the feedbacking, right? So here there is no need of it at all, which means if you give some D as input, then it will wait for some time and then it will give the same one as output. This is called as delay. It is also called as buffer. So buffer is going to introduce some delay. That is why it is called as D flip-flop. Interesting, right? So why is it called D flip-flop? Is whatever you are giving at the input, the same thing is going to be shown at the output after some delay. That is why it is also called as delay flip-flop, and it has got lots of applications, right? So one application is this. Sometimes there will be uneven propagation delays, which means sometimes what happens is, I told you this, there are some struck gate errors, right? So there will be a NOT gate here, and the NOT gate will be delaying the signal for some time, and there will be a straight line here, and straight line will be giving the signal directly. Now if you want the input to arrive at this gate at the same time, then you could delay the bit here, right? And likewise there are various examples, various applications. We shall see all those examples, but this is how it could be used, which means it is used to delay sometimes some bits. Maybe in computer networks also, if you remember it, I told you about the token ring. In token ring we wanted to see that some bits are delayed at least for some time, otherwise the minimum size of the token ring is not going to be sufficient, right? Then what we do is we are going to introduce a delay device, that is nothing but the delay device, D flip-flop here, okay? And now this is about the equation. Yes, this is the characteristic equation. Characteristic equation is what? Qn plus 1 equal to D. Now let's see what is the excitation table and then the state diagram. Okay, let's see the state diagram here. There are only two states, one is 0 and other is 1, and there are two inputs for D. So D can be either 0 or D can be either 1. If D is 0, output is always going to be 0. If D is 1, output is going to be 1. Similarly, if D is 1, output is always going to be 1, and if D is 0, output is going to be 0. Got it? And now what about the excitation table? The excitation table is like this: Qn plus 1, which means and then what is D. So if I want to change it from 0 to 0, 0 to 1, 1 to 0, 1 to 1, what are the inputs that should be given? Which means if I want to change a 0 to 0 or 0 to 1 or 1 to 0 or 1 to 1, what are the inputs that I give at D? So this, we already know that output depends on what the input we are going to give at D. Therefore it is going to be 0 1 0 1, right? So this is the excitation table. If you didn't understand how I got it, maybe you can look at this and you can see it. See this? I hope that you understood it, because after these many examples you should understand. Okay, anyway, let me not take any guess. Maybe someone might not understand it. I don't want to take any chances here. See, now we know that it is from 0 to 0. Therefore you go to the table where you see 0 to 0. So in order to get 0 to 0, what is the D? 0. That is why it is 0, right? And 0 to 1. So see this, 0 to 1, if you have to get this, then the Qn has to be 0, right? That is why it is O. 0 to 0, 0 to 1, right? Yes, 0 to 1 is where? Here. 0 to 1, therefore D has to be 1, right? And then 1 to 0, 1 to 0 is this, 1 to 0, D has to be 0, that is why D is 0. And 1 to 1, right, sorry, 1 to 1, so therefore D has to be 1, therefore D is 1. So that is how we could write the excitation table. So this is all about the D flip-flop. Later we are going to use D in various applications. I'll show you all that. D and T are very important when we go to the counters. Let me not confuse you now. Let's just stick to the flip-flops. Later I'll show you what counters are and why we are using these flip-flops. Okay. Now they'll give us one flip-flop and they'll ask us to convert to other flip-flop. Why is this useful is, generally we don't manufacture all the flip-flops possible. We manufacture one flip-flop and then we try to convert it to other ones, right? So one way to do it is, first thing is, conversion of a given flip-flop to other flip-flop is like this. So if you want to understand it better, see this. Let us say there is a given flip-flop and which is having, let's call it as AB flip-flop, right? And now I want to use this and I want to convert it as some other flip-flop which will take CD, and these are the outputs, right? So I want to convert it to CD. So inside it there is AB and I want to convert it to CD. Then what I should do is, I should be able to express A and B in terms of C, D and the output. Then it is done, isn't it? Therefore in the middle I am supposed to put a combinational circuit, right? Some combinational circuit in such a way that A will be expressed as a function of C as well as D, and B will be expressed as a function of C as well as D. Therefore for outside it looks as if it is just CD, and internally if you want the behavior of the CD flip-flop, the corresponding changes are made here and then the input is given to A and B. Therefore in such a way that A and B will behave now as the CD, right? So how to get that is, look at the steps. Get the characteristic table of the target one. So what is the target? C and D, right? So get the characteristic table. So if you write it, it will be like this: C, D, and then Q, and then Qn, isn't it? Then replace the Qn, which means you can replace this one, right? Replace the Qn with the excitation table of given flip-flop. What is the given flip-flop? AB. Therefore replace it with the excitation table of AB, right? And then what is that they are saying? Obtain the expression for the input of the given flip-flop and realize it, which means then you see this A and you see this function B and you express this in terms of CD and Q, right? What does it mean? Then you express A in terms of CD and Q, then you realize it, then that is nothing but the combination circuit which you are going to place it here, right? So that way you can implement it. So understood this? These three steps are simple. First one is target tables. No, you find out the characteristic table, target flip-flop, and next thing is replace the next state using excitation, right? And then obtain the expression for the input. So let's see this. I'll take an example and explain you. We have already converted, I think, JK to T flip-flop, right? So what is the main difference between JK and T flip-flop? In JK flip-flop, if you combine all the, like this, see this. Now if it is JK flip-flop, okay, here I have to convert a JK flip-flop to T flip-flop, right? So let's go in this method and just see it. It is very simple one. So first thing is you should write the characteristic table of the target one. So what is target? I want to manufacture a T flip-flop, right? So characteristic table is T, Qn, and then Qn plus 1. This is the characteristic table, right? And let me fill it out: 0, 0, 0, 1, 1, 0, 1, 1. Now what about T equal to 0? It is simply latch mode. And what about T equal to 1? It is simply this one, right? Complementing. And now you replace this this next state, right, with the excitation. So excitation table means this one, right? So how do you want to change from 0 to 0 in JK? So you know that in JK 0 to 0 can be changed either by staying in the same state or resetting it. So what is staying in the same state? So which is nothing but latching, which is 0, 0, or what is reset? Reset is 0, 1, right? Therefore it is 0 and don't care. What about this 1 to 1? 1 to 1 can also be done by staying in the same state, right, which means 1 0, or setting it is 1 0, right, staying in the same set is 0 0, setting it is 1 0. Then what do I get? I get don't care and 0, right? And what about 0 to 1? So in JK, if you remember it, how are you going to get 0 to 1? So 0 to 1 is either toggle or set. So what is toggle? 1 1, right? So I'm talking about this one, 0 to 1, which means toggle. Toggle means complementation, which is 1 1, or set. Set is nothing but 1 0. Then what is it? 1 and don't care, right? And what about this one? 1 0. So 1 to 0. So again it is toggle, which means 1 1, or reset. What is reset? 0 1, right? Then what is it? 5 and 1. Got it? So now we have to implement J and K in terms of these two, right? The reason is simple. Already we are given a JK flip-flop here. JK is given, and now I want to convert it into a T flip-flop. Then what should you put here? Which means J should be expressed as a function of T. J should take T as input as well as Q as input, and then it should implement it, right? It is Q and it is Q prime. So I want to fill the combination circuit here. That is why I'm doing everything, right? Now see this. What should be J? Now J is simply saying that it can be 0, don't care, and this. So if you want it, you can directly, maybe if you just want to simplify it, since there are don't cares. If you don't understand it, I'm directly doing it. If you don't understand it, you can actually simplify it using the K map. But drawing K map for two variables is really funny. You please do it. See, now J is nothing but, if I have this, if you look at it, right, if I put a 1 here, J will be equal to T, isn't it? Therefore J is directly equal to T. Okay, so let me do it then. I can't take any chances here. See, now I'm just simplifying J, right? So what is J? One is T, other is Qn, 0 0 0 1 1 0 1 1. These are the various combinations, right? 0 0 0 1, and then 1 0 and 1 1. Yes. Now see this, J is 1 at 1 0. So 1 0 is nothing but this one, right? And J is don't care at 0 1. 0 1 is this one, and J is don't care at 1 1, which means here, right? Then which one do you want to take? If you want to combine it, only way is this, right? Then what is it? J is equal to T, isn't it? Sorry, T is equal to, yeah, J is equal to T, right? Why? T equal to 1. And similarly, if you simplify this, right, you can see that how to simplify this again. Yeah, K, right? So K has to be expressed in terms of these two. If you look at it, it is going to be 1 here, and yes, and it is going to be 1 here, and it is going to be don't care. Let's just see this. So what is that you are supposed to get? You are supposed to get K equal to T prime, right? So it is T Qn 0 1 0 1, right? And just watch it. The 1 is, where is 1? It is don't care. Wait, I have written something wrong here. Okay, so it is don't care 1, this, and I think it is 1, right? Here it is 1. Now I can write the table here. It is 0 0, it is 0, and it is Q, T and Qn. It is T, it is Qn, it is 0 1 0 1. Now watch it. Now it is 1 at 1 1, which means here it is 1, and it is don't care at 1 0, which means it is don't care at here, and it is don't care at 0 0. So 0 0 is here, right? Now how can you combine it? So the only way to combine it is like this. Then what is that you are getting? K equal to T. Okay, K equal to T. Got it? So now both the T and K both are equal to K. Now both are equal to T. J and K both are equal to T, or like this, simply connecting them, right? Then what do you understand? So either J and K are going to be both 0 0, or both are going to be 1 1, which means either it is going to be in latch mode or toggle mode. That is how we got the T flip-flop. It is not very interesting, in the sense it is very simple, small one. Let's convert the reverse way, which means instead of converting a JK flip-flop to T, what if I want to convert T into JK? That will be interesting. Let's see this. I want to convert T flip-flop into JK. That one will be a bit interesting. So T to JK flip-flop, which means the given flip-flop is T. I have only one input T, and I have to construct a JK flip-flop here, right? Therefore, I have to express T in terms of J and K, right? T has to be expressed in terms of J and K, right? So what are the steps? Construct the characteristic table of the target flip-flop. So what is the target flip-flop I am aiming at? JK. Therefore, I am going to write target flip-flop characteristic table. So are you following this? Why am I writing characteristic in this one is because later I want to write T in terms of J and K. That is why T has to come here and J and K has to come here. If you ever get confused in the exam, just write this diagram and you will understand which table should I write here. You should write the JK table so that you can express T as a function of J and K. Then you have to write characteristic equation, characteristic table here, and then the excitation table here. Then you can write it in terms of that. Okay. Now see this 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, right? Okay. Now how does JK behave? Qn plus 1. In 0 0 it is simply latch mode, which means Qn will be there. And in 0 1, okay, you please do one thing. If you don't understand this, you open that T and then see the excitation table. I'm directly going to write it here, right? And now 0 1, what is 0 1? It is reset, which means 0 0. What is 1 0? It is set, which means 1 1. What about 1 1? It is toggle, which means 1 0, right? So this is Qn plus 1. Understood this? So 0 0 is same latch mode. That is why whatever is Qn I got it, and 0 1 is reset, therefore it is 0, and 1 0 is set, therefore it is 1 1, and 1 1 is toggle, therefore I got the complement. And now we are going to see what should be the excitation table for T. So how should the T table look like? If I have to go from 0 to 0 in T flip-flop, it is nothing but latch mode, right? So T has to be 0. What about this? T has to be 0. What about this? T has to be 0. Whenever you want to complement it, T has to toggle. Now again it is 1 to 1, therefore it is 0, right? And again 0 to 1 it is toggle, and again 1 to 0 it is toggle, right? Therefore whenever you want to change the state, we are going to toggle. That is why there we are going to put ones and all the others are going to be zeros. Now next thing is we have to realize, or we have to get the characteristic equation for the T, which means we have to see what should T be, this function, in terms of J, K and Q. The reason is we have to convert the T into this one, right? So now just simplify it. 1 2 3. So one is JK and other is Qn. 0 0 0 1 1 1 1 0 0 1. Okay, now look at this one. This is 0 1 1. So where is 0 1 1? Yes, and this one is 1 0 0. So 1 0 0, and this one is 1 1 0. 1 1 0 is here, right? And this one is 1 1 1. 1 1 1 is this, right? Therefore I got two prime implicants, in fact 3, but one is redundant. These two are essential, but this one is redundant, right? Now how can you write it? Now T equal to, watch it, T equal to what about this prime implicant? It is Qn prime, and then what is it? J. So it is J Qn prime. J Qn prime, right? Plus, what about this one? This one is where is it? Yes, Qn and then K Qn. Check it. Check this once. So this one is this one, right? I'm talking about this one. Yes, it is K and then Qn, and then this one is q prime, yes, q prime and then j, yes, fine. So that is what we got. Now what is that we should do? I should put the combinational circuit before this flip-flop, therefore I can convert the t into jk. So I have the t given already, t is there and it is q and it is q prime, right? And now I want to convert it into j and k, therefore j is here and k is here outside. Now see this, t equal to j into qn prime, which means I need a OR gate. It is the sum of products, right? I need a OR gate to which two AND gates are going to be given, right? It is one AND gate and it is one AND gate, and one AND gate is going to be given the input j and other AND gate is going to be given the input k, right? And one AND gate is going to take qn prime, which means you can take this one, right, and j into qn prime, put a bubble, or you can directly take qn prime, no problem, right? And the other one is qn, which means it is going to directly take qn, right? So now this is the gate. Understood this? This is q and this is qn complement. See this. Now given t, we have converted it to jk, right, by putting this combinational circuit. So it is j into qn prime plus k into qn. Therefore you give just here whatever input you want to give, then the input is converted appropriately in such a way that will be given to t flip-flop, and t flip-flop will produce the output as if the output is produced by jk flip-flop, right? Okay, if you didn't understand this example well, I'll take more examples and solve it. Okay, we shall see more examples, you'll understand it. So it is basically simple. You are going to take the given whatever is target, we are going to write the equation for that characteristic function, and then we are going to write the excitation table for the given one, so that whatever is given, that one has to be expressed as a function of the whatever is given, that one has to be expressed as a function of the required, right? Therefore this is what we should fill in. So this entire part is called conversion. Conversion is nothing but what is that you are going to put here. Sometimes what we need is we need to count the clock cycles. So you know what a clock is, right? I have shown you, right? This one 1 0 0 1 like this, right? And then we want to count how many clocks have been produced till now, and sometimes we want to count in a modular manner. For example, I'll just tell you an example. Let us say we have a CPU, and then we are supposed to provide the service of one cycle to each device. Let us say there is one CPU, and now we have 5 devices, and now all these 5 devices have to be scheduled, or have to be allocated the CPU in a round robin manner. Then what I do is one clock I'll give it to the first one, second clock second one, third clock third one, fourth clock fourth one. Let us say 4 devices, and again the next clock has to be given to the first device, which means whenever I want such a requirement that I have to count some modular counting. Here it is mod 4 counting, right? Because first clock, second clock, third clock, fourth clock, again fifth clock, sixth clock, seventh clock, eighth clock. That is how every device is going to get it, right? So in such cases we want to count, and then sometimes we in CO again we shall see there is something called as control signals. So we want to generate the control signals. So whatever it is, we need some devices which are called counters, which are able to count the clock, right? Clock is nothing but the input that you provide. Now there are various types of counters there. I'll just give you the theoretical points here, and then we shall see the practical points. With examples I'll clear you all these points. For now just take them down, and I don't think that you'll understand anything now for some time. Unless I finish the problems or unless I take the examples, you will not understand anything. So let me finish it first. Now you just take it down. I'll just give you all the points. These points are important in order to answer the theory question. These are the important points. Now the counters are used to provide accurate timing and control signals. So timings means we are going to count the clocks, and then each clock we are going to assign to one device. I'll show you with an example later. And control signals we shall see it in CO later. There are 2 types of counters. One is synchronous and other is asynchronous. So what is the main difference between synchronous and asynchronous is, in synchronous counters all the flip-flops respond to the same clock instances, which means if you have various devices, Then in synchronous counters, all of them are going to get the same clock, right? I'll show you later. And in asynchronous counters, the output of one flip-flop drives the clock of the another flip-flop. So I'll just show you after this. And next one is synchronous counters are faster than asynchronous counters. The reason is simple. In asynchronous counter, what should happen is from one clock or from one device, the signal has to come out, and again that is going to form the input to the next device, and again that signal has to come out, that signal has to come out. Therefore, the signal has to ripple through all the devices. That is why asynchronous are slower. And if you compare to synchronous, at the same time we are going to apply the signal to all the flip-flops, therefore it will be very fast, right? And now, due to the simplicity of design, asynchronous counters are used in IC fabrication. IC means integrated circuits. So simplicity of design means it is very easy to design asynchronous counters. The simplified version of synchronous counter is called shift counters. So shift counters are very popular counters in the sense their main functionality is they have some information and they will just move it to the next one, and that one will move it to the next one, that one will move to the next one. That is called shifting, right? So and these shift counters are even useful in implementing the registers shift operations. We shall see that. Next one is the basic elements used in the counter is shift counter is D flip-flops. So generally there are these two flip-flops are majorly generally used, T and D. Why they are very much used is they have only one input, T and D, and D flip-flop is very much used in synchronous and T flip-flop used in asynchronous, right? I'll show you with examples that also. And now there is something called as ring counter. Ring counter and Johnson counter are a kind of shift counters. Okay. So anyway, we shall see all these points with examples. I know you will not be able to understand this theoretically. Now we shall see the examples. Okay. Please note them down. You can pause the video and just write down all the points one by one. Okay, fine. Watch it. Counters are of two types. One is synchronous and other is asynchronous. I told you. Just see how does the synchronous look like. Synchronous will be looking like this. So there are many flip-flops, right? And actually there are various things like this. So for every flip-flop, the input I am not showing it here. See, input is I0 and output is Q0. Input is I1, output is Q1. Input is In, output is Qn minus 1. What happens to the input is, this input is going to be a function of all the other flip-flops, which means sometimes it can take the input from like this, and it can take it, and it can take it like this. Therefore from middle also it can take it, and then apply some combinator circuits, and then that will be applied to this. Similarly there will be some combinator circuit and that will be applied to this, like that. So what I mean to say is, applying the input to synchronous counter is very, very complex. The reason is, every input can be a function of all the outputs together. It is going to be a complex thing, right? But then the main characteristic of this synchronous counter is like this. These are all flip-flops, and if you see this is a clock, and a same clock or common clock is applied to all the flip-flops. See this clock is applied to this clock, same clock, right? And it is all edge triggered. It is here, it is shown as edge triggered. It could be anything in general, right? Now the how fast is it, which means what is the speed at which we can get the output, that is called the fastness, right, or the speed. So if you apply a signal here at the input, the output will immediately appear here, right? And then before applying the next signal, we should wait for the output to come out of this, and maybe if there is any combinator circuits involved, then that combinational circuit should take the output and then provide the input here. So once you apply input, before applying the second input, you should wait for at least some time, and the time is equal to propagation delay of each flip-flop, of one flip-flop, plus if there are any combinational circuits involved, you have to even add them, right? So which means the propagation delay in the synchronous counters, this is the synchronous counter, is equal to, you take one flip-flop, because once you apply here, the signal has to come out of this, and after the signal comes out, we might apply the signal to the combination circuit, and then the output is going to be applied to the flip-flops again. Therefore, before you apply the next input, you should at least wait for the previous input to completely propagate and produce the output, right? For that, how much time it might take? One is you wait for the propagation delay of the flip-flop. Second is you wait for the combinational circuits which are used like this to allow the signal to pass through them. Therefore, this is the total time taken for us in order to propagate the signal and get the output. Then how much time should be the clock signal? So what is a clock is, you can take, think of it in many ways, but then the basic definition is, or the simplest definition which we can apply here is, let us say you are applying a input now. After how much time should you apply the next input? So the difference between these two, that one I call it as clock. That is the relevant definition for this evaluation, right? Generally you know the clock, right? So clock is having this time period is this, right? So from here to here, that is the time period, right? And again from here to here, that is the time period. Fine, that is okay. But then coming to this definition, we know that once we give the input, the time taken for it to produce the output is this one plus this one. Therefore, once you give the input, you just wait until this much time so that the next input is input can be applied. Therefore, the next input can be applied only after you get the output of the first input, right? So this is the time taken to get the output after applying the first input, and then you should at least wait for this much time before you apply the next input, right? Anyway, this time is very less. In the sense, the synchronous counters are very fast because the time taken is just time taken to pass through the one flip-flop and then the combinator circuits. Now let's see the asynchronous counters. Now you'll understand, once we show this, then you'll understand that it is very fast. See this? Now here the concept is, you are going to apply the clock to the first flip-flop, and the output of the first flip-flop is going to form the input to the input clock to the next flip-flop. And now the output of the next flip-flop is going to form the input clock to the next one. I am talking about the clock, and all of them are given only simple inputs, right? So input is simply one. Sometimes it could be a bit complex, but then anyway it will include not more than one or two OR gates or AND gates. Anyway, the input is simple, but then the clock is complex. First one is going to take one clock, and for the second one the clock is output of the first one, and for the third one the clock is output of the second one, like this, right? And for the last one the clock is this. So once you apply any input here, if I have to see the output, the time taken will be the total propagation delay in all the flip-flops. It is a rippling effect, right? Now the signal has to ripple through all these flip-flops. Let us say if there are n flip-flops, then what is the total time? N into flip-flops plus, if there are any combinational circuits involved, we have to even consider them. So between this one and this one, if I put a combination circuit, then we should even take the sum of all that time taken by the combination circuits. Therefore, the time period here is n into flip-flops. How many are flip-flops? Because we have to ripple the input through it, and then if there is any combination circuit involved, we have to take even that, right? And now the clock should be, what is the clock? Clock is nothing but, once you give an input now, after how long can you give the second input? That depends on how long does it take for the first input to propagate and produce the output. Once the output is stabilized, once you have collected the output, then obviously you can give the next input, right? Therefore, you should at least allow it some time so that the signal will propagate and then convert to output. So your time should be at least this much. After applying the first signal, you should at least wait for this much time before you apply the second signal, so that the output will be converging, right? So now we shall see some examples by each of them. Once we see the examples, we will understand it even better, right? So the theory questions possible here is, which one is faster? Now you can clearly see that here the output has to come out of only one flip-flop, but here the output has to come out of n flip-flops. Therefore, clearly synchronous is faster and asynchronous is slower, right? But then both are commonly used, both are having advantages and disadvantages. We shall see both of them with examples. Synchronous counter has been simplified to something called as a shift counter. So how does it work, and what are the inputs is like this. You know what is a synchronous counter, right? So we are going to apply the same clock to all the flip-flops at the same time. Therefore, every flip-flop is going to respond to the same clock. So it is going to be faster, but the design is going to be complex, which means, see this, In synchronous counter, what happens is every input is a function of every other output. That is actually the definition of synchronous counter. But if I have to do this, it is going to take a lot of the combination circuit. Therefore, just to simplify things, right, we have simplified it so much that, see this, so we are simplifying it. Its design is more complex. Synchronous circuit design is very complex. Therefore, we are trying to simplify it, and the simplification is like this. II is equal to Q of I minus 1, which means we are going to take a flip-flop, and from its output we are going to give the input to the next one. So if we have a flip-flop, first flip-flop, see, you know that how the synchronous counter look like, right? There are going to be n flip-flops like this, right? And now everyone is going to get the same clock, right? And now I'm saying that from this flip-flop we are going to provide the input to the next one. From this flip-flop the output is going to provide the input to the next one. That is what I'm saying, which means II means the input to one flip-flop is nothing but the output from the previous one, which means the output from the previous one is going to be here, output from the previous one is going to be here, right? So I1 is going to take the output from I0, Q0 as the input, and then the second one is going to take the input from the this one, the one before it, as the input, right? Like this as I have shown you. Here data is shifted from one flip-flop to the next flip-flop, so this is called shift counter, right? Why is it called shift counter? Is data is shifted from here to here if you watch it, and here to here if you watch it, and here to here, right? But only thing that we didn't discuss is what happens to the first flip-flop. So if I represent the first flip-flop with 0, then what is I0? What are you going to give it? So that is what we should discuss. So there are two things. Except the first one, every other flip-flop is going to receive the information from the previous one, and in fact all are D flip-flops. In shift register, shift flip-flops, we are going to use D flip-flops. Okay, now see this, except the first one, all are going to receive the input from the previous one. That is the specialty of the shift flip-flop. And now what are we going to do with the I0, which means the input to the first one? So there are two cases. Input is always going to be taken from n minus 1. N minus 1 means this one. I am assuming that I have 0 to n minus 1 flip-flops, right? So out of which 1 to n minus 1 have been discussed, right? But only thing I have to discuss is what happens to the input of the 0th flip-flop. Now there are of two cases. One case is it can directly take qn minus 1, which means the last output, and then take it and give it to this, or it can take the output from this one and then give it to this, right? So there are two varieties possible. Now I0 is a function of whatever is the output of the last one. Now if you directly give to I0 whatever you get from the last one, then it is called as ring counter, and if you give to the I0 whatever is given to the last one complement, then it is called Johnson's counter. And I don't know if you have understood anything from this, but I'll take the example and I'll make this very clear. It will be very easy. So one point you should note here is, actually synchronous counter has the equation this one. Every input can be a function of any output, right? But then we simplified it so much that one flip-flop is taking the input from only one flip-flop, the previous one, and the first one is taking the input from the last one, right? So when we did so many modifications, so many simplifications, actually what has happened is design got simplified. Because of this, design is very simple, but then the performance got hit a lot. So now if you watch it, if I have n flip-flops in general, how big, how many states can it represent? So if I have n flip-flops, then each flip-flop can hold one bit. Therefore, the number of bits, number of combinations possible by n flip-flops is 2 power n, isn't it? Therefore, 2 power n states are possible. And if you remember in TOC, with 2 power n states, how big a counter can I make? Mod 2 power n, isn't it? Mod 2 power n counter can be made, if you remember that. So if you remember the question where we discussed in TOC, where we have modulus counters, which means divisible by 4, divisible by 5, congruent to 2 divisible by 3, something like this. So whenever there is a divisibility question, I have shown you that we were actually using n states, right? Therefore, with n flip-flops, I could represent 2 power n states. How is it possible? Every flip-flop is able to hold 2 bits. Therefore, totally 2 power n states are possible, and using 2 power n states, a machine can act as a mod 2n counter, 2 power n counter, right? But then, because of the heavy simplification of this counter, the counter will not be able to count all 2 power n states. It will be able to count very less. Let's see how much are we able to count using the ring counter and Johnson's counter. So what is the difference between ring counter and Johnson's counter? This one. In ring counter, what happened is, if I have many flip-flops like this, this one is going to take input from this one is going to take input from this, the previous one, and the first one is going to take input from the last one. This is the ring counter, and anyway the same clock is going to be applied to all of them. And what about this Johnson counter is, it is also called as twisted ring counter, twisted ring. So there is a small twist here. So what is the twist is? Watch it. This is same. This one is going to take the input from this one is going to take the input from this, but the first one, this one, is going to take the input from complement of the last one, right? So if you watch it, it is coming from the complement of the last one, right? And everything is same clock is applied to all of them, right? So let's see which one is working how, and how are they called counters, everything. Let's see all of them. Okay. Hi, till now we have seen this synchronous counters. In synchronous counters, what happened is, we have applied the clock signal to all the flip-flops at the same time. That is why it is called synchronous counters. And now coming to asynchronous counters, the specialty of this is, output of one counter is going to be the clock to the other one. I mean, the clock is going to ripple through all of them. That is why it is also called as ripple counter. I'll show you with example. What happens is, one flip-flop will be there, and from that the output will come out, and that output is going to be the input to the next flip-flop, right? Clock to the next flip-flop. Like that, the clock is going to ripple through all the flip-flops, right? That is why it is called ripple counter. And now the basic flip-flop used is T. So T flip-flop is used in this. In the synchronous, generally the basic flip-flop used is D. But even though we have seen other examples, there are exceptions. See, it doesn't mean that you should not use any other. But then the basic flip-flop generally used is T flip-flop. You can fix it that way. In all the IC fabrications, T is used, right? Similarly, it is generally used for this binary counting, which is up counting. Up counting means increasing order, 1 2 3 4 5 6 7 8 and again 0, in case if it is modular, like that, which means it will always go up, right? The up counting are used for implementing incrementations. Incrementations means sometimes you would like to count from 1 to n and then again come back. That is called incrementing. So whenever our counting is in the incrementation, we generally go for this kind of up counter. Due to the simpler design, asynchronous counters are preferred in IC. So it is very simple that clock need not be applied to all the flip-flops. Therefore, it is generally preferred in IC fabrications. And moreover, the heat. Okay, let's not get into this. For computer science, it is enough. Okay, fine. Next one is IC 7490 is a decade counter, that is mod 10 counter. So there are already some IC circuits are available. You can directly buy them, and they have some standard names, and one name is IC 7490. So it is a decade counter, that is it is a mod 10 counter. Similarly, IC 7492 is a hexadecimal counter, that is mod 16 counter. So these circuits are already fabricated and they are readily available for you. You can buy them and you can use them. So I don't know if you understood anything by this theory, but then anyway I am going to take an example and it will be very clear from then on. Okay, we shall see some examples. Now watch this. This is the counter given, and now they are asking what type of counting it is performing and what is the type of the counter, in the sense it is self-starting or free-running, whatever. One thing you could directly see is it is just T flip-flops with 1 given as the input, and now output of this T0, which is Q0 prime, is given as the clock. In the earlier one, that mod 8 counter which we have seen, in that one we have seen that this Q0 is going to be given as the negative edge triggered, but then here it is modified from q0 to q0 prime, and as well as the negative edge is now modified to positive edge triggered. Therefore there are two modifications here, right? So it is going to be parallel, neutralized, and you can observe that it is a mod 4 counter which is up. Yes, you will directly get it, but then I really don't suggest that you follow this method or by heart it. It doesn't take a lot of time to do it. Okay, so let's see what happens. Now if you are looking at this q0n, which means next state of q0, it is always going to be complemented, right, for every clock. The reason is every clock is going to contain a positive edge, and therefore after at that point it is going to be toggled. So whatever was the previous state, we are going to get the complement of it, right, when for every clock, right? And what about this q1? q1n is going to be q1 complement, right? It is going to be complement of q1 whenever it is positive triggered. Which one is positive triggered? q1. So it is you need to be very cautious here. Now this t1 is actually triggered whenever q0 prime is this one, is changing from, it is a positive edge triggered, right, 0 to 1. So when q0 prime is changing from 0 to 1, what can you say about q0 in terms of q0? In terms of q0, it is changing from 1 to 0, right? So why should I convert it from q0 prime to q1? Because in the state table I'm not going to write q0 prime, I'm going to write q0, right? That is why I'm changing it. See, why am I doing it is, just check this. If q1 is the most significant bit and q0 is the least significant bit, okay, this is the present state and this is the next state. Now I want to write next state in terms of the present state. Now if you watch it, I didn't write anything about q0 prime. So since the state table is going to contain q0, I am just converting what happens to this q1n in terms of q0. That is the reason. Okay. And now what are the four states possible? 0 0 0 1 1 0 1 1, and you know that this q0 is going to be complemented. Complemented means whatever is the this one, it is going to be exactly complement. So after every clock, q0 is going to be complemented. So it is going to be 1 0 1 0, and now whenever q0 changes from 1 to 0, q1 gets complemented, which means q0 changes from 1 to 0 at these 2 points, right, 1 to 0 1 to 0, q1 gets complemented. So what is q1? Here q1 gets complemented to 1, and here q1 gets complemented to 0, right, and the remaining is going to be same. Now you just check it, what has happened. If you look at 0 0, which is nothing but state 0, see, I think you understood this. 0 0 I represent as 0 like that. Now 0 0 is represented with 0, it is going to the state 1, and again state 1 is going to state 2, and state 2 is going to state 3, and state 3 is going to again state 0, right? So which is nothing but mod 0, this mod 4 counter, which is actually up counter. Why? Because we are starting from 0 and 0 1 2 3, we are going that way. Therefore it is mod 4 up counter. Got it? Now check this one. So for every clock, both are positive triggered, positive edge triggered. Now q0 for every clock, you know that q0n is directly going to be complemented for every clock, right? Because every clock is going to contain a positive edge, therefore it is going to be triggered with 1, and therefore it is going to be complemented. And if you look at q1n, the next state of this 1, it is going to be complemented only when there is a positive edge from q0, which means only when q0 is going from 0 to 1, right? That is the positive edge. So only when q0 translates from 0 to 1, then q1 is going to be triggered, otherwise it is going to be in the latch mode, right? And now q0, q1, q0, q1n, q0n, right? 0 0 0 1 1 0 1 1. See, we have already seen the example, so we could do it fast. Now watch it. So whenever for every clock, q0 is going to be complemented, therefore it is going to be 1 0 1 0, and then whenever the q0 is going to be from 0 to 1, which means here 0 to 1 and 0 to 1, you are going to apply the complement. I mean q1n is going to be complemented. So how is this q1n going to behave? 1 0 0 1, right? Yes. Now check it. From 0, it is going to 1 1, which means 3. From 3 it is going to 1 0, which means 2, and from 2 1 0 it is going to 1, and from 1 it is going to 0, right? So it is nothing but down counter, right? It is not up counter, it is a binary down counter, right? And it is mod 4 down counter. So why do you think that we got this? Because of the change here. Previously it was negative edge and then negative edge triggered, right? But here, since it is a positive edge triggered, and from Q0 there is a change in this. It is a down counter, and anyway this counter is free running and self starting. That are already implied. Okay. Given this counter, they are saying that Q2, Q1, Q0, the initial state is 1 0 1. So why do you think that they have given this Q2, Q1, Q0 is? They wanted to say that Q2 is the most significant bit and Q0 is the least significant bit. And now this is a asynchronous counter given. So clearly you can see that all of them are positive edge triggered, but then the clock to this is the original clock. So actual clock is applied to Q0, T0, and then the output of this first flip-flop is given as the clock to the second one, and the output of the second one is given as the clock to the third one, right? Okay, now let's see how these flip-flops are actually toggling. How are they changing the inputs? Okay, let's see that first. So you know that Q0 n, so which means Q0 is going to complement its state for every clock. Right? And then Q1n, which means this one, output of this, is going to be complemented Q1 prime only when, so when is it going to happen? Only when Q0 prime, this one, right? Q0 prime is giving it a positive edge. What is positive edge? 0 to 1. If Q0 prime has to give a positive edge 0 to 1, then what should Q0 give? It should give a edge 1 to 0, which means Q0 should give negative edge. Or forget about positive edge and negative edge. So whenever the transition is from 1 to 0, so that we can, in the table, state table, we can easily do it. And now coming to Q2n, right? I'm talking about the flip-flop, this one. It is going to toggle, which means Q2 prime, only when the clock is a positive edge. Clock is giving the positive edge. So which one? Q1 is giving the positive edge. So positive edge is nothing but 0 to 1. Alright. So whenever Q1 is giving 0 to 1, then Q2n is going to be complemented. Now let's see what are the state table. So from the state table, you can construct the state diagram, right? Present state, we can write it in terms of Q2, Q1, Q0, and the next state is Q2n, Q1n, Q0n, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Let's see what happens here. Now Q0 is going to be complemented for every clock, which means whatever it is, we are going to get complement of it, which means 1 0 1 0 1 0 1 0, right? And then Q1 is going to be complemented. See, Q1 is going to be complemented whenever Q0 is going from 1 to 0. So whenever Q0 is going from 1 to 0, 1 to 0 here, then at that point Q0 is going from 1 to 0, then Q1 is going to be complemented. So watch it. Q1 is going to be complemented, which means it is 1, it is 0, and it is 1, and it is 0, right? And the rest of the places, it is going to be same. So what are the rest of the places? 0 1 0 1, right? And now whenever Q1 is going from 0 to 1, Q2 is going to get complemented, which means see Q1 is going from 0 to 1, which means at this point it is going from 0 to 1, and then 0 to 1, 0 to 0, 0 to 1. At this point it is going from 0 to 1. That's it, right? So only at this point it is going to be complemented. So how is it going to be complemented? So here, right? So at this point it is 1, and at this point it is 0, and at the remaining places it is same, which means 0, 0, 0, 1, 1, 1, right? Now we can draw the state diagram, and from the state diagram we can see if it is in 1, 0, 1, what happens after 4 clocks. If the initial state is 1, 0, 1, what happens after 4 clocks, right? Let me draw the state diagram here. If I am in 0, from 0 I can go to 1, and from 1 I can go to 6, and from 6 I can go to 0. 9. From 6 is here, right? From 6 I can go to 7, and from 7 I can go to 4, and from 4 I can go to 5, and from 5 I can go to 2, and from 2 I can go to 3, and from 3 I can go to 0, right? Therefore, if the initial state is 1, 0, 1, 1, 0, 1 is nothing but 5, then what is the state after 5 clocks? Which means if you are here at this point, right, what happens after 5 clocks? 1 clock, 2 clock, 3, 4, after 4 clocks, 1, 2, 3, 4, 3, 4, 4 clocks we are going to be in 1, which means 0, 0, 1 is the answer, right? So after 4 clocks you are going to be there. Fine. Now flip-flop has various advantages. As we know that flip-flop is able to save 1 bit every flip-flop, and then putting all these flip-flops together we can use them in various phases or various devices. So just now we have seen some applications. They are as counters. So how are they used as counters? We have already seen that mod 3 counter, mod 4 counter, maybe a ring counter, twisted ring counter. So they are all used as counters. What are they counting? They are generally used to count the number of clock pulses. Apart from that, we can even use them as frequency divider. Why is it called frequency divider? Because the output frequency is going to be divided. If the input frequency is f, I have already shown you some examples in which if the input frequency is so and so, the output frequency is going to be less than that, right? So that is one of the applications. One is about the counters, and the other thing that the flip-flop can do is it can act as memory device. So especially sequential memory. So what is sequential memory is, it is not randomly accessible. We can access it in sequence. I'll show you now with examples how we can use it. So one of the applications of this one is it is used as accumulator in microprocessors. Later when we discuss about microprocessors in some other subject, then I'll tell you how to use it as how the microprocessor is using accumulator. But then the building block of accumulator is again flip-flop. Okay, so here what we shall do is, not to discuss about how it is used as memory, I'll explain you with few examples how shift registers are generally designed. So we are going to talk about shift registers. What is a shift register is, we generally move the bits. We shift the bits from one location to the next location, one location to the next location. I'll take an example and explain you. Instead of explaining you with words, you might not understand it. So in the next video I'll explain that. Okay, fine. Now let's see how we use how to design the 3-bit shift register. So in order to design the 3-bit shift register, we are supposed to have 3 flip-flops. So in general you can take any flip-flops, but the most popular one is the D flip-flop. We can use some other flip-flop also as D flip-flop, but the most important thing here is, if the underlying design contains D flip-flops, it will be easy for us to move the bits. So most popular design is using D flip-flops. Okay. Now there are various ways you can use this circuit. One way is to use it as serial input, serial output device, which means we send input from one side and we take output from other side. So serially, which means if I have to enter, since there are 3 flip-flops, we can store 3 bits there, and how to store those 3 bits by sending them serially one after the other. Okay, let us say I am sending them serially one after the other, and then how to read the output again by taking them serially. Then that is called as serial input, serial output. I'll just show you what I am trying to say here. Okay. Now assume that we are starting at clock. Okay, this is clock, and the next one serial input, and now we have 3 flip-flops Q1, Q0. Assume that initially nothing is there in these flip-flops, which means 0 at the clock 0, and no input is applied. And at clock number 1, let us say I want to store in this register a sequence 101. This is what I wanted to store, which means I'll be trying to send this 101 into them. So I want this 1 to be present at the least significant bit, which means here I want this 0 to be present here, and I want this 1 to be present here. So instead of 101, let us say I want to have 110, then it will give you some difference. 0 should go here and be standing there, and then 1 should be here, and then the other one should be here. Okay, so now what I'll try to do is, initially at clock 0 nothing is there, and now at clock 1 input 0 is applied. Why is 0 applied? Because I am trying to push this one first into this circuit so that it will end up there by the end of the clocks, the number of clocks that I'll tell you. Okay, and now so after this I'll apply 1 clock. At clock number 1 I am going to give the input as 0. Okay, and now after that clock number 1, what happens is, when 0 is here, we know that this D flip-flop simply transfers the data from input to output after every clock, which means this 0 will come here, right? So Q2 will contain 0, and this one will contain 0, and this one will contain 0. Okay, so actually 0 is already there, you need not do that. So that is why I have taken the example 101. But if I take the example 101, which one is least significant, which one is more significant, you are getting confused. But if I take this input, this one as 0, the least significant bit is, you might ask me, what is the use of doing this? Okay, let's go with 101 only. Later we shall take one more example if needed. If I take 101, then only I think this example will make some sense. So initially at clock number 1, I am going to input at the serial input 1, I am going to give here as 1. Okay, and then I'll wait for 1 clock. Then after 1 clock, that 1 will go as Q2, which means that 1 will go and stand here. Okay, now at Q2 we have 1. Fine. And now next thing is, I want to input 0. So this one has been input given, and now I want to input 0. So at clock 2 I am going to give 0 as the input, so which means 0 is applied, right? And then when I apply 1 clock, what happens is, this one will move forward, because this is also given to the same clock. This flip-flop is also given to the same clock, and since it is a D flip-flop, it will also move the data forward, which means this one will move here and this 0 will move here. Okay, so what does it mean? This one will move here, right, and this 0 will move here. Earlier this one was moving here. Are you finding the directions, right? So it is serially one by one is going, and here there is still 0. And next thing is, I have to again input 1. Therefore at clock 3 I'll again input 1. Then what happens? I'm again giving 1 here, right? Then if I apply 1 clock, what happens is, everything will move forward, which means this one will move here, this 0 will move here, and this one will move here, right? So which means this one will move here, this 0 will move here, and this one will move here. Therefore by the end of 3 clocks I am able to place 101 onto the shift registers. Now you just imagine that in all the flip-flops, okay, you just imagine that we have n-bit shift register, which is a serial input device. Then how many clock pulses are required in order to place those n bits on the flip-flop? So in earlier case, if the initial number was 0, you might have cut down 1 bit, but in worst case, how many clocks you should wait? N clocks, right? Therefore, in a serial input shift register, which is n bit, if you have to put n bits on the shift register, the number of clocks required is n. So n clocks are required to put n bits on the flip-flops. Got it? And now let's say I want to read it out. I want to observe, or I want to read what is there in the flip-flop at some later point of time. What is there in this shift register? Then let us assume that we are operating it in the serial output. Then how much time does it take for us to take the values out? See this? I want to see what the output is. So what I'll do is, at this point, let's say at some point Q2, Q1, Q0 is containing 101, okay, at some point, and I want to see the output. Now already 1 is present at Q0, and Q0 is nothing but the output. Therefore 1 is already there, isn't it? So 1 we get it, which means output is going to be 1 at this point, and later I'll apply one more clock. So by applying one clock, what happens is this one will be moving out, and this 0 will come here, right, and this 1 will come here, and assuming that input given is 0, 0 will be there, which means no input is given, then 0 will be here. Then what happens? We are able to see 0 after 1, right, and after the second clock, this 0 will come here and this 1 will come here, and assuming that no input is given, 0 will be given here, right, which means 1 will be present at the output. Therefore 101 will get it after 2 clock pulses, right? So for a 3-bit shift register, we have to apply 3 clock pulses in order to give the input in a serial manner, and we have to apply 2 clock pulses to take out the output in a serial manner, right? Therefore, if its size is n bits, if it is n bit flip-flop, if it's n bit shift register, then the number of clock pulses required for serial input is n, and the number of clock pulses required for serial output is n minus 1. Therefore total number of clock pulses required in order to store some information on a n bit shift register and take it out in serial input serial output manner is 2n minus 1. Got it? Now one other way of operating this one is, instead of using it as serial input serial output, we can also use it as parallel input parallel output, which means we can connect, instead of connecting like this, we could actually give this one is out, this one is in, this one is out, this one is in, right? Then we can directly give the input in one go. If I have to apply 101, I'll give 1 here, I'll give 0 here, I'll give 1 here, and then I'll apply 1 clock. Then automatically values present will be 1, here 0, and here 1, right? And I can directly read them, which means if I go with parallel in parallel out, isn't it? I can give the input parallelly and I can read them parallelly. If I go with parallel in parallel out, in just 1 clock I can directly input the bits and then I can directly read the bits outside. But then that is not the concept of shift registers. Shift registers are generally supposed to shift, right? So that is why I am not discussing about this parallel input. Now this parallel input parallel output is nothing but a kind of RAM, a random memory, random access memory. Okay, so here one question that you should remember is this one: how many clock cycles does it require in order to input some information into shift register in serial input mode, which is n. In order to output it, it is n minus 1. Got it? Number system mainly deals with how we represent a number and how we count the numbers, counting. Okay, so it all began with this. Earlier, when let's go back to the caveman days. So when these cavemen used to be there, they used to have cattle and they don't know how to count them. So what they used to do is, whenever they let the sheep or buffaloes out, what they do is, for every sheep they let out, they used to take a stone and set it aside for every sheep, right? Then what happens is, if you have 100 sheep, you end up collecting 100 stones, right? If you have 10 ships, if you let out 10 ships, you'll just put 10 stones aside. Later in the evenings, when they again bring them back into their homes, then they'll just again verify it with the stones. For every stone, for every cattle that comes in, for every sheep, they are going to take out that stone. So that is how they used to count. So this is where it all started, counting. So later what happened is, if you trace back the history, the usage of base 10 was done by Genghis Khan, and I don't know exact year. So okay, so how did this base 10 number system come up with is, we have 10 fingers. So since we have 10 fingers, people started counting with 10. So that is how base 10 has come up. Initial number system was base 1, which was having only one symbol, which is a stone, and later we had base 10, which is having 10 symbols from 0 to 9, and later base 8 and base 16. So let me write down all of it. First one is, we started with this base base 1. So in base 1 we have only one symbol, and that is nothing but 0, right? Even you might have remembered about, you must be remembering about this abacus. Abacus, if you have used it in your school days, it is base 1 number system, right? That is where they start teaching you how to count. You remember that you used to pull the balls with the pearls or the balls which were in the strings, and then count. That is base 0. And later the next popular number system was base 10. Why is base 10 popular? The reason is simple. We have 10 fingers, and so we started counting in base 10. And what are the numbers we have in this? 0, 1, 2, 3. These are all the symbols we use. 5, 6, 7, 8, 9. Okay. So generally what we do is, whenever we have digits in a number system, we generally use one symbol to represent the digit. If the number system is having, let's say, base 11. Now how many digits are we supposed to have in base 11? 11 digits. So 0, 1, 2, 3, so on 9. It is going to make up 10 digits, and we need one more. So we cannot write 10. The basic convention that we follow is, every digit is in any number system has to be represented with a single number, single symbol. So there are two symbols, a combination of two symbols. Therefore there is a chance that when you write a number, you might get confused, because already 1 and 0 are already existing here, and again you are writing 1 and 0 here. So we might get confused whether it represents 10 or it represents a 1 followed by a 0. So just to avoid that confusion, what we do is, we use the other symbols like A, B, C, D. So A, if you write it, there is no confusion, it is 10. A single symbol is used to represent a digit in this base, right? 11 is like that. And what about next one, base 12? Base 12 number system, it should contain 12 digits, and 0, 1, 2, 3, so on 9 is going to form 10. We need two more digits, and we need, the two digits have to be 10 and 11. If I write 10 and 11 directly, then already 0 and 1 are existing, so it might lead to a confusion when you write them in numbers. So for that reason, we are going to use a single symbol A and B, right? So like this, we are going to have number systems. So one thing that you should observe is, we are following a convention that when the base of a number system is something, we have exactly those many number of digits in the number system, and then all the digits are supposed to be less than the base. In this case, if you see it, we are having 0 to 9, all the digits are less than 10. That is the convention we are following. But then in exam, they might form some other number systems also. I'll come to that point later. Fine. And the next popular, like this, we have the most popular number system, which is base 16. So why is base 16 popular is, whenever you write any number in base 2, so we have base 2. Base 2 is the most popular number system which is used in binary number system, which is used in computers, as you know, on and off, 0 and 1, it contains 0 and 1. So whenever you write any number in this 0 and 1, Then if you have to represent a very big number like this, 0 1 1 0 1 0 1 1 0 1 1 1 0, something like this, and if you have to read this number and explain it to someone, it is going to take a lot of effort to remember it. So for that reason, what people tried is they tried clubbing it. They tried clubbing 3 bits or 4 bits like this, 3 bits or 4 bits, something like this. Then if you club 3 bits, then it forms base 8 number system, and if you club 4 bits, it forms base 16 number system. I'll come to this point when we discuss about how to convert the number from one number system to the other. For example, we can convert the number from base 2 to base 4, base 4 to base 8, base 8 to base 6, something like this. We can do the conversions. I'll come to that point later. So base 2 is 0 and 1, and then we have one more popular number system, base 8. Is simple. It is just the combining 3 bits in base 2. We generally use base 8 to represent a number which is already in binary. I'll come to that point later with examples. So 0 1 2 3 4 5 6 7. So here I want you to note one point. If the base is 8, then the number of symbols we have is 8, and all the symbols, all the digits should be less than the base, which is 8. So we cannot have a number 8. For example, can I have a number 0 1 2 6 in base 6? We cannot have it. The reason being, if you observe this 6 cannot be present in the number system which is having base 6. The reason is all the digits in base 6 should be less than 6. So it cannot be a number in base 6. It is not a valid representation. And now what about base 16? How many digits are we supposed to have? 16 digits. So which means we are supposed to have from 0 to 9, which is 10, and then 6 more. So from 0, 0, 1, 2, so on 9, 0 to 10, right? It is 10, and then we are supposed to have 6 more. So since we cannot have 10, 11, 12, so on 15, for that reason we are going to have A, B, C, D. A, B, C, D, E, F, 6. So this is 10, this is 11, 12, 13, 14, 15. Like that we can have the number system represented. Now what are the various problems which are possible on this is, they will give us they'll ask us to change the number system from one number system to other. For example, if base of a number system is B1, they'll ask you to convert it to B2. Right? So if B1 and B2 are in powers of 2, then I suggest that you convert them to binary base 2 and then convert it to other. It is very easy. If they are not in powers of 2, if they are in powers of, let's say, if let's say they are not in powers of 2 and there are some different numbers, then what you can do is convert them to base 10 and then convert them to the required base, other base. So these are the various questions that are possible, and sometimes what they give you, they will give you some equations and then they will ask you to find out what is the base of the number system that the numbers are present in. I'll give you all the questions with examples, you'll understand it. And then they might even form some weird number systems like this. So they might say that we have formed a new number system with base 7, and base 7 is supposed to have how many symbols, how many digits? 7 digits, right? So instead of having them from 0 to, generally the general convention is that we are going to have 0 to 6, which is nothing but 7 symbols or 7 digits. But then what they would say is, we are having the digits in this as -3, -2, -1, 0, 1, 2, 3. So these are the symbols we have in our number system, and this -1, -2, -3 are represented as A, B, C. Then they will ask you to convert a given number into this base. So this is generally not used in practice, but then an examiner in GATE might ask you some questions like that. We shall even examine questions like that. Okay. So what I'll do next is, I'll take all the questions which are possible on this basic concepts and I'll just clear them. Then you'll be strong with basics. Then we go on to the difficult questions. Okay. Fine. Let's see how to convert a number from one base to the other base. For example, You might try to have, they might ask you this question. They might give you one number system, let's say b1. The base of the number is b1, and they will give you a number, and they will ask you to convert it to some number. They will ask you to convert it to some base, some other base, the same number. So given a number in one base, you are supposed to convert it to other base. So what are the steps you should follow is, first step is convert the given number from base b1 to base 10. Okay, and then the second step is convert the base 10 number to base b2. So there are two steps involved. Let's take both these steps and see with some examples how to do that, and then I'll tell you some shortcuts as well. So first see how to do this. So first see how to convert a number from some other base to base 10. The rule is like this: if you have a base, a number like this, a, b, c is the number base x, then what is the number in base 10? If this is the equation given, then the general method is you have to apply the weights. Weight of c is x power 0, weight of b is x power 1, and weight of a is x power 2, right? And now you correspondingly you multiply the corresponding digits with the weights and then sum them up, then you are going to get base 10 number. So what does it mean? A into x square plus b into x plus c should be equal to the number that we require in base 10. Remember this. Okay, now let's see some examples on this. For example, if they have given you a number like this, 123 base 7, what is it in base 10? What does the number represent? Then how can you do it? Apply the weights. Weight of this one is 7 power 0, and weight of this one is 7 power 1, and weight of this one is 7 power 2. Then sum of them, the corresponding digits with the weights, and then sum of them, then you are going to get the answer. So how much do you get? 7 square into 1 plus 7 power 1 into 2 plus 7 power 0 into 3. So this is the number we wanted in base 10. You please fill it up. I think it is 49 plus 14 plus 3. Okay, you just see what the result is. Okay, this is in base 10. This is the number that 123 is representing, right? And let's see one more example. Let's say we have something like this. 1, 2, AB base 16 equal to how much in base 10? Again do the same method. What is the weight of each one? You multiply with this and you can get the answer. What is the weight of B here? 16 power 0. What is the weight of A? 16 power 1. Weight of 2? 16 power 2. Weight of 3? Weight of 1? 16 power 3. So you can write it same way. So weight of B is 16 power 0, which means 16 power 0 into B. So what is B? You have to be careful, bit careful here. So what is B? In base 16, you should know what are the values of A and B. Value of A is 10 and value of B is 11. Value of C is 12. Value of D is 13. E is 14 and F is 15. And now what is the value of B? B is 11. Therefore, into 11 plus, what is the weight of A? Weight of A is 16 power 1, which means 16 power 1 into, what is A? A represents 10, therefore write it as 10 plus, what is the weight of the digit 2 there? It is 16 power 2. 16 power 2 into 2 plus 16 power 3 into 1. So this is the final number that you get in base 10. So this is how you can convert any number to base 10. Got it? So what is one other way to do this is, I'll try to take a binary number and explain you. You can apply the same method to this. This is a straightforward method. This method works always. And if you are looking at any shortcut, shortcut depends on the way you practice it. If you practice well, it will be a shortcut. Otherwise, both will be same. So I'll just tell you one more example. For example, if you have 1 0 1 0. This is base 2. What does the number represent in base 10? If this is the question asked, then how can you solve it? Again, take the weights. Weight of this one is 2 power 0, 2 power 1, 2 power 2, 2 power 3. So 0 into 2 power 0 plus 1 into 2 power 1 plus 0 into 2 power 2 plus 1 into 2 power 3. So if you sum them up, it is going to be 10 in base 10. So 10 in base 10 is 1010 in base 2. Now there is a shortcut here. You need not convert it this way. I'll just tell you, and you can apply this shortcut to all the number systems as well. The shortcut is like this. I don't know whether to call it as shortcut or not. That all depends on how well you practice it. So now if you have 1 0 1 0, how can I do it is, watch it. The basics are like this. If you have a number 1, I'm talking about base 2. For example, if you are considering base 2, if you have number 1, this is 1 in base 10 as well. If you append any digit to this, if you append any digit to the right of it, then what happens to the entire number is whatever the number was earlier representing multiplied with 2 plus whatever is added. Okay. So with examples it will be easy, don't worry. See, if you have 1, I am appending 0, what does it represent is whatever the number was earlier representing, which is 1, multiplied with the base, which is 2, and then adding it up with the newly added number. So what does it mean? 1 0 represents 2, got it? And now let's say we have 1 0 already, and now I am appending a number 1. What does the total number become? So 101 is 5, we know that. Let's see how to get it from this rule. So whenever you have any binary number, see, I am talking about base 2, and the same method can be applied to any base. You can take it to base 10 and you can take it to base 6, base 8, anything. In fact, I derived this method by looking at the base 10 only. Now if you have something, some value like this 1 0, and if we append it something, then what the value is, how to calculate it is, see what the value of the earlier number was. Earlier number's value was 2, and then multiply with its base, which means 2, and then add it with this one. Then what do we get? 5 is what I got. Understood this? 101 is 5. Now if you have 101 101, and if I append 0, then what is the total value of this? Take whatever the earlier value was for 101, which was 5, we just calculated it, and then multiply it with the base. What is the base? 2, and then add 0. Now what is the total value? 10. Therefore you can even evaluate that the value of 1010 is 10 using this method, right? So how to do it first? See this, you can directly do it this way. Value, you have to start from the most significant bit, which means here, start from the leftmost. Value of this one is 2, and then 2 multiplied with, value of this one is 1, and what about this one? 1 into 2 plus 0, which is 2. What about this one? 2 into 2 plus 1, which is 5. What about this one? 5 into 2 plus 0, which is 10. Are you getting this? So this way you can even evaluate any big number, right? For example, if you want to evaluate the value of this 10 10 10, you want to see what this value is without writing the equations, then how can you start off? See, value of this one is 1, and value of this one is 1 into 2 plus 0, which is 2, and value of this one is, I'll just write the values also here. Value of this one, initially it was 1, and next it became 2, and next it became 5, right? And now this one, so what is it? 5 into 2 plus 0, which is 10, and again I have appended 1, which means 10 into 2 plus 1, which is 21, and then again I have appended 0, which means 2 into 21, which is 42. Therefore the value of this one is 42. Got it? So how did I get this method? Just from base 10 itself. So it is applicable to any base. For example, if you look at 123 or 125, so what is its value in base 10? How did I get it? take 1, multiply with its base. What is the base? 10. So 1 into 10 is, sorry, it is 1. And now if I have to find out what is the value of 1 followed by 2 in base 10, number is already in base 10, I am just doing it. So multiply 1 with the base, which is 10, and then you add 2, which becomes 12 now. And if I want to find out the number, the value of this, multiply 12 with 10 and then add 5, which means 125. So from here only we derive this, and this can be applied to any number. For example, if you want to, so now see this, if you want to see how, if it is valid or not, you can even test with the given equation. I have already given you this equation, right? So let me just show you here. I have already given you this. A, B, C, base x, and I told you that its value is ax square plus bx plus c in decimal. Now how can we get it even by this method which I just used? Now see this. Now the value of a we know is simply a, okay, and whenever we have a into b, then what did I say to write? I mean a appended with b. What did I say just now? So a has to be multiplied with the base x, and then you have to add the digit b. Got it? And this is the value of ab in 10, base 10. Now when you have abc, how to do it is, you have to multiply the earlier number with the base, and then you have to add the newly appended number c, the newly appended digit c. Now what does the total sum make it up? See this, that equal to ax square plus bx plus c. So this method is right. Now whether to call it a shortcut or not, that actually depends on how you look at it, right? So for example, if you want to see what the value of 1 2 1 2 in base 3, right? Now how to do it? The value of this one is 1, and what about the value of 1 followed by 2? 1 into 3 plus 2, which is 5. The value of this entire thing is 5 now. And now what about 5 followed by 1? 3 into 5 plus 1, which is 16. What is the value of this entire thing followed by 2? 3 into 16, 48 plus 2, which is 50. Got it? So definitely if you practice it, I feel that this method is easier. So that is all up to you. So now what did we see here? Why am I doing all this? So the reason is this. Now whenever you want to change from one base to the other base, the steps are change from base, that given base, to base 10, and then change from base 10 to the required base. So now in this entire till now in this video, what we discussed is how to change a number from base b1 to base 10. Now let's see how to change a number from base 10 to base b2. Okay. Now let's see the second model. How to convert a number from base 10 to some other base, let's say b2. We have already seen how to convert a number from base b1 to base 10. Now we take the same number when we convert it to b2, then ultimately we have closed the loop. So from b1 we are able to convert the number to base b2. So the second step. Now let's take an example and I'll explain you. Let's take the simple one. Let's say we have number 10 or number 11. This number is given in base 10, and now the question is, I want to find out its value in base 2. So we already know this. You might have done this many times. It is very simple. I'll just take an example for those who don't know it, and later I'll give you even some other way to do it. Okay. So now number 11. So when you have to continuously keep dividing it with 2, and then note down the remainders, and then we go in the reverse order and we arrange the number, right? So first we divide with 2. What is the quotient and what is the remainder? Quotient is 5, right? Why? 2 into 5 is 10, and the remainder is 1. And again divide it with 2. What is the quotient and what is the remainder? Quotient is 2 and the remainder is 1. Again I divide with 2. What is the quotient? 1. And what is the remainder? Remainder is 0. Okay. and again I divide with 2. What is the quotient? 0. And what is the remainder? 1. So whenever you get a quotient as 0, you stop there. And now you take all the remainders and then arrange them from bottom to top. So what do you get? 1 0 1 1. So 1 0 1 1 is the number representation for 11 in base 2. Got it? So this way you can do it, but the problem with this type of conversion is, if you observe it, the number of steps taken for this will be too high. If the number is x, let us say a number x is given in base 10, and you are supposed to convert the number to base 2, then how many steps are required? So if you calculate it, it will be log x base 2 steps, isn't it? How did I get it? If number x is as big as 2 power n, if the number x is as big as 2 power n, every division is going to make it 2 power n minus 1, 2 power n minus 2, so on, right? Every division is going to make it from 2 power n to 2 power n minus 1, and from 2 power n minus 1 to 2 power n minus 2, like this. So we are going to do this until this one becomes this power becomes 0, which means we are roughly going to have log x base 2 steps, and this is very big if you have a big example. So let me tell you how big it will be if you have some number like this. So if the question is given like this, given number is 32 base 10, and you are supposed to find out what its quotient is, what the number is in base 2, then I'll use the same method. So 32, when I divide with 2, what is the quotient? 16. What is the remainder? 0. And when I divide with 2, what is the quotient? 8. What is the remainder? 0. And again divide with 2, quotient is 4, remainder is 0. Again divide with 2, quotient is 2, remainder is 0. Again divide with 2, quotient is 1, remainder is 0. Again divide with 2, quotient is 0, remainder is 1. Now you put all of them from bottom up. So how many do you get? What do you get? The final answer is 1, 2, 3, 4, 5. This is 32 in base 2 if you go with the conventional method of converting it. But then don't do this. So I'll tell you some other method how you can do it easily, right? So first, before going to that method, I just want you to observe something. So whenever you have the bases in the powers of 2 or in the powers of 3 or in the powers of 4, like this. So if you want to convert a number between base 2 and base 16, or base 2 and base 4, or base 2 and base 32. So if this is given, so what does it mean? Both the numbers are in bases, which means one given number is in base 2 and you are supposed to convert it to base 16, which is in the power of 2, or given number is in base 16 and you are supposed to convert it to base 2, which is in power of 2, or if it is between 2 and 4, if it is between 2 and 32. If you have anything like that, you follow this method. I'll just take an example and I'll tell you how to do this. Let us say the number given is 1056. This is in base 16, and now we are supposed to convert it to base 2. So how to convert it is, you can observe that 16 is 2 power 4, right? You have to get it. You have to observe that clue first. 16 is 2 power 4. So what does it mean? Every digit which is in base 16, has to be represented using 4 digits in base 2. Every digit which is in base 16 has to be represented with 4 digits in base 2. You have to keep that in mind. Now let's take every digit in base 16 and let's convert it to base 2. You can either go from LSB or MSB, that is not an issue, but then you just see that LSBs will be in the LSBs here and MSBs will be in the MSBs here. You can go with any method. So now let me convert this one. 1. So 1, I have to represent 1 in base 2 in such a way that it is represented as 4 bits. So what is the 4-bit representation of 1 in base 2? 0, 0, 0, 1. Got it? And next one is 0. Represent 0 in base 2 in 4-bit representation. How do we get it? 0, 0, 0, 0. And again, next one is 5. So represent 5 in base 2 in 4-bit representation. How do we get it? 0, 1, 0, 1. This is 5. And what about the next one? 6. So represent 6 in base 2 in 4-bit representation. 0, 1, 1, 0. Therefore, this is the given number in base 2. Got it? So this is how you converted base 16 number into base 2, right? And now let's see how to convert a base 2 number into base 16. Let's say we have a base 2 number like this: 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, something like this. This is the base 2 number. This is the base 2 number, and now I want to convert it to base 16. So here you should be bit careful. Earlier you directly converted it, but here you should be bit careful. So the method is same. So what is it? 2 power 4 is 16 power 1. So what does it mean? Every 4 digits in base 2 has to be represented using 1 digit in base 16. Every 4 digits in base 2 has to be represented using 1 digit in base 16. Therefore, you try clubbing 4 bits. Here you should be careful. Whenever you are trying to club 4 bits in base 2, you should start it from LSB, not from MSB. The reason is, if you start from MSB, you might end up with fewer than 4 bits in the last one. Then what happens is, you will try to add a 0, append a 0 at the end. What does that mean? You are appending a 0 in the right hand side. When you append the 0 in the right hand side, the number is actually multiplied by 2. Just now we have seen it, right? If I append a 0 in the right hand side, the number is actually multiplied by 2. But if you start from the leftmost side, if you start from the least significant bit, and if you keep on clubbing, even if the number of digits remaining at the end are not 4, if it is 2 or 3, and even if you add zeros to make it to 4, in the MSB, the value of the number doesn't change. Got it? Therefore, you keep this in mind. Whenever we are trying to convert it, we are just trying to convert them from the LSB, right? So you just club these 4 first, and then these 4 first, and then there are only 3. For that reason, you can append a 0 and you can club it. Got it? Now 1111, if you convert it, this number is equal to 15. So what is 15 in base 16? 15 is represented by F, right? And then 1110, if you convert it, this is 14. What is 14? E. And 0100, it is nothing but 8. So it is 8EF base 16. Therefore, converting a base 2 and base 2 to base 16 is easy, isn't it? And you can similarly convert between 2 and 8, 2 and 4, because they are all powers of 2. For example, if you want to convert, let's say 101, 110, 11 into, this is given in base 2. If you want to convert it into base 8, what do you want to do? How do you want to do? Now we know that 2 power 3 is equal to 8 power 1. What does it mean? Every 3 digits in base 2 should be represented as 1 digit in base 8. That is the meaning of it. Now what should I do? Club 3 bits in base 2. From where? From LSB, not from MSB. So just keep that in mind. Okay. Now that is the only way you can go wrong there. So append one more, right? So what is this number? So this number is 3. What is this number? This number is 7. What is this number? This number is, I think, 2, right? So this is 273 base 8. Is this a valid base 8 number? Check this. All the digits in this have to be less than 8. Yes, they are all less than 8. 7 is also less than 8. Therefore, the number is valid and we have converted base 2 to base 8. Got it? And how to convert base 8 to base 2? Let's see this again. Let's say this is the number given in base 8. You want to convert it into base 2. This is given in base 8 and now I want to find out what the base 2 is. How do I get it? Again, 2 power 3 is base 2 and 2 power 1 is base 2. So 2 power 3 is base 8 and 2 power 1 is base 2. So what does it mean? We have to represent every digit in base 8 as 3 bits in base 2. So how can we do that? Every digit here has to be represented as 3 bits. So either you can start from MSB or LSB, it doesn't matter much. So what does it mean here? 0, 1, 1 is here, and what about 7? 1, 1, 1, and what about 2? 0, 1, 0. Now check this, you got back the original number. Got it? See, and original number doesn't have 0 given, but then adding a 0 doesn't change anything, so you remove it. So you got back the original number. So that is how the conversions work. Now after knowing this, so one thing you have to be careful is, I am able to convert from 2 to 4 and 4 to 2 and 2 to 8 and 4 to 8 like this. Sorry, 2 to 4 and 8 to 8 like this. I am able to do it like this: 2 to 4, 4 to 2, and 8 to 2, 2 to 8, and 2 to 16. I am able to do all this, but then I didn't tell you how to convert base 8 to base 16. Actually 8 square is not 16, it is 64, or it is not in the powers, right? Then the best thing is convert this one to 2, and then from 2 to 16 you can do it this way. Got it? So anyway, what I mean to say is, if bases are in powers of 2, you can use the base 2 binary number as the intermediate form, and again you can convert it back, right? So this is how the conversion is happening between base 2s, and you can extend this method even to base 3, which means if you can convert from base 3 to base 9 directly. How? Every digit in base 9 can be represented as 2 digits in base 3, because 3 square is 9. Or you can convert between 27 and then 3, right? Every digit in base 27 can be represented as 3 digits in base 3, right? Vice versa, you can do that. Or you can convert between 4 and 16. So in the same way you can play with them, right? Now let's see what is the significance of this in converting a number from base 10 to some other base. Now let's get back to that point. Okay, so earlier I have shown you that in order to convert a number from base 10 to base 2, I'm taking a lot of steps to do this, right? So that is the reason what I want to do is, even though I want to convert a number to base 2, I'll try to convert it to a higher base like 16 and then convert it to base 2 again. This one will be easy for me, which means from base 10 I'll try to convert it to base 16 and then base 2. So let's see how it is easy. Now I want to convert this 32 only. 32 base 10 to base 2. But then I don't want to use that tedious method. So what we can do is convert it into base 16 first. So again the same rules. Whenever you want to convert it into base 16, how can I do that? 32 divided by 16. What is the quotient and what is the remainder? Quotient is 2 and remainder is 0. And then 16, when I divide it with this, what is the quotient? Quotient is 0 and the remainder is 2. Therefore, what is 32 base 10 in 16? It is nothing but 2, 0. 2 and 0 is in 16. Now you convert this number to base 2. How can I convert the number to base 2? We already know that a number which is represented in 16, if a digit is represented in base 16, you have to use 4 bits or 4 digits to represent it in base 2, which means 4 bits have to be used. For 2, 4 bits. So what is 4 bit representation of 2? 0, 0, 1, 0. And what about 0? 1, 2, 3, 4. So this is 32. Sorry, base 2. Value of 32 in base 2. Anyway, these two are insignificant, you can remove it. Therefore 1 followed by 5 zeros. 1 followed by 5 zeros. Got it? Therefore what I am trying to say is, whenever you want to convert a number from base 10 to a smaller number system, let's say like 3, then better you convert it to 9, because you have to divide that number with 9 nines and then convert it to 3, or it is even simpler if you can convert it to base 27 and convert it to 3. Like that you can choose among them, right? If a very big number is given, don't try to keep on dividing with 2, keep dividing it with 64 or 128 or 1024. Even you convert it into 1024 and later you convert it into the base 2, right? I hope you are getting it. But generally that big numbers will not be given in the exam, but it is worth noting this this point. Okay, let me tell you one more example and I'll wind up with that. So let us say you are talking about 65 65 base 10 and I want to find out what its number is in base 2. If you go with this normal conversion, it will take a lot of steps, right? So what is the other way? You convert it into base 16 and then convert it to base 2. That way it is simple. So what can you do is convert it to base 65. I want to convert it to base 16. So when I divide with 16, what is the quotient? 4. What is the remainder? 1. Right, and when I divide with 16, what is the quotient? 0. What is the remainder? 4. Then you take this. Therefore it is 4 1 base 16 is 65 base 10. Now you convert this to base 2 easily. So how? Represent 4 in 4 bits and represent 1 in 4 bits. If I represent 4 in 4 bits, it is going to be 0 1 0 0, and I represent if I represent 1 in 4 bits, it is going to be 0 0 0 1. Right, so this is in base 2. So this is the value of 65. We got it easily. If you have to go with that method, you have to do a lot of steps, right? So now if a very big number is given, for example 1 6 7 8 9 1 0, something is like this. This very big number is given and you are supposed to convert it to base 10 base 2. This is given in base 10, you are supposed to convert it to base 2. Then the best thing is you go with bigger numbers and then divide it, and then you can, after getting the result, you can go with the base 2. I'll try to divide this one with 1024 and get the reminders. Okay, using calculator I'll do it. I'll try to divide it with 1024. If calculator is directly having base 2 represented, is fine, but then I don't know if calculator will be having base 2 representation for this. So in case if you don't have it, then divide with 1024 and then get the reminders, and then you write them bottom up, the reminders, and then you convert each remainder into base 2 later. Otherwise, if you keep on doing with that method, it is going to take a lot of time. Take a higher powers of 2, convert it into that, and then from there you can convert it to 2. That is what I mean to say. So this is how all the conversions work. And I didn't discuss about the fractions. Fractions also you can do it the same way. So okay, we shall do it later in some later floating point numbers. Okay, as of now we shall fix it to this. And we shall see some of the questions again, the examples, more examples. Okay. We shall see a topic called complementary number system. Okay. So, complementary number system. The main reason behind introducing this complementary number system is, earlier what happened was, whenever we had to use two numbers, we generally use a adder, but then if you have to subtract a number from some other number, then we have to use a subtractor. That is what we do on even using pen and paper. But then this particular subtraction is going to involve borrow, right? And when we have to borrow, we might have to go far away sometimes and then borrow a bit from here, from there, and then subtract it here. So subtraction is bit complicated in order to design it as a circuit, and moreover, if we already have an adder, again putting a subtractor on the chip on the motherboard, this circuit for subtraction is going to make it bulky and costly. So the main reason, remember this, the main reason behind proposing this complementary number system is to do the subtraction also using the addition circuit only, which means the main advantage is, why we are going for this, the main advantage is subtraction can be done using addition only. So subtraction can be done using addition. That is the reason why we are going for this complementary number system. So if you have to understand the intuition behind it, how it is designed, why it works, why certain things work here, you have to understand a lot. So instead of directly giving you the formula and then asking you to by heart it and the conditions, what I'll try to do is I'll try to explain everything, why it works, where did we derive it from. So before going to the theory, let me take examples and explain you with the examples, and later I'll discuss about the theory. So first let's understand what is complementary number system and how many complementary number systems are there and how each one works. So for example, if the base is B, if we have base B, which means the radix is B, in base B number system we generally have two types of complementary number systems. So one is called as b minus 1's complement, b minus 1's complement, which means we can work completely in this system, or the other is called as b's complement, which means we can either use for a given b, either we can choose this system or this system, and subtraction will become easy using an adder. So this particular b's complement is called as radix complement. The reason is the radix of the radix here is b, and we are using b's complement only. That is why it is also called as radix complement. And in this one, since we are using b minus 1's complement, it is also called as diminished radix. Diminished radix complement. So try to understand this. Now what is that I am trying to say is, we are going to use something called as complementary number system, which is nothing but writing a number in some other form, which will make the subtraction easy using just the addition. So using this complementary number system, addition can be done very easily. Now for example, if you have a base b, then we can have two types of complement. One is b minus 1's complement and other is b's complement. So b's complement is called as radix complement and b minus 1's complement is called as diminished radix complement. So in order to get the complement here, let us say we have a number x. Then in this diminished radix complement, if you have to find out the complement of number x, if you want to find out b minus 1's complement of number x in this b minus 1's complement system, what happens is we have to take b power n minus 1 minus x, where n is b is base, the radix, and n is the number of digits in x. Therefore if you write like this, this is called as b minus 1's complement of x. And in case of this b's complement, the radix is nothing but b power n minus, the complement is b power n minus 1. So if you observe these two, the difference between b minus 1's complement and the difference between b's complement is simply a 1, which means if we can find out the b minus 1's complement and if you add a 1 to that, you are going to get b's complement. So that is what we are going to do. Now you might get a doubt why we are doing that. So the intuition behind it, the logic behind it, we shall see later. First of all, let's try to get used to these conventions. So let's try to see for every base what is b minus 1's complement and b's complement. Then we shall go into the problems. Then we can again get back and see why this one is working like that. Okay. So now let's say base is 2. In base 2, how many complements can we have? One is b minus 1, which means 2 minus 1's complement, and other is b's complement, which means one is we can have 1's complement and other is we can have 2's complement. Okay. And let's say base 3, then how many complements we can have? So one is we can have 2's complement and other is we can have 3's complement. Now if you observe it, 2's complement is here as well as 2's complement is here. So are they both same? No, they are not same, they are different. Then how to find out which one is what? So from the context, from the base, you can find out which one they are talking about. Okay, even though they are looking as they both are same, but they are different. So why are they different? Just see this. Now if you have a number x, then how can we find out 1's complement in base 2 in this one is, we have to take 2 power n minus 1 minus x. This is the formula in order to find out the 1's complement in base 2. Now what about the, how to find out the 2's complement in base 2 is x complement equal to 2 power n minus x. So this is 2's complement in base 2. What about base series 2's complement? So base series 2's complement will be like this: x complement equal to 3 power n minus 1 minus x, right? And what about this base series 3 power n minus x? Getting this? So on. We can have even base 10 complement, like for base 10 also we can have complements. So in base 10 we have two types of complements. One is 9's complement and other is 10's complement. Now I think you can guess, in place of b if we can put 10. Okay, how am I getting this? In place of b I am putting 2 here, in place of b I am putting 3 here. So similarly in place of b if we can put 10 here, what is x complement? So x complement in 9's complement will be 10 power n minus 1 minus x. And what about 10's complement? X complement in 10's complement system will be 10 power n minus x. Got it? So this is how all the bases will work. Similarly you can have base 16 also. Base 16. So I'm just giving you an example. So for every number system, even for base 30 you can go with it, base 100 also you can go with it. So for base 16 what you can have is 15's complement is the diminished complement, and then 16's complement is the actual complement. Okay, so it is radix complement and it is diminished radix complement. So you can substitute the same thing there. So in place of 10 if you put 15 you are going to get this. So what I want you to observe is, in order to get see, every base will have generally two types of complements. One is diminished radix complement and other is the radix complement, and both of them are popularly used, but the most popular or most widely used is radix complement, which means this one. So by writing like this you might not understand anything. What I'll do is I'll take examples and explain you how everything works here. How does it make sense? Now let me take some examples. Let's take base 10. Base 10 is what you are very much used to. So in base 10 I have a number like this. Let's say I have a number 685. This is the number I have. Now I want to find out its ones complement. So ones complement I want to find out. Now what is the formula? So ones complement is nothing but 10 power n minus 1 minus the given number 685. Now what is 10 power n? So what is n here? N is the number of digits. How many digits are there? 3 digits are there. Therefore it is nothing but 10 cube minus 1 minus 685. Now what does it turn out to be? 999 minus 685. So which means finding out the 9's complement in base 10 is nothing but subtracting every digit from 9. See this, it is nothing but 999 minus 685. So in order to get the 9's complement, I have written 1's complement here, it is 9's complement. I am talking about 9's complement. So in base 10, in order to get the diminished radix complement, which is 9's complement, what you are supposed to do is, you are supposed to take the 9 and subtract every digit from 9. So see this. So what do you get here? 4. What do you get here? 1. What do you get here? 3. Got it? Similarly, let's say you have 214. You want to find out what is the 9's complement. Then 999. Then what do we get here? It is 5. And this is 8. And this is 7. Right? And let's say you have 1, 2, 3. You have to find out the 9's complement. 999. So it is 6. It is 7. It is 8. Right? Let's say you have to find out 1, 2, 3, 5 is the number, and you want to find out the 9's complement, and you have to subtract it from all 9s. So what do you get? 4 here, 6 here, 7 here, 8 here. Got it? So likewise you can find out the 9's complement. Now in order to find out the 10's complement, so if you observe this, the difference between 9's complement and 10's complement is just this minus 1. So in 9's complement we have minus 1 extra. Therefore from here, if you have to get this, you find out the 9's complement and add a 1, then you are going to get this. So if you add 1 to this, which is nothing but 315. 315 is called tens complement of this number. If you add 1 to this, which is nothing but 786, which is the ninth complement of this. If you add 1 here, which is nothing but 877, which is tens complement. If you add 1 here, it is nothing but 8765, which is tens complement of 1235. Got it? So that is how in base 10 you can get the ninth complements and tens complement. So why is it useful? We shall get back to that point soon. We shall get back. Now let's talk about base 2 now. So you understood this? In base 10, in order to get the ninth complement, you are supposed to subtract everything from 9. So let's talk about. So in base 2, if you have to get 1's complement, which is nothing but diminished radix complement. So what should we do? You have to take 2 power n minus 1 minus the given number. Then you are going to get the 1's complement. What is n here? N is the number of digits in the number x. So let's take an example and see it. So let's say I have a number x in base 2 only. Let's say the number x is 1011. So let's see what happens for it in 1's complement. So how many digits are there? 1, 2, 3, 4, which is nothing but 2 power 4 minus 1 minus x. So x is 1011. So now what is 2 power 4 minus 1? 2 power 4 is 16, minus 1 is 15. So if you try to write 2 power 4 minus 1 in binary, it will become 1, 1, 1, 1 minus x. X is 1011. Therefore, what did it turn out to be? It turned out in such a way that in order to get the 1's complement, you have to take the given number, take each digit and subtract the digit from 1. Then if you write the result, then you are going to get the 1's complement. Then what do we get here? It is 1, 1, 1, 1, 1, 0, 1, 1. Then what do we get here? 0, 0, 1, 0. So this is the 1's complement. So if you observe it, in order to find out the 1's complement of any number, you have to just take the number and subtract it from 1's. And incidentally, it even turns out that in order to find out the 1's complement, if you check it, just change the number from 1 to 0 and 0 to 1, then you are going to get the 1's complement. The actual rule is, if you have to get the 1's complement, you have to subtract that number from this number, right? Which turned out to be this. And it turns out that in order to get the 1's complement, you have to subtract every number from 1. That is what everything turned out to be. Incidentally, it also turned out that in order to get the 1's complement, you have to just take 1 and make it 0, take 1, make it 0, take 0, make it 1, take 1, make it 0, which means if you flip from 1 to 0 and 0 to 1, you are going to get the 1's complement. Got it? So you can check one more example. Let's say I have a number 1, 0, 0, 1. I want to find out the 1's complement of it. What should we do? Take 1, 1, 1, 1 and subtract it from there. Then what do we get? 0, 1, 1, 0. Again, if you observe it, it is nothing but flipping 1 to 0 and 0 to 1, then we are going to get the 1's complement. Got it? So let's take one more example. 1, 1, 0, 1, 1, 0, 1. Now we have to subtract it from 1, 1, 1, 1, 1, 1. Then what do we get? 0, 1, 0, 0, 1, 0, 0. Again, if you check this, the flipping rule again works here. You take all this and flip them, you are going to get this. So that is how 1's complement work. Now what about the 2's complement? 2's complement is nothing but 2 power n minus x is 2's complement. If 2 power n minus 1 minus x is 1's complement, then 2 power n minus x is 2's complement. What is the difference between these two? The only difference is we are going to add a 1 there, right? So which means you find out the 1's complement and then add a 1, then you are going to get 2's complement, right? So if you observe it, this 1, adding a 1 is universal, which means you can take any number system, any base. Once you find out the diminished radix complement, which means once you find out the b minus 1's complement, then in order to find the b's complement, you are going to add 1 only. The reason is 1 is 1 in any number system. So when you have 2 power n minus 1, the 1 is same in all the number systems. Therefore, it is easier to find out the diminished radix complement and then convert it into radix complement. So now these are all 1's complement, right? So now let's find out the 2's complement. In order to find out the 2's complement, you have to add a 1. Then what does it turn out to be? It is 0, 1, 0, 1. add a 1 to this, then what does it turn out to be? 0, add a 1, okay, 0 1 1 1, add a 1 here, what does it turn out to be? 0 0 1 0 0 1 1, right? Now I'll tell you what happened here. So one thing to observe is, in order to find out the 2's complement, you can find out 1's complement and then convert it to 2's complement, and there is one more simple trick. So they say that you wash the bits from the left hand side, sorry, this LSB, and once till you find out the first one from LSB, you leave the bits as it is, and after you see the first one, you complement the remaining bits, which means you start from the left hand side, and whenever you see the first one, you leave it as it is, and the remaining bits you just complement it, right? Here also, whenever you see the first one, you leave it as it is, and the remaining bits you just complement them, then you are going to get the 2's complement. What I am trying to say is, in order to find out the 2's complement, you have two methods. One is find out the 1's complement and add a 1 to it. Other is you start from the leftmost, the least significant bit, like that, and whenever you get the first one, that is also called as seek bit. In some books they call it as seek bit. So whenever you come across the first one, leave it as it is and leave all the zeros till that part as it is, and after that part you complement it, right? So probably these examples doesn't give you that feel. I'll take a different example where you can understand it easily. Let's say you have 0 1 1 0 0 1 0 0. This is the number I have, and I want to find out the 2's complement. Finding 1's complement is straightforward. You can just complement it and get the 1's complement. Now I want the 2's complement. How can I get the 2's complement? See this. You start from LSB and start looking at the bits till you get the first one, which is the seek bit. You write all the bits as it is, and after that bit you just complement the remaining bits. So what does it mean? From here you just write all of them as it is, 0 0 till the seek bit as it is. After that you have to complement everything that you get. Now what are these? 1 1 0 0 1. So this is the 2's complement of the given number. If you don't trust me, you can find out the 1's complement of it and again add a 1 and you will get the same number, right? So if you want one more example, we can see it. I hope that you are understanding it. I know that you know all this, but still I want to give you the correlation among all the number systems once, so that in exam whatever number system they ask, you will be able to answer. It's not just about 1's complement or 2's complement. They might ask you 7's complement, 8's complement, like that. So just for some practice here. Once you understand these basics, later part will be easy for me. So now 1 0 1 1 0 1 0 0 1 0 0. Let's say this is the number I have. Now I want to find out the 2's complement. What is the method? Find out the 1's complement and then you can get the 2's complement by adding a 1. But without doing that, you start from the least significant bit and you keep scanning it, and whenever you see the first one, till that part you leave it as it is, and after that you are going to complement the remaining bits, right? So here this first one is going to be the seek bit. So till this part you leave the bits as it is, which means you have to leave it as 0 0 1, and after this you have to complement everything. All of this have to be complemented. What do we get? 1 1 0 1 0 0 1 0. So this is the 2's complement of the given number. Got it? So let's see one last. Let us say 16. Shall we take 16? We shall take the number system 16 and see what are the 2 complements we have in that, and let's see what happens with each one of them. Okay. So let us see base 16. Base 16. So in base 16 we have 2 complements. One is diminished radix complement, which is 15's complement, and other is 16's complement, radix complement, right? I want to do both of them. Now in order to get the 16's complement, let us say I have a number like this. X is the number x given is 1 2 3 4, and I want to find out 15's complement. How can you find it out? It is 16 power 4, n is 4 digits, minus 1 minus x. Okay, And 16 minus 4 is, see, if you are not able to understand what this is, 16 minus 4, 16 power 4 minus 1 is actually the maximum number that could be represented in a hexadecimal number system using 4 digits. We have already derived this. What is b power n minus 1? B power n minus 1 is the maximum number that can be represented in a base b number system with n digits, if you remember that. Okay, and similarly 16 power 4 minus 1 is the maximum number that can be represented in a 4-bit number, in a 4-digit number in base 16. So what is the maximum number that you could represent in a using 4 bits or 4 digits in 16 bit in 16 base? It is nothing but f. How did I write this? By this, right? In fact, if you write b power n minus 1 where b is the base, it is nothing but the maximum number that can be represented in a base b using n places, right? So here also always remember this, it can be written as b minus 1, b minus 1, b minus 1, so on n times or n digits, where b minus 1 is the highest possible digit in base b, right? Here f 4 times because of this 4, and the highest possible digit in base 16 is 15, that is why f, right? Minus x is 1, 2, 3, 4. So in order to solve this, you should know these basics: a, b, c, d, right? So what is a? 10, b is 11, c is 12, d is 13, e is 14, f is 15 in hexadecimal, right? Now I have to subtract this number from all this. F 1, 2, 3, 4. Fine. What is f? 15. 15 minus 4 is 11. What is 11? B. Alright. What is f? 15. 15 minus 3 is 12. So what is 12? C. What is f? 15. 15 minus 2 is 13. So 13 is what? D. F is 15. 15 minus 1 is 14. So which is nothing but E. Therefore, this is the complement of this in 15, right? Which means E, D, C, B. This one is 15's complement. 15's complement of 1, 2, 3, 4. Now, how to get the 16's complement? 16's complement of 1, 2, 3, 4 can be obtained by taking the 15's complement and adding a 1 to that. So how does it work? E, D, C, B is the 15's complement, and if I add a 1 to that, so what is B? B is 11. So 11 plus 1 is 12. 12 is nothing but C. C, C, D, E. Therefore, this number is 16's complement of 1, 2, 3, 4. Got it? So this is how we can get the 15's complement and 16's complement. So what I mean to say by doing all these examples is, for every base we generally deal with two types of complements. One is the radix complement, other is diminished radix complement. Why are we doing all this? Why are we introducing these special rules, and why are we doing all this is just to do one simple thing, that is subtraction. Subtraction can be done using the adder just by using the complement number system. So just to do that possible, just to make it possible, we have introduced all these rules and all these systems and all these formulas. Now why should it all work? Why is this called complement? Why is it called complement, and why is it not called negative? Or what is the relationship between complement and subtraction? Why this complementation? We shall see now. Okay. Now let's talk about Hamming code. Hamming code is single bit error correction code. So it means that if there is an error in one bit, then it will correct it. So why are we interested in only in one bit is, one bit error is the most frequently occurring error, and the probability that many bits or more than one bit get corrupted is very low. That is why we are interested in one bit error correction. Now how does it work is, I'll take this theory for some time. Later with problems it will be very easy. Let me finish some theory here. Let us say we have to we are sending m bits. Okay, so m is the number of bits in the message. Now what we use is, to the actual message we add some parity bits. These parity bits are used in error correction. Okay, so let us say we are going to send actual data that has to be transmitted is m bits. To these m bits we add extra p bits, p parity bits and these are redundant. These are useful only for error correction. Okay, and now we'll be transmitting it to the other side. Now when this message containing m plus p bits, totally m plus p bits, is received by the other side, then what are the various cases we might get? Various cases will be, there will be no error at all, or there can be a single bit error in any one of them. Now we are interested in knowing only about single bit error. So our assumption is, if there is an error, there will be at most single bit error. 2 bits are not going to get corrupted. Okay, now what I am trying to say is, when you are transmitting these m plus p bits to the other side, there will be no error at all, or any one of these m plus p bits might get corrupted. Therefore any one of these m plus p bits can be corrupted. So m plus p cases, each one representing 1 bit position that can get corrupted, or no bit can be corrupted, which means there is no corruption at all. So whenever receiver receives these m plus p bits, he might have to handle these many cases. So the total number of cases we have is these many. Now we should be able to detect each one of these cases separately. So how are we going to do that? Using p bits. Therefore using p bits we have to get those many combinations as there are the number of cases, right? So using p bits I will get 2 power p combinations, and now these p combinations should be able to handle all these cases. Therefore 2 power p should be greater than or equal to m plus p plus 1 is the condition. Got it? Okay, I don't know if you understood this or not. Now let me take an example and I'll tell you. So let us say we are going to send 4 bits. Okay, 4 bits of information. Now to these 4 bits, just to do this correction part, I'll be adding p number of parity bits, and I don't know the value p. Now when I'm sending these 4 bits, along with 4 I'll be sending p. Therefore the total number of bits that will be transmitted is 4 plus p, right? So when the receiver receives these 4 plus p bits, any one of these 4 plus p might get corrupted. Therefore these many cases we have to handle. Along with that there will be no corruption at all, right? Which means 1 case. So how many total cases we are supposed to handle? 4 plus p plus 1, which is nothing but p plus 5 cases we have to handle. How can we handle these cases? Using the p parity bits. Therefore our p parity bits should be producing 2 power p combinations, and these number of combinations should be greater than or equal to the number of cases. Then only each combination can differentiate each case, right? So this is the condition. Then it turns out that this entire number turns out that, let's see what is the value of smallest value of p that can satisfy this equation. See, the reason is simple. We want to add as less number of parity bits as possible, because we don't want to send many parity bits which are redundant, of course. Therefore I want to find out the smallest value of p which will satisfy this inequation. So if I put p equal to 1, it is 2 and it is 6, it is not satisfying. P equal to 2, it is 4, it is 7, not satisfying. P equal to 3, it is 8 and it is 8. So if I put p equal to 3, it is 2 power 3 is greater than or equal to 3 plus 5. Yes, it is satisfying. Therefore how many number of bits, parity bits I should add in order to do error correction in 4 bits? It turns out that it is 3 bits. Therefore I'll be sending 4 message bits plus 3 parity bits, which means totally I'll be sending 7 parity bits. 7 bits to the receiver. Now when 7 bits are being sent, then what are the cases we get? An error might occur at first bit or second bit or third bit or fourth bit, fifth bit, sixth bit or seventh bit, or there may be no error at all, which means 0. Therefore we are supposed to handle all these 8 cases. Will we be able to handle all these 8 cases using the combinations? It is possible, because since we are having 3 parity bits, we have 2 power 3, which is 8 combinations, right? So each combination can handle each case. Now the next point is, We understood that if you are sending 4 bits, we are supposed to send 3 parity bits. But then how should we arrange? How should we arrange these parity bits? That is one next important question. So the reason we should be, the logic behind this technique is simple. Now when we are having these 3 parity bits, each bit will be assigned the responsibility to take care of some message bits. Out of these 4 bits, each bit of parity will be assigned to take care of to take the responsibility of some of the message bits, right? And now if anything goes wrong in those selected bits, that particular parity bit will say yes, these are one of these has got corrupted. Now how to form this, how does it all work? Let's take an example and see. Okay, now I'll solve few examples. Later I'll tell you how it is really working, but try to remember the way I'm doing it. Okay, now we just have seen that if number of bits, message bits have to be 4, then the parity bits that have to be sent is 3 along with them, right? Therefore totally for 4 message bits I'm going to send 3 parity, so totally 7 bits. Now let's take an example. Let us say the message that has to be transmitted is 1100. Just for the sake of example, I'm just doing this. Or you can even take a BCD number. So let us say we are sending a BCD number 0101, so which is 5. So we are trying to send a number 5 to the other side. So in order to correct this single bit, we are going to add 3 parity bits. So totally how many bits are we going to send? 7. So you write down like this: 1, 2, 3, 4, 5, 6, 7. Okay. Now in this 7 bits, at every power of 2, this is 2 power 0, 2 power 1, 2 power 2. At every power of 2, try to include the parity bits, which means parity bit P1, parity bit P2, parity bit P3. And at every other position, you try to include the message bits, which means message bit M1, message bit M2, message bit M3, message bit M4, right? And now we have to fill in these places. We know already what to write in M1, M2, M3, M4, that is already given. We are supposed to fill in P1, P2, P3, right? So M1 is 0, M2 is 1, M3 is 0, M4 is 1. That is done. Now how to fill this is, we are going to select few bits for every parity location, which means every parity bit is going to take care of some of the message bits in such a way that the parity along with those messages is going to make either even parity or the odd parity. By default, we are going to use even parity method. Everyone is using even parity method only. Either you can go with odd parity or even parity, it is up to you. But here by default we are using even parity. Okay, everyone is using that. Now after this, how to know which parity bit should be assigned what? For that reason, see this. Let us assume C1, C2, C3 are the final things that the receiver will check. Let us call them as check bits. So C1, C2, C3 are the bits that the receiver will calculate in order to find out which place the error has occurred. Now when you are sending 7 bits, what are the various combinations that you, or what are the various cases that you might get? There might be no error, or there might be error at position number 1, position number 2, position number 3, so on, position number 7. Therefore we have to handle all these 8 cases. So one case is there might be no error at all, other case is there might be error at position number 1 or position number 2 or position number 3 or position number 4 or position number 5, position number 6 or position number 7, right? So for every position there might be an error. See, when you are sending these 7 bits, it is not just the data might get corrupted, even now the parity might get corrupted, and therefore you will not be able to distinguish whether the data has got corrupted or parity has got corrupted. So you are supposed to find out every error. Error can occur either in parity bits or in message bits. We are supposed to correct them. Okay. Now see this. Now how do we know? How do you know which one to assign what is? See this. P1 will be assigned for this combination. P2 will be assigned for this combination. P3 will be assigned for this combination. So which means, if you observe this column, see later you will understand why I am doing this. Now understand the method. Now observe this column. Where are ones? 1 is here, so this is 0, this is 1, this is 2, this is 3, this is 4, 5, 6, 7. Now what are the combinations that are having 1 for C3 for combination 1, 3, 5 and 7, right? Therefore C3 or let's say combination 1, 3, 5, 7 fall in one category, isn't it? So what does it mean? The parity bit present at position number 1 is going to take care of the bits 3, 5 and 7. See this. The position at the bits 3, 5 and 7 are some of the message bits. 3, 5 and 7 are some of the message bits which will be taken care by parity bit 1. So you need not by heart it. Once you write this, you will be able to get that. Only thing is you have to write C1, C2, C3 like this and P1, P2, P3 like this. Even if you don't remember this, by looking at this, once you get the position number 1, you already know that at position number 1, parity 1 is present, right? And now look at the column C2. If you look at it, what is it covering? So what are the ones here? One is at 2, and other is at 3, and other is at 6, and other is at 7. What does it mean? The parity bit 2, P2, will take care of 3, 6 and 7. Check this. 3, 6 and 7 are some of the message bits which will be taken care by P2, which means it is the responsibility of P2 to see that the parity of all these bits put together is even. Okay. And now if you look at this one, this particular C3, just see this. What are the bits it is having? 4, 5, position 6, 7. What does it mean? It is the responsibility of P4. It is the responsibility of P4. Sorry. It is 4, 5, 6, 7 only. Yes. It is the responsibility of the bit position, placed at 4. So 1, 2, 3, 4 means here. It is the responsibility of the 4, which means P3, to take care of 5, 6 and 7, which means this one and this one. Got it? So that is how responsibilities are allocated. Therefore this is the responsibility of P1, this is the responsibility of P2, and this is the responsibility of P3. P3 is present at position number 4, P2 is present at position number 2, and P1 is present at position number 1. I think you understood this. Simple. What did I do till now? A message is given and we know that we are supposed to add 3 bits of parity. How do we know that we are supposed to add 3 bits of parity? From the inequation that I have written earlier. What is that? 2 power p is greater than or equal to m plus p plus 1. In that one, the smallest number of p that can satisfy is 3. So if 3 is satisfying the inequation, 4 will definitely satisfy. But then don't go for 4 because it is not required. We have to keep it as low as possible. Got it? And then I am writing this. Only thing you should remember is I am numbering them from 1 to p plus m. Right? Here p plus m is 7. 1, 2, 3, 4, 5, 6, 7. Right? And then at the positions at powers of 2 you write the parity bits, and at the remaining positions you write the message bits. Got it? And then you write the check bits. So these check bits will be computed at the receiver side, C1, C2, C3. Now if you observe it, C3 is going to take care of 1, 3, 6 and 7, which means if C3 is 1, it means that there might be an error at 1, 3, 5 and 7. So 1, 3, 5 and 7 will belong to one category or one group, and in that group the parity bit present is P1. So what does it mean? It is the responsibility of P1 to take care of these message bits 3, 5 and 7, or it is the responsibility of P1 to make the parity of this entire complete group as 0 or even, right? And once we send this to the other side, if there is any bit corrupted in 3 or 5 or 7 or 1, then the parity will change. Got it? Through that you can understand that one of this, by looking at P1 and this group, you can understand that one of this is changed. I'll tell you how it works. Let's compute it completely. So likewise, every parity bit is being assigned some of the data bits which it has to take care. Now let's see how this one works. Now we have to fill this part P1. Now see this, P1 is taking care of 3, 5 and 7. So P1 is taking care of 3, 5 and 7. So if you see this, 3, 5 and 7, they have 0, 1, 1, which means even number of ones is already present. So we wanted to maintain even number of ones. So you put a 0 here. So completely in this group 1, 3, 5, 7. Now even number of ones are present. That is what is called even parity. I want to maintain that. So I think you know even parity or odd parity, right? If I have 1 1 1 0, what is the parity bit you should place here in order to make the parity even? 0, because by putting 0 here, the number of ones is going to be even. If I have 1 0 0, what is the parity bit I should put here so that the number of ones are going to be even? 1. So we count the number of bits, number of ones, and if we have to maintain it as even parity, we put the number appropriately so that the total number of ones is going to be either even or odd. Okay, fine. Now check the next one. Now I want to check P2. See this? Now P2 is going to take care of messages 3, 6 and 7. So 3 is 0, 6 is 0, 7 is 1. So in this 3, 6 and 7 there are odd number of ones. To make the total number of ones as even, we have to put 1 here. Now next one is P3. P3 is going to take care of 5, 6 and 7, which means 4 is going to take care of 5, 6 and 7. So the location number 4, which is P3, is going to take care of 5, 6 and 7. In 5, 6 and 7, if you observe it, there are even number of ones. Therefore you put 0 here. So we make it even parity. Got it? Therefore, even though the message that we want to send is 0101, which is 5 in BCD, the message that we will be sending is after adding the parity bits 0 1 0 0 1 0 1. This is the message that we will be sending. Got it? Now how will this be useful in correcting the error is, we shall see what happens. Now let us say this particular bit got corrupted. This particular bit, which has to be 1, has got corrupted to 0, and so at the sender, at the receiver, even though we have sent this, the receiver has got 0 1 0 0 1 0 1. So the receiver has got that. Fine. Now 1 2 3 4 5 6 7. Now let's see how will the receiver calculate it. Now receiver has to calculate 3 bits, the check bits. What are they? C1, C2, C3. How will the receiver calculate C1, C2, C3? Watch it now. Now what is C1? C1 is nothing but this one, right? So C1 contains the group 4 5 6 7, this one, right? So it will try to check 4 5 6 7 if it is even parity or not. Yes, the 4 5, the bit, okay, it has got this one, right? We have to corrupt it, so it is 0. Fine. Now 4 5 6 7, if it is supposed to have even parity, but then because of this corruption it got odd parity. Therefore C1 is going to be 1. It is saying that there is something wrong in this. So we got it. And now what about the next one, C2? See this? C2 is going to take care of 2 3 6 7, which means 2 3 6 7. In these 4 bits here, the bits received 2 3 6 7, we have even number of ones. Therefore what is that we are going to say? No error here, right? And in the C3 is going to take care of 1 3 5 7, right? So 1 3 5 5 7, which is 1 3 5 7. So which is even? Sorry, 1 3 5 7, which is odd. Only 1 1 is there. Therefore this one is also error. So 1 0 1, which means 5. Location number 5 has got error. This is location number 5. This is location number 5. We are able to know that location number 5 has got error. Therefore we can correct it. See, in one good thing about binary numbers is, if you can identify the position of the error, you need not say what the actual bit is, because you have to just toggle the bit. If it is 0 there, you have to toggle it to 1. If it is 1 there, if it is you have to toggle it to 0. It is just like this. If you say that this bit is corrupted, then correcting it is easy. If the bit you got is 0, then the original bit would have been 1. Got it? Okay. So now why do you think that this method works is simple. See, what is this one saying? This one is saying that in the bits that I have checked, there is an error and I don't know which one it is. This one is also saying that in the bits that I have checked, there is an error and I don't know where it is. And this one is saying that in the bits I have checked, there is no error, right? Which means C1 and C2 are saying that there is error. So C1 is nothing but, C1 is representing 4 5 6 7. C3 is representing 1 3 5 7, right? which means both are saying that there is an error in these two. Now what is the intersection of these two? Intersection of these two is 5 comma 7. Got it? And now C2 is saying that I don't see any error in my bits. So what are its bits? 2 3 6 7, which means we have to minus 2 3 6 7, right? So we doubt that there is an error either in 5 or 7, and it is saying that there is no error in 7. Therefore what is the error? 5. That is how it works. So we are going to allocate some number of bits to some check, and then they are going to check, and if some of them, no, if two of them are saying that there is an error, we have to take the intersection of it, and then if the other one is saying no error, we have to take minus. Let us say all of them are saying that there is an error, which means C1, C2, C3, all of them are saying that there is an error. Then what could be the error? You have to take intersection of all these. So intersection of all these is nothing but 7. Clearly it is making 7, isn't it? Let us say C1, C2 and C3 are saying that 1 1 0, which means C1 is saying there is an error, C2 is saying there is an error, but C3 is saying no error. Now we have to take intersection of these two. So intersection of these two is 3 comma 7, but then C3 is saying there is no error, which means from this we have to subtract 4 5 6 7. So what will go off? 7 will go off. What will remain? 3. So it is 6, right? C1 C2. Oh, C1 C2 is this one. So 6 7, sorry. So C1 C2 is representing this one. So which means we are supposed to get 6 7 here, and then 7 is removed, therefore 6. Got it? Okay, I don't know whether you understood with this example or not. I'll take more examples and I explain you. Okay.